Hey everyone, welcome to Simplilearn's YouTube channel. In this session, we will be learning the data structures and algorithms full course. But before we begin, let me tell you guys that we have daily updates on multiple technologies. So if you're a tech geek in a continuous hunt for latest technological trends, then consider getting subscribed to our YouTube channel and don't forget to hit that bell icon to never miss an update from Simplilearn. Now without further ado, let's get started with the agenda for today's session. First, we will understand what exactly is an algorithm. Followed by that, we will understand what are data structures. Once we are done with the fundamentals of algorithms and data structures, we will continue with pointers in C programming language. Later, we'll start with our first data structure, that is the arrays in data structure. Next, we will understand a little more detail about arrays, where we will understand the two-dimensional arrays and multi-dimensional arrays in data structure. Next, we will dive into the linked list in data structure. After that, we will understand linked list in a much more detail by understanding the variety of linked lists, that is the singly linked list, doubly linked list, circular linked list. After that, we will get started with stacks in data structure. After stacks, we will understand queues and dequeues in data structure. Followed by that, we will understand our linear search algorithm. Next, we will continue with tree data structures. And after that, we will understand an algorithm based on tree traversal. After we understand the tree data structure and its traversal, we will get started with binary trees and binary search tree. Next, we will have recursion. After understanding recursion, we will again start with trees, where we will understand AVL trees in data structure. Followed by that, we will learn the bubble sort algorithm. Next, after understanding the bubble sort algorithm, we will get started with insertion sort. Next, we have selection sort, merge sort, quick sort algorithms. Once we are done with the sorting algorithms, we will get started again with the data structures, where we will dive into graphs. Once we are done with the graphs, we will understand the relevant algorithms, which are the Krushkal's algorithm, backtracking algorithm, and then we will understand the spanning tree in data structures. Once we are done with the spanning trees, we will understand the breadth first search algorithm and depth first search algorithm. Later, we will understand the greedy algorithm. And finally, we will wind up the session by discussing Prim's algorithm. So all the agenda pointers that we discussed in the agenda will be explained in detail, theoretically as well as practically. So make sure that you stick to the end of this tutorial to understand every data structures and algorithms concept that you ever need in detail and with perfection. So without further ado, over to our experts.
We will discuss what is an algorithm. But before we begin, let me tell you guys that we have daily updates on multiple technologies. If you're a tech geek in a continuous hunt for latest technological trends, then consider getting subscribed to our YouTube channel and don't forget to hit that bell icon to never miss an update from Simplilearn. Now without further ado, let's get started with the agenda for today's session. First, we will get started with what is an algorithm. Followed by that, we will look into the characteristics of algorithm. Next, we will learn how to write an algorithm. Moving ahead, we will look at algorithm analysis and algorithm complexities. After that, we will discuss the advantages and disadvantages of algorithms. And finally, we will see some differences between algorithms and programming. I hope I made myself clear with the agenda. Now, let's get started with the first point, that is, what exactly is an algorithm? So how does algorithm work in real life? So we'll have a use case here. On my screen, we have a lady and she is Shreya. Shreya wants to make some tea, and for that she is following some steps. So the first step is she'll take a pan and fill it with water and place it on a gas stove. Followed by that, the second step is she'll make sure that the water comes to a nice boil, and then she adds some tea leaves and sugar. Followed by step 2, we have step 3, where she'll allow the leaf to be fully expanded and she'll add some milk after that. Next, we have the step 4, where she will wait for the tea to come for a good decent boil. Next, we have step 5, where she'll turn off the gas and she'll take the pan off from the stove and the tea is ready to get filtered. And lastly, we have the step 6, where she is all set with the tea. So in computer science, an algorithm is a method or set of rules that we must be following to perform some specific calculations or other problem-solving operations. As a result, an algorithm is a collection of rules or instructions that govern how a work needs to be conducted step by step to achieve the desired results. To accomplish a task, we first provide some input and then follow a sequence of steps to acquire the required outcome of the input. So that is the fundamental definition of an algorithm, and we also had a use case. And now we will move ahead and understand the characteristics of algorithms. So basically we have 6 characteristics of algorithm. So the first one is it should be clear and unambiguous. The second one is that it has to be well-defined inputs. And the third one is that it has to be having well-defined outputs as well. The fourth property of an algorithm is its feasibility, followed by that finiteness, and finally we have language independence. Now we will look into each one of the characteristics in detail. So first we have clear and unambiguous. So this statement is the one which states that the algorithm should be straightforward, simple and easily readable. Each one of its steps should be distinct in every way and lead it to a single conclusion. So the next one is it should be having well-defined inputs. So this means that an algorithm should indicate what output can be expected, as well as the input should be properly well-defined. Now we have the third one. Similarly, we should also have well-defined outputs. So the well-defined output characteristics of an algorithm means that the algorithm must clearly indicate what output can be expected, as well as the output should also be well-defined. Followed by the third characteristic, we have the fourth characteristic, that is the finiteness of algorithm. So the finiteness of algorithm says that the algorithm must be finite and it must not result in infinite loops or similar situations. So followed by the fourth one, we have the fifth characteristic that defines about the feasibility of an algorithm. So feasibility of an algorithm states that the algorithm must be really simple, generic and practical. It must be able to be executed with resources available. Now the last characteristic of the algorithm is being independent of the language. So it means that the algorithm should be defined in such a way that it is completely independent of the language. It must be simple instructions that can be implemented using any programming language. So these were the 6 major characteristics of algorithm. Now let's move ahead and understand how to write an algorithm. Writing an algorithm does not have any hard and fast rules. Next, algorithms are never created to support a specific programming language. As we all know, algorithms should be capable enough to support the conditional statements such as if else, switch, etc. An algorithm should be capable enough to execute some of the conditional statements such as if else, switch, etc. And also it must be capable to execute the iterative statements such as for loop, while loop, do while loop, etc. We usually create algorithms in a step-by-step manner. However, this isn't always the case. After the problem domain has been well defined, algorithm writing is a procedure that is carried out. We build an algorithm to find a solution to a problem. A problem can be resolved in a variety of ways. Let's look at an example of how to write an algorithm. Consider the following scenario. We need to create an algorithm to determine the largest number among the 3 given numbers x, y, and z. As a result, the initial solution to the problem can be written in this manner. So we begin with reading all the 3 numbers, and in the second step we will have a condition that says if x is greater than y, we will proceed to step 4, else we will proceed to step 5. Next, in step 4, we establish a condition that if x is greater than z, then x is the largest of the 3 numbers. Otherwise, z is the largest. If y is greater than z, z will be the greatest number. Otherwise, y will be the largest number amongst all the 3 in step 5. And the procedure will be terminated. Let's have a look at what the next solution has to offer. In this algorithm, we begin by reading all the 3 variables, then compare all the 3 numbers in the third step to determine the largest number, which is if x is greater than y, then there is another if else statement that states that if x is greater than y, then x is largest. Otherwise, z is the largest. Then there's if else statement which says that if y is greater than z, then y is greater. Otherwise, z is the greatest of the 3 numbers. So this is how we have multiple solutions to the same problem. So after discussing these solutions, we will move ahead and understand algorithm analysis. The algorithm may be studied in two levels. First, before it is made, and then after it is created. The two analyses of an algorithm are as follows. The first one is priori analysis and the second one is the post analysis. So first we will talk about the priori analysis. Priori analysis refers to the theoretical analysis of an algorithm performed before its implementation. Before implementing the algorithm, other parameters such as processor speed might be considered, which does not affect the implementation component. Next, we will talk about post-analysis. A practical analysis of an algorithm is called as posterior analysis, and it utilizes any computer language to build the algorithm. The purpose of this analysis is to determine how much time and space the algorithm takes to operate. Now, after being understood the algorithm analysis, we will be able to comprehend the algorithm complexity. Two methods can be used to assess the algorithm complexity. The first one is time complexity, which states that the amount of time required to finish an algorithm's execution is known as its time complexity. Followed by time complexity, the other one is the space complexity, which is calculated by the quantity of space required to solve a problem and produce an output of space complexity of an algorithm. Let's take a closer look at these complexities. Now we will begin with time complexity of an algorithm. The big O notation is used to express an algorithm's time complexity. The asymptomatic notation is used to depict temporal complexity of big O notation. The time complexity is mainly determined by counting the number of steps required to complete the task. Let's take a look at an example to understand this time complexity in a much better way. If we want to find out a multiplication of n numbers, we can do it by executing a loop from 1 to n, then calculating multiplication when the loop ends. Then multiplication holds the n numbers multiplication and last we return the calculated multiplication. The loop statement's time complexity will be at least n, and when the number of n increases, the time complexity will also increase. While the code's complexity, that is, returns multiplication, will remain constant because its value is unaffected by the value of n and it will obtain the result in every single step. Next, we will discuss about space complexity, which is expressed with big O notation just as time complexity. These four items are stored in space complexity. It initially saves program instructions, then stores constant values, then stores variable values, and finally it keeps track of function cells, jumping statements, and so on. The sum of auxiliary space and input size is used to calculate space complexity. The extra space or temporary space used by an algorithm is referred to an auxiliary space. After learning about algorithm complexity, we will look at some of the algorithm's pros and cons. So let's start with the advantages of algorithms. Firstly, algorithms are easy to understand. Next, algorithms are step-by-step representation of a solution. And lastly, the problem is broken down into smaller bits or steps in an algorithm, making it easier for the programmer. Now, an algorithm also have various drawbacks, one of which being it takes long time to write, hence it is time consuming. Second con of the algorithm is algorithms make it harder to demonstrate branching and looping statements. So followed by the advantages and disadvantages of algorithms, we now enter into the final segment where we discuss the differences between algorithms and programming. So the first difference is that an algorithm is a type of programming. On the other hand, a program is more directly associated with the computer performing one or more tasks, but an algorithm is more of a notation, a technique for solving a problem. Now, let us discuss the second difference. An algorithm can be decoded or run by a human, whereas the program is only run or decoded by a set of compilers of the computer. Now, the third difference. Basically, an algorithm is a design of the solution to the problem. Here, we can only analyze the solution, but we can never run it. But whereas on the other hand, programming is completely a different ball game. Here, you can directly implement a certain phase or an entire program and test the programs and get an output. So the fourth and the last difference between an algorithm and programming is an algorithm is written using natural human vocabulary, whereas programs are written using any programming language such as C, C++, Java, Python, etc.
We live in an information age, which means data and information are the heart of everything we do. The IT sector in which we work requires a lot of data and information which is widespread and can be stored anywhere. As a result, the question arises as how do we store this data so that we can retrieve it quickly for the further use. So, hello everyone, welcome to the Simplilearn YouTube channel. In this session, we are going to discuss an introduction to data structures. But before we begin, let me tell you guys that we have daily updates on multiple technologies. So if you are a tech geek in a continuous hunt for latest technological trends, then consider getting subscribed to our YouTube channel and don't forget to hit that bell icon to never miss an update from Simplilearn. So without any further ado, let's get started with the agenda for today's session. First, we look at the definition of data structures. After that, we will understand why we need data structures. Later, we will discuss the different types of data structures. Finally, we will look at the importance of data structures. Hope I made myself clear with the agenda. Now, let's get started with our first concept, that is, what are data structures? Data is an information that has been translated into a form that is efficient to movement or processing in computing. As it relates to today's computers and transmission media, data is an information that has been converted into binary digital form. The term raw data refers to the data in its most basic digital format. After defining data, let's look at what data structure entails. A data structure is a data organization, management, and storage format in computer science that allows for efficient access and modification. Or a data structure is an algebraic structure about data that contains a collection of data values, their relationships, and their functions or operations that can be applied to the data. We will now understand why exactly we need data structures now that we have already defined what is a data structure. So, let us have a look at some of the data structure characteristics. The first one is, each data structure allows data to be stored differently. Following that, the data structure allows for more efficient data search and retrieval. Then, specific data structures are chosen to solve specific problems. Last but not the least, it enables the management of large amounts of data such as large databases and indexing services such as hash tables. Let us now look at some real-world examples of data structures. First and the foremost, we have the dictionary. Assume that we are looking for the word Simplilearn in the dictionary. And we know it begins with the letter S. So we can search for this word beginning with the letter S, and then this is an example of array data structure. As a result, this dictionary can also function like an array data structure. Following by that, we have a music player example. If you have a playlist with 3 songs, the second song will play after the first and the third will play after the second. So these will be played without any interruption because all these 3 songs are linked with each other using linked list type of data structure. So followed by linked list, the next example we have is the data structures. The stack of books analogy is a perfect example of the real-time working of the stack data structure. Subsequent to that, assume there is a line of people at a ticket window and the person who comes first gets the ticket. This particular movie window queue is an example for the real-time implementation of queue data structure. Last but not the least, Google Maps. Google Map is the graph data structure in which all the cities and states are connected. If we want to go from one place to another, there may be many ways to do so. So we can use some algorithms to find the shortest path. As a result, the Google Map is a perfect example for the graph data structure working analogy. Following that, we will look at some different types of data structures in this tutorial. So the first type is the linear data structure. The elements in the linear data structure are arranged subsequently one after the other. They are simple to implement because the elements are arranged in specific order. Followed by the first type, the second type is the non-linear data structure, which we will be discussing a bit later. So in linear data structures, we have 4 different types. The first one is the array data structure. Memory elements are arranged in a continuous order in arrays, and arrays elements are of same type. The software program also determines the type of elements that can be stored in arrays. So followed by arrays, we have linked list. Linked lists are completely similar to data structures. Data elements in linked list data structure are linked together by a series of nodes. Furthermore, each node contains the data items as well as the address to the next node. The third data structure is the stack data structure. Elements in a stack data structure are stored using LIFO principle. In other words, the last element stored in the stack is removed first. In stack, operations can only be performed in one end, namely the top. And the last data structure is the queue data structure. Unlike stack, queue data structure operates in the FIFO principle, which states that the first element stored in the queue is removed first. In a queue, insertion and deletion are carried out from opposite ends. Now we will discuss the second type of data structures, which are the non-linear data structures. The nonlinear data structure is the second type of data structure. Nonlinear data structures do not have elements in any order as opposite to the linear data structures. Instead, they are arranged in hierarchical order, with one element connected to one or more others. So the first one in the nonlinear data structures is the tree data structure. A tree data structure is built using nodes and edges. Each element in the tree data structure is called as node or vertex. Each vertex or node is connected to the other nodes or other vertices using edges. And the second one in the list is the graph data structure. A graph data structure is completely like a tree data structure. It also has the vertices and edges. Each vertex in a graph data structure is connected using edges. The only difference between a tree and graph is that in tree you can have n number of vertices, but in graph you will have only 2 vertices. After discussing the graph data structure, we will move ahead into the last segment of this tutorial, that is importance of data structures. So the first one, data structures are widely used in almost every aspect of computer science, both for simple and complex computations. Next, data structures are used in all areas of computer science, including artificial intelligence, graphics, big data, operating systems, and much more. After that, the data structures are an essential component of many computer algorithms because they allow programmers to manage data efficiently. Lastly, a proper data structure selection can improve the efficiency of a computer program or algorithm.
Hi everyone, I'm Vaibhav Khandelwal and I welcome you all to Simplilearn's YouTube channel. In this session, we will learn about pointers. We shall begin our session by learning what a pointer is and its syntax. After that, we will learn about different ways to access variables. Then we will discuss types of pointers. Then we will dive into its use cases. We will discuss about pointer arithmetics, pointer to a pointer, array of pointers, and some concepts like call by value and call by reference. Post that, we will discuss its advantages and disadvantages. Finally, we will take a glance at what is our key takeaways from this session. But before we begin, make sure you have subscribed to our YouTube channel and clicked on the bell icon so you never miss an update from Simplilearn. So without any further ado, let's get started with what are pointers. A pointer is a variable that points to an address of another variable. It is declared using a star symbol, also called asterisk. And then we allocate a memory of a variable to it. We can access a variable's address using the ampersand symbol in the same manner as the pointer declaration. Let's write a code. We will declare a variable a is equals to 5 and a pointer ptr. Then we will assign this variable a's value to pointer ptr. Now let's write a print statement to directly access the variable's value using variable name. Let's write another print statement to print the value of a using pointer. Let's try and execute this program. As you can see, we have successfully accessed variables value using both variable name and pointers. Let's get back to our slides. Now, let's discuss different types of pointers. First up, null pointer, void pointer, while pointer, and dangling pointer. Let's discuss these in details. First up, null pointer. It is a kind of pointer that points to a null memory. As you can see in the figure, here is a pointer which is pointing to a null memory. To get a better understanding, let's try a simple program in the code editor. Let's write a code. First we will declare a pointer var. Then we will assign its value to null. Now let's try to print this statement. Let's execute this. As you can see, since this pointer points to a null or nothing, that's why it doesn't print anything. Let's get back to our slides. Next, void pointer. When a pointer is created with data type void, then this pointer is called void pointer. If we want to print the variable's value, then we have to typecast this pointer to avoid any error. For better understanding, let's get back to the code editor and try it with a simple code. First, we will declare an integer variable a is equals to 5 and a void pointer ptr. Now we will assign address of a to pointer ptr. Let's write a print statement to print this pointer. Let's run this program. As you can see, we are getting an error. That's because we can't print a void variable. To print this, we have to typecast this variable to integer. Let's do this. We can typecast a variable like this. Now let's print this. As you can see, we can print it now. Let's get back to our slides. Next, while pointer. When we create a pointer but don't initialize it by assigning any memory to it, then this kind of pointer is called while pointer. These pointers can be very tricky. They can even cause a program failure or a segmentation fault. Let's get back to the code editor and try it with a simple code. First, let's declare a pointer ptr. But we will not assign it with any address. Let's write a print statement to print it. This time we will directly print it. Let's execute this. As you can see, we are not getting any results because there is no value assigned to it. Sometimes it may even throw segmentation error. Let's get back to our slides. Next, dangling pointer. Let's suppose there is a pointer p which is pointing at a variable. Now, if we deallocate this memory using a free function, then this pointer will point at a free space or a non-existing memory. Then this pointer will become a dangling pointer. To get a better understanding of this pointer, let's try it with a simple code. Let's declare a pointer ptr. Here we will dynamically allocate memory using a malloc function. To do this, we will put int star in a bracket, then malloc function, then in another bracket we will put memory size to be allocated. Now let's declare a variable a and assign its address to the pointer. Now to make it a dangling pointer, we have to deallocate the memory of this pointer. We will use free function for that. Now let's write a print statement to print this pointer. Let's execute it. As you can see, since we have deallocated its memory, that's why it is pointing to nothing. Hence, it doesn't print anything. Let's get back to our slides. Till now, we have discussed pointers, ways to access variables, and types of pointers. Now, let's talk about use cases of pointers. We will talk about pointer arithmetics, pointer to pointer, array of pointers, call by value, and call by reference. Now, let's dive right into it. Let's talk about pointer arithmetics. We can use four arithmetic operations on pointers: increment, decrement, addition, or subtraction of an integer from a pointer. Since pointer operates on addresses, it only makes sense if we apply pointer arithmetics on sequential data structures like arrays or strings. Let's discuss them in detail. First up, increment. If we apply this operator on a pointer, then it will shift this pointer's address to its sequential successor. As you can see in the figure, as we increment the pointer's value, we shift to the next index of the array. Let's get back to the code editor and try it with a simple program. Let's declare an array of size 3. Let's give them some value. We will then declare a pointer and assign it to the array's first element. Now let's write a for loop to traverse this array. In this for loop, we will increment a pointer's value and print this pointer's value to traverse this array. Let's try and execute this program. As you can see, we have traversed this complete array. Let's get back to our slides. Next, decrement. If this operator is applied on a pointer, it will shift this pointer's address to its sequential predecessor. As you can see in the figure, as we decrement this pointer, we also shift to array's previous index. Let's get back to the code editor and try to implement it. Let's declare an array of size 3 and assign it some values. Now let's declare a pointer and assign array's last element's address to it. Now let's write a for loop to traverse this array. In this for loop, we will decrement the pointer's value. Also, we will keep printing this pointer's value to traverse this array. Let's try and execute this program. As you can see, we have traversed this complete array from the back. Let's get back to our slides. Next, the addition of an integer to a pointer. If this operator is applied on a pointer, it will leap forward accordingly. If the integer is 2 and our pointer points at the first element, then the pointer will sequentially skip one element and shift to the next element. Let's implement it in the code editor. Let's declare an array of size 7 and assign them some value. Then declare a pointer and assign it to the array's first element. Now let's take an integer n to add in the pointer. Now let's write a for loop to traverse this array. In this for loop, we will increment the pointer's value with integer n and we will keep printing the pointer ptr's value. Let's execute this code. As you can see, we have traversed this complete array skipping one element at a time. Since we have skipped 3 elements, that's why we are getting last 3 values as garbage values. Let's get back to our slides. Next, subtraction of an integer from a pointer. If this operator is applied on a pointer, then accordingly it will leap backward. If the integer is 2 and our pointer points at the last element, then the pointer will skip one element and shift to the previous element. Let's try and implement it in the code editor. First, let's declare an array of size 7 and assign it some values. Then declare a pointer ptr and assign it to the array's last element. Now let's take an integer n to subtract from the pointer. Now let's write a for loop to traverse this array. In this for loop, we will decrement the pointer's value with integer n. Also, we will write a print statement to print this ptr's value. Now let's try and execute this program. As you can see, we have traversed this complete array from back, skipping one element at a time. Since we have skipped 3 elements, that's why we are getting last 3 values as garbage values. Let's get back to our slides. Let's talk about precedence of these operators. Operator asterisk and ampersand have the same priority as the unary operator increment and decrement. These operators are evaluated from right to left. Let's understand this concept with an example. Suppose if a pointer p points to a variable x, then we can swap x with pointer p in that expression. In the first row, we have y is equal to x plus 1, which means we are storing an incremented value of x in y. Similarly, if we replace x with a pointer p, we can store incremented value of pointer in y. In row 2 and row 3, we are incrementing x and storing incremented value in x itself. We can do this with pointers as well. In row 4, we are attempting to execute pre-increment with a pointer p. In row 5, we are attempting to execute post-increment with pointer p. Here we have to put star p in braces because these operators are evaluated from right to left. So to give more priority to pointer p, we have to use braces as they have highest priority. Let's talk about another use case, pointer to pointer. Basically, in this situation, a pointer will point at a variable via another pointer. We declare it with two asterisk symbol. Let's discuss it with an example. Suppose a pointer 1 points to a variable and another pointer 2 points to that pointer 1. This way, pointer 2 will indirectly be pointing to the variable. Let's go to the code editor and try implementing it. First, we will declare a variable var a pointer ptr1 and a pointer to this pointer ptr2. Then we will assign this variable var's address to ptr1 and ptr1's address to ptr2. Now we will write a print statement to print variable var, ptr1 and ptr2. Now let's try and execute this program. As you can see, ptr1 and ptr2 shows variable var's value as ptr2 is pointing to ptr1 and ptr1 is pointing to that variable. So indirectly ptr2 points to the variable var. Thus it prints the variable's value. Let's get back to our slides. Let's discuss the array of pointers. As the name suggests, it is an array that has all its elements as pointers. These pointers can be pointing at another array. It is declared as an array with asterisk symbol. Let's discuss it with the program. First, we will declare an array A of size 3. Then we will declare a pointer array ptr of size 3. Now we will write a for loop to assign A's element's address to ptr's element. Then we will write another for loop to traverse ptr and print its element. Let's try and execute this program. As you can see, it prints the value of array A's elements because array ptr's elements are pointing to array A's elements. Let's get back to our slides. Next, call by value. We don't use pointers in this concept, but it is very important to understand this concept to get better understanding of the next topic, call by reference. In call by value, we call a function and directly pass the variable's value as parameters. In this situation, a copy of those variable is created and get passed into a function as parameters. If we modify these parameters, it will not affect actual variables. Rather, these copies will get deleted as soon as the function body ends. Let's try implementing it in the code editor. Let's write a code. First, we will declare a variable x equals to 100. Then we will write a function call to function func with argument x. Next, we will write a print statement to check if any changes happened due to the function. Now, let's write definition for this function. We will take a void function with argument as x. In this, first we will set x equals to 200. And then we will write a print statement to print this value. Let's try and execute this program. As you can see here, when we get back to the main block from function, its value again reverted back to 10. Because in call by value program, we only pass variables copy into the function, not the actual variables. Let's get back to our slides. Next, call by reference. In this, if we call a function, but this time we pass the variable's address as parameters, then in this situation, actual variables will get passed into the function as parameters. If we modify these parameters, it will modify the actual variables even outside the function scope. Let's try implementing it in the code editor. First, we will declare a variable int x equals to 100. Next, we will write a function call for function func with argument as address of x. Then we will write a print statement to check if any changes happen due to the function. Now let's write definition for this function. It will be a void function with argument as pointer x. In this, we will first set x equals to 200. Then we will write a print statement to print this value of x. Now let's try and execute this program. As you can see, this time variable access value didn't revert to 100. That's because in call by reference we pass actual variable's address to functions, so it will modify them as well. Let's get back to our slides. During the course of this video, we have learned a lot about pointers. Let's discuss some advantages of the pointers. First up, pointers are useful to access a memory location. Pointers are also an effective way to access the array elements. Pointers are used for the dynamic memory allocation and its distribution. Pointers are also used to build complex data structures like linked list, graph, tree, stack, queue, etc. Now, let's talk about some disadvantages as well. First up, pointers are difficult to understand, so a programmer needs to be careful while handling them. They might raise some errors like segmentation error or access some unrequired memory and cause program failure. If a pointer is pointing to an incorrect value, then it might corrupt memory. Pointers may also cause memory leakage. Also, pointers are slower than variables. At last, let's sum up what we have learned in this session with key takeaways. First up, a pointer is simply a storage location for a data in a memory. We can use pointers to traverse array more efficiently. We can also use function pointers to call a function dynamically. We can perform arithmetic operations on pointers as well. When we define an array of pointers, its elements can also point to function, making it easier to call different functions at once. Hope you guys found it informative and helpful.
Hey everyone, welcome to Simplilearn's YouTube channel. In this session, we will learn about arrays in data structure. But before we begin, make sure that you have subscribed to our YouTube channel and don't forget to hit that bell icon to never miss an update from Simplilearn. Now, let's get started with the agenda for today's discussion. So at first, we will learn why exactly we need arrays. Followed by that, we will understand what is an array, then the types of arrays. Next, we have the declaration of arrays. Followed by that, we will learn how to initialize an array, then access the elements in an array. After that, we will understand the basic operations that can be performed on arrays. And to wind up the session, we have the advantages and disadvantages of arrays. At the end, we'll have some key takeaways. I hope I made myself clear with the agenda. Now, let's begin with the first topic. That is, why did we actually need an array? So, to understand this, let's go through a simple concept. Let us imagine that we have some data and the data is related to students, right? So, if we wanted to store the marks of individual students, then we had to declare a variable for each of the student. So, you can see we have student 1, student 2, student 3, 4 and 5 and their individual scores. So the score 1 is assigned to student 1 and so on, with student 5 being assigned to score 5. So in the real time, this might be a little clumsy. We have here just 5 students, so that is okay. But what if we had 500 students or 5,000 students? Right, that might be an issue. There we have to create some 500 or 5,000 variables and it would be a little tough to handle that, right? Even if we wanted to apply some operations collectively on all the variables, that might be a little tedious. So what if we had one variable which could store all the 5 students or 500 students or 5,000 students all together and make it really easy for us to apply some operations collectively on all the students? Right? This sounds a little bit logical. So similarly, we do have a data structure which can do that, which can collectively store all the data elements in it as a single variable. And it will also help us to apply the operations which are logical or mathematical on all the variables and their values together as a whole. So that is the purpose why we had created arrays. That is the purpose why we needed arrays. So far we have understood what was the necessity for arrays. Now we will understand what exactly are arrays. So basically an array is a linear data structure that stores the elements in a sequential manner, one after the other. And when you declare an array, the variables will be stored one besides the other, that is adjacent to each other in a sequential order. Now let us understand how the array is represented by the compiler. Now the next part, that is the memory representation of arrays. Now let us imagine that we have declared an array which stores character type data. And another important point to remember about arrays, when you declare an array, it stores only a single data typed elements only. For example, here we have declared a character type array, right? So we cannot store integer type data or float type data in it. We only have to save character type array or character type elements in this particular array. So now let us imagine that we have created an array which is of character data type, and these are the elements which are A, R, R, A, Y. Now how does the compiler represent it in the form of memory? So when you create an array, these are formed, that is the index values and the address. So basically compiler will select a block of memory and it has addresses to that block, and it can be anything. Right here we have 11, 12, 13, 14 and 15, and in real time it might be 1001, 1002, 1003, 1004, 1005. The main motto is assign a sequential block of memory, and this is the array and the elements are A, R, R, A, Y, and this particular one, which is the last one, is the index of the array, that is the position of the array for user. So using this index you can access the elements in the array. More on that in the accessing part. So let us imagine that we wanted to access the element R. So how to access it? We might not know the address, right? In that instance, we will use the index. This is for R reference. So we will tell, I want the element from array index number 2. And then we'll have the ARR, R element. So in the practical form, this is how we use the index. Now let's continue with the lower bound and the upper bound. So the first initial location is called as the lower bound, and at the last or the max value of the array is called as the upper bound. Now let us jump into the next topic where we will understand the different types of arrays. So these are the different types of arrays: one-dimensional arrays and multi-dimensional arrays. In multi-dimensional arrays, we have two more types, that is two-dimensional arrays and three-dimensional arrays. So how are arrays different from each other, right? So the first one, we'll deal with the first one, that is the one-dimensional array. Now, how is an array declared as one-dimensional? For that, we need subscript. So one-dimensional array requires only one subscript to specify the number of elements in an array. So how is it actually represented? So here you can see an example right on my screen. So here is how a one-dimensional array looks like. So here we have the data type, that is integer data type, and marks is the name of the array, and this is the size of the array. And here the elements will be stored, and here it is the index value of the array. And remember, the index value of array always starts from 0. In the previous example, that was only for basic understanding, so I just started that with 1. In the practical way, the array index always starts from 0. So followed by the one-dimensional array, we will deal with the multi-dimensional arrays. In that, we have the following. The first one is the two-dimensional array, and the second one is the three-dimensional array. In the multi-dimensional arrays, we require more than one subscript. In the previous example, we had one-dimensional array, so the subscript is just 1, that is 10 columns, right? So we just had one single row and 10 different columns. But in the multi-dimensional arrays, we need multiple rows and multiple columns, right? So we need 2 subscripts for two-dimensional array and more than 2 subscripts for three-dimensional arrays. So first we have the two-dimensional arrays. The 2D array is organized in the form of a matrix which can be represented as a collection of rows and columns. So here is the example. As you can see on my screen, we have 3 columns and 3 rows. And we have 2 subscripts that define the number of rows and the number of columns and the elements in each and every row. So the 1, 2, 3 confines the first row, 4, 5, 6 confines the second row, and 7, 8, 9 will be the third row. Now similarly, we have three-dimensional arrays. A 3D array is a collection of 2D arrays which consists of three subscripts: block size, row size, and column size. So here we have an example for that. So we have three subscripts. That is, the first one is block size, the second one is the row number, and the third one is column number. So this happens to be the first block, this happens to be the second block. And this is how a three-dimensional array can be represented. Now we have the next stage where we will understand how to declare the arrays. And the syntax is right on my screen. You need to specify the data type of the array, which is integer, float, or character, any selection which you make. Followed by that, you need to select an array name for your array, and inside that, you need to declare the array size. And sometimes you can also eliminate the array size if you wanted to, have a dynamic array. And here is an example for that. You have integer data type, name of the array is example, and the array size is 6. So the compiler will allocate continuous memory block of 6 integer type blocks. So these are the few more methods to initialize the array. So here you can see integer data type, array name is A, element size is 5, and we have 5 elements. The method 2 is, remember I've said you can eliminate the size of the array, right? So here you can use this way as well, integer data type, array name A, and no size here, and you can directly declare the elements. And the method 3. So here you have the name of the array, size of the array, and you are allocating the elements to the individual memory locations. This is also another method to initialize array. And method 4 is using a for loop. You can just initialize a for loop and the I value will be stored in the array locations starting from 0. Now let us understand how to access the elements in an array. So to access the elements in an array, you need to specify the name of the array and memory block where you have that element that you want to access. So here we have an example, which is integer data type, name of the array is xyz, and the element we wanted to access is 5. So here we have an example that is integer type array name is xyz, and it has the size 5. And now we wanted to access the first element in an array. That can be done using the first index, that is xyz of 0 index, that is the first element, and accessing the second element, and so on. xyz of 1 will be the second element, xyz of 2, 3, 4 will be the third and fourth and fifth elements. Now let us understand some basic operations that can be performed on the array elements. So the following are the operations that can be performed on the array elements, that is the traversal, insertion, deletion, searching, and sorting. Now let us get into practical mode and try to execute some examples based on traversal of the array, insertion of an element into the array, deletion of an element from an array, searching for an element in an array, and sorting the complete array. So at first we'll carry out the traversal operation. So here we have an array that is A of 5 and the elements are 1, 2, 3, 4 and 5. Now we're going to use a for loop to traverse through this array and print all the elements sequentially. Now let us execute this code and see the output. So as you can see, the code got successfully executed and the elements, that is 1, 2, 3, 4 and 5 from the array A are printed sequentially. Now moving ahead, we'll try to execute some examples based on insertion of element into the array. So on my screen you can see an example for inserting an element into the array at the starting position of the array. Now let us try to execute this code and see the output. Don't worry about the codes. These code documents will be attached in the description box below and you will be able to have an access to it and run these codes in your personal laptop and get a better learning experience. Now you can see the code got successfully executed and now it is asking for the size of the array. Let's declare it as 5 and now let's enter the elements into the array. Now it is asking for the element to be added at the beginning of the array. Now we have 2, 3, 4, 5 and 6 existing in the array. Let's add the first element, 1, and there you go. The resultant array is 1, 2, 3, 4, 5 and 6. The element which we added at the ending, which is 1, is supposed to be in the first or the beginning part of the array, which is here at the first index location as planned. Now let's get started with another example on the insertion. Now let's try to insert an element at any given location as per the user's choice. So as you can see, we have a program on my screen, and running this program must help us to insert an element into any given location of the array. Now let's try to quickly run this program and see the output. So there you go. Enter the elements into the array. Let's enter 1, 3. Let's try to run this program and see the output. So there you go. The program got successfully executed, and now the output is asking for us to tell it the number of elements in an array. Now let's say 4 elements. So now let's enter the 4 elements. 1, 3, 4, 5 and 6. Okay. So the 4 elements, which is 1, 3, 4, 5 are been inserted. Now it is asking for the location where you want to insert the element. Now let us insert it in this second location. Now let us set the value as 2, and there you go. The resultant array is 1, 2, 3, 4 and 5, and the element, which is 2, was supposed to be added in the second location, and it has been successfully added. Now let's try to execute another example based on insertion, where you will try to insert the element in the last position. Now this program on my screen will help us to add an element at the end of the array. Let's quickly run this program. Now it is asking for us to enter the 5 elements of the array. Let's enter that. Now it is asking to enter the element to be inserted. Now let us enter the element, and this element should be added at the end location as discussed. The resultant array is 1, 3, 5, 7, 9 and 11. Now let's continue with the deletion operation. Now the program on my screen is an example for deleting an element from the beginning position of an array. Now the program got successfully executed, and it's asking for us to enter the size of the array. Let's enter the size as 5. And now let's enter the elements of the array, that is 1, 2, 3, 4 and 5. Now the element from the first location, that is 1, has been deleted, and the resultant array is 2, 3, 4 and 5. Now the code on my screen will help you to eliminate the element from the ending location of an array. Now let's try to quickly run this program and see the output. So you can see that the program is successfully run, and it is asking for us to enter the size of the array. Let's enter 4. Now let's enter the elements of the array, that is 1, 2, 3 and 4. Now after eliminating the last element from the array, that is 4, we have the resultant array, that is 1, 2 and 3. Now a little homework for you guys. Let's try to execute an example for deleting an element from any location of an array. This will be a homework. Now don't worry, try on your own, and if you don't get that, you can refer to the comment sections below, where you have the code document attached in the description box, and you can refer to it. Now let's continue with the next operation, where we will search for a given element in the array. So you can see that on my screen we have an example which will help us to sort the elements in an array. Let's quickly run this. So there you go, the program got successfully executed, and now it's asking for the array size. Let's enter 5, and now let's enter the elements in a random order. Now the resultant array should be sorted. So there you go. The array after being sort is 2, 3, 5, 14 and 21. So there you go, the array got sorted. So now we have finished our practical session. Let's have a quick overview again. So traversal in an array is a process of visiting each element once Traversal can be done by various means, that is by counting the array elements, printing the values sorted in the arrays, and sum of all elements present in the array, and many more. So this is how we traverse our array from the first location to the last location. Again, the insertion operation. Insertion in an array is the process of including one or more elements in an array, and it can be done at the beginning, at the end, and at any given index of an array, which we executed for all the three types of examples. Now next we have the deletion operation. So deletion operation or deletion of an element is a process of removing a desired element and reorganizing the array, and it can be done at the beginning, at the end, and at any given index. So we have executed the example for at the beginning and at the end, and the homework was at the given index. Don't worry if you don't figure it out, you can always refer to the example document which is mentioned in the description box below. Now the search operation. Searching is a process of finding a given value in the list of values, and it decides whether the search key is present in the array or not, and we have executed an example on that. And again, the sort operation, where we will sort the given array. If the given array is not in the default order or in a given order, that is ascending or descending, then we can sort the order of the array by the user's choice, given it is ascending order or descending order. Now in the next section of the tutorial, we will discuss the advantages of using arrays. So the first one is array stores multiple elements of same data type with same name. Next one, elements in an array can be accessed randomly using just the index number. Array memory is predefined, so there is no extra memory loss. Array avoids memory overflow. And finally, 2D arrays can represent the tabular form of data in a very efficient way. Now let us also have a look on some of the disadvantages of using arrays. The first one, the number of elements in an array should be always predefined. So there is no chance that you can add some extra element in the last moment. Array is static in nature, so its size cannot be varied after declaration. What if, consider that you wanted to store 10 student data in one array and you end up having just 7 students. So the remaining 3 is a waste, right? So you're wasting memory there. That's the problem. And insertion and deletion operations in an array is quite difficult as the array stores elements in a continuous form. And finally, allocating excess memory than required may lead to memory wastage. Now we have the final key takeaways of the arrays. So we discussed why do we need arrays, then we discussed what are arrays, followed by that we discussed types of arrays, next we had a declaration of arrays, accessing elements from an array, initializing the arrays, and basic operations on array, that is the practical demo part, and finally we have discussed the advantages and disadvantages of using an array. Now with that we have come to an end of this tutorial. Hello everyone, welcome to Simplilearn's YouTube channel. Today in this session, we will learn about two-dimensional arrays. But before we begin, make sure that you have subscribed to our YouTube channel and don't forget to hit that bell icon to never miss an update from Simplilearn. So without further ado, let's get started with the agenda for today's session. We will begin with learning what are two-dimensional arrays. We will then understand the need for two-dimensional arrays. Followed by that, we will learn the syntax of two-dimensional arrays. Advancing ahead, we will visualize two-dimensional arrays, and finally we will enter into our hands-on part where we will practically see how to initialize a two-dimensional array and also learn how to access elements in it, and next we will try to print the elements in a two-dimensional array. I hope I made myself clear with the agenda, so let's get started with our first topic, that is what are arrays. So we will see a brief definition of arrays. The array is a data structure that stores elements of the same data type in a sequential order. Two-dimensional arrays are considered as an array of arrays. Two-dimensional arrays represent the information in the form of rows and columns, which is completely similar to a tabular form of data. Following by the definition and briefing of the two-dimensional arrays, we will understand the need for two-dimensional arrays. So the main advantage of using a two-dimensional array is the elements can be represented in the form of a matrix, that is rows and columns. Using two-dimensional arrays, we can initialize, access and print multiple elements in the matrix form by just running one single code segment. You can see an example right on my screen here. This is an example of marks list. Suppose a class has 3 subjects, namely English, Science and Maths. We have 4 students and we wanted to represent the data in the form of a database. So here, the marks of the 4 students can be represented using 2-dimensional arrays. Now, we will see the syntax of a 2-dimensional array. So here, the syntax. At first, we need the data type. The data type can be integer, character, float, string, etc. Then we have the name for the 2-dimensional array. And later, we can have 2 subscripts which represent 2 dimensions, that is, the rows and columns. The first subscript defines the number of rows and the second subscript defines the number of columns. And note that the column number can never be null. At the end, we have a semicolon to terminate the syntax. And here we have some examples of 2-dimensional arrays. So in the first example, we have the name of the 2-dimensional array and we have 3 rows and 4 columns. And followed by that, we have another example which is of character data type and the name of the array is names and we have 7 rows and 15 columns. Next, we will see how to visualize 2-dimensional arrays. We read earlier that 2-dimensional arrays are a collection of rows and columns. Let's see an example of 2-dimensional array. We will consider an array with 6 rows and 4 columns. As you can see on my screen, we have integer type array and the name of the array is array and we have 6 rows and 4 columns. The product of rows and columns will give us the total number of elements present in a 2-dimensional array. In the current example, we have 6 rows and 4 columns and the product is 24. So we must have 24 elements in this array. Next, we will see how to initialize 2-dimensional arrays. So there are 2 ways to initialize a 2-dimensional array. So in the first method, we declare the elements in the set of curly brackets. This array consists of 3 rows and 3 columns. Note that the index always starts from 0. Here we have 3 rows. It means the row starts with 0 and ends with 2. The same goes for the column. But sometimes this method might be a little confusing. So we have a better method. The advantage of this method is clarity. We can visualize all the elements with better clarity compared to the previous method. So the first 3 elements are 9, 6 and 1. They are present in the first row. And in the second row, we have 144, 70 and 50. They comprise the second row. And finally, the third row in which the elements are 10, 12 and 78. So far, we have learned how to visualize and initialize a 2-dimensional array. So we have done it by using the index values, that is the row index and the column index. So the row index value was 3 and the column index value was 3. For accessing an element in the 2-dimensional array, we need to pass the name of the 2-dimensional array followed by the row index value and the column index value. For example, let us assume that we wanted to access the element 9. For doing so, we will pass the name of the array followed by the row index value and the column index value as shown below. That is int first 0, 0. And an important point here is indexing always starts with 0. We will now start printing the 2-dimensional arrays. So to print a 2-dimensional array, we will be using 2 nested for loops. So to understand the process of printing the 2-dimensional array, let's get back to the practical mode and we will work on a code. So on my screen, you can see an example for 2-dimensional array. So here we have declared an array with the name first and we have 3 rows and 3 columns. And inside that, the first row of elements is 9, 6, 1 and the second row of elements is 144, 70 and 50 and the third row of elements is 10, 12 and 78. Followed by that, we have 2 counter variables which are I and j. So we are using the first counter variable I in the outer for loop and the second counter variable j in the second inner for loop. And inside the inner for loop, we have a print statement which is used to print the elements in the array. Now, let us try to execute this code and see the output. So you can see the code got successfully compiled and we have our elements here, which is 961, 144, 70, 50, 10, 12, and 78. Now let us understand the logic. So here we have declared the counter variable as 0 and the condition is I should be less than 3, which is true. So the control will enter into the second inner for loop. Here we have j is equals to 0 and j should be less than 3, which is true. So here the condition or the statement is valid and it will print the first element 9. Followed by that, j will be incremented again. J is now equals to 1 and j is less than 3. So again we'll print the second element 6. Again j value will be incremented to 2, so 2 is less than 3. Then we will print the third element, that is 1. Now when you increment the value of j from 2 to 3, the condition will fail because 3 cannot be less than 3. So the control will enter into the outer for loop. Here we have I value is equals to 0, which will be incremented to 1. So 1 is less than 3. Again, the control will enter the inner for loop. Here again, we will check for j is equals to 0, which is true. So we will print the second row of elements, that is 144, 70, 50, in the same way how we printed the first row. Right, so j will be equals to 0, so then we'll print the first element. So j will be incremented to 1 and 1 is less than 3, then we will print the second element, that is 70. And again j will be incremented to 2 and 2 is less than 3, so we will print the third element, that is 50 in the second row. And again j will be incremented to 3 now. The compilation of the condition will result in false, so it will exit the second for loop and it will come back to the first outer for loop. Now the value of I will be incremented to 2, so 2 is less than 3. The control will enter into the inner for loop again. Then we will print the third row of elements, that is 10, 12, and 78 in the same way how we printed the first row and the second row. After printing the third row, the condition will fail when j value is incremented to 3 and it will enter the outer for loop. Here the I value will be incremented again from 2 to 3 and the condition fails. Now the overall control will come out of both the for loops and it will terminate here. So that's how we got 9, 6, 144, 70, 50, 10, 12, and 78. So with that we have come to the conclusion, and so far we have learned the following things. What are two-dimensional arrays? Why we need two-dimensional arrays, syntax of 2D arrays, visualizing 2D arrays, initializing 2D arrays, accessing 2D elements, and finally print the elements of two-dimensional arrays. So with that, we have come to an end of this tutorial.
Hey everyone, I'm Krushkal and I welcome you all to Simplilearn's YouTube channel. In this session, we will learn everything about linked list. We shall begin our session by learning what the linked list is and why do we need them. Then we will try to implement it in the code editor. Then we will discuss different types of linked list. Then we will learn various operations that we can perform on linked list. Post that, we will discuss some advantages and disadvantages of the linked list. Finally, we will take a glance at what are the final key takeaways from this session. But before we begin, make sure you have subscribed to our YouTube channel and clicked on the bell icon so you never miss an update from Simplilearn's YouTube channel. So without any further ado, let's get started with what is linked list. A linked list is a linear data structure made up of nodes. These nodes consist of two parts, data and reference to another pointer. Typically, a linked list starts with a head node, which goes all the way up to the last node, which is called tail. Next, let's discuss why do we need linked list. A linked list is a linear data structure like arrays, but an array can only offer a fixed size, whereas a linked list can dynamically increase its size. Also, operations like insertion and deletion are much easier in a linked list than in an array. Now, let's try to implement the linked list in the code editor. Let's start by creating a node. To create a node, we need a class. Let's declare a class node. We will declare its member as public. The first member is int data and the second member is node pointer next. Now we will go into the main block and initialize our first node. To initialize a node, we need to use node star. The node name head equals to null. Similarly, we will create more nodes. And our last node tail. Now we will allocate these 4 nodes in the heap. To do that, we will use a node name equals to new node star, new node braces. Now we will allocate all the nodes in the same manner. Now we will assign data to our first node. To access the member of the node class, we will use arrow formation. Then we will use data equals to, let's give it a value as 2. Now we will link this first node with our second node. To do that, we will use head, same arrow formation and next, which will be equals to our n1 node. And now we have created our first complete node. Now let's create other nodes as well. N1 arrow data is equals to, let's give it 3. N1 arrow next is equals to N2. N2 arrow data is equals to 5. N2 arrow next, 2 arrow next is equals to tail. Now tail is equals, tail arrow data equals to 7 and tail arrow next is given null. Now let's call a function to print this list. We will give head as the argument, as we can only traverse a linked list from its head. Let's write a definition for this print list function. This function will be a void function. Argument is node star a. We will use while loop to traverse this linked list. We will give it condition if a is not equals to null, then cout is a data and L. Now we will change our cursor from the current node to the next node. To do that, we will use a is equals to a arrow next. Now let's try to execute this code. As you can see, we have traversed our complete linked list. Now let's get back to our slides. Now let's discuss different types of linked list. The first are singly linked list. Next is the doubly linked list, the circular linked list, and finally we have the circular doubly linked list. Let's discuss each one of these in details. First up, singly linked list. It is a unidirectional linked list. While using the singly linked list, we can only traverse it in one direction, that is from head node to the tail node. Next up, doubly linked list. It is a bidirectional linked list. We can traverse it in both the directions. In this linked list, the node has an additional pointer that points to the previous node. Next up, circular linked list. It is a regular linked list except for its last node points to the head node. Programmer needs to be careful while traversing it, or they might get stuck in an infinite loop. Next up, the circular doubly linked list. It is a combination of doubly linked list and a circular linked list. Its last node points at the head node and the previous pointer of the head node points to the last node. It is also bidirectional linked list so that we can traverse it in both directions. We have now discussed the linked list, why do we need linked lists, and types of linked list. Now let's learn about some operations we can apply on linked list. We can use majorly two operations on linked list. First up, insertion and deletion. We can perform these operations in three different situations. First, at the beginning, at the last, or at a specific position after a node. Next, we will discuss these operations in detail. First up, insertion. We will discuss first insertion at the beginning. We have to give the first node's address to the new node's next pointer to execute this. Next up, insertion at the end. We have to give the new node's address to the last node's reference pointer. Next up, insertion at a specific position. To do this, we will have to change the reference address of the previous node to the new node's address and the new node's reference pointer to the next node's address. Now let's discuss deletion. First up, deletion at the beginning. We have to change the first node's address to the null to execute this. Next up, deletion at the end. We have to change the second last node's address to the null. Next up, deletion at a specific position. We will change the reference address of the previous node to the next node's address. We have learned a lot about linked list during this session. Now let's discuss some benefits of linked list. First up, a linked list is a dynamic data structure. That is, we can dynamically increase its size. Next, it offers easy insertion and deletion than other linear data structures like arrays and string. Since it can dynamically increase its size, resulting in no memory wastage. Next, it is pretty handy in implementing complex data structures like stacks and queues, etc. Now, let's talk about some disadvantages as well. First up, since the linked list is made up of nodes, it takes extra storage for storing data and reference pointer. Next, the traversal in the linked list is a bit harder than other data structure. Reverse traversing is easy in doubly and circular doubly linked list, but since it uses one extra pointer, it takes extra storage, making it another limitation. At last, let's sum up what we have learned in this session with key takeaways. First up, we have recognized linked list as a dynamic data structure. Next, a linked list offers faster insertion and deletion operation. Next, linked list traversal is hard because we have to start from the head node every time. Finally, a linked list is an asset in implementing other data structures like stacks and queues. And this was all for today's session. Hey everyone, I'm Vaibhav Khandelwal and I welcome you all to Simplilearn's YouTube channel. In this session, we will talk about single linked list. We shall begin our session by introducing a single linked list. Then, we will try to implement it in the code editor. After that, we will try various operations on them like insertion and deletion. Finally, we will sum up what we have learned from this session. But before we begin, make sure you have subscribed to our YouTube channel and clicked on the bell icon below, so you never miss an update from Simplilearn. So without any further ado, let's get started with introduction to single linked list. A single linked list is a linear data structure made up of nodes. These nodes consist of two parts, data and reference to another pointer. These nodes can be traversed using pointers. It starts from the head node all the way up to tail node. Now let's try to implement the single linked list in the code editor. Start by creating a node. To create a node, we need a class. Let's declare a class node. We will declare its member as public. The first member is int data and the second member is node pointer next. Now we will go into the main block and initialize our first node. To initialize a node, we need to use node star. The node name head equals to null. Similarly, we will create more nodes. And our last node tail. Now we will allocate these four nodes in the heap. To do that, we will use a node name equals to new node star, new node braces. Now we will allocate all the nodes in the same manner. Now we will assign data to our first node. To access the member of the node class, we will use arrow formation. Then we will use data equals to, let's give it a value as 2. Now we will link this first node with our second node. To do that, we will use head, same arrow formation, and next, which will be equals to our n1 node. And now we have created our first complete node. Now let's create other nodes as well. N1 arrow data is equals to, let's give it 3. N1 arrow next is equals to N2. N2 arrow data is equals to 5. N2 arrow next, 2 arrow next is equals to tail. Now tail is equals, tail arrow data equals to 7, and tail arrow next is given null. Now let's call a function to print this list. We will give head as the argument, as we can only traverse a linked list from its head. Let's write a definition for this print list function. This function will be a void function. Argument is node star a. We will use while loop to traverse this linked list. We will give it condition if a is not equals to null, then cout is a data and L. Now we will change our cursor from the current node to the next node. To do that, we will use a is equals to a arrow next. Now let's try to execute this code. You can see we have traversed our complete linked list. Now let's get back to our slides. We have now introduced the single linked list. Now let's discuss some of the operations we can apply on a linked list. First up, insertion. We can perform insertion at three different situations, like at the beginning, at the last, or at a specific position after a node. Next up, deletion. Similar to the insertion, we can perform it in three different situations as well. At the beginning, at the last, or at a specific position after a node. Let's talk about them in detail. First up, insertion at the beginning. To execute this, we have to give first node's address to the new node's next pointer. Next up, insertion at the end. To execute this, we have to give new node's address to the last node's next address. Next up, insertion at a specific position. To execute this, we will change the previous node's reference address to the new node's address and the new node's reference pointer to the next node's address. Now, let's try these operations in a code editor. As you know, a linked list is made up of nodes, so we should start by creating a node. To create a node, we need a class node and we will define its members as public int data and node pointer next. Now we will create a function to insert a new node in front of the list. For this function, as an argument, we will give the reference to the head of the list and integer new data. Now in the definition, we will allocate a node new node equals to now we will put in the data in the new node. We will use arrows to access the data equals to new. Now we will make the next of this new node as head. Now we will move the head to point to the new node. Now we will create another function to insert a node after a specific position. As arguments, we will give it the address to the previous node and the integer new data. We will first check if the given previous node is null. If it is, we will print given node cannot and then we will return the function. Otherwise, we will allocate a new node and then we will enter the new data in that. Now we will make the next of the new node as a next of the previous node. And then we will move the next of the previous nodes as new node. Now we will write a function to insert a node at the end of the list. As an argument, we will give it a node pointer to pointer head and integer new data. We will first allocate a new node we will also create a last node and give it now we will put in the data in the new node since this new node is going to be the last node, so we will make its next as null. Now, if the linked list is empty, then we will make the new node as head. To check that, we will use if star head is equals to null. If it is, then we will do star head equals to new node. Else, we will traverse it to the last node. While last, next, not null, last is equals to last, next. Now we will change the next of the last node as new node. Return. Now we will write a function to print this list. While node is not null, cout node arrow data handle and node equals to node. Now we will write the code for the main block. First we will define a head node. And mark it as null. Now we will start using those functions to make a linked list. First we will use append function to add 6 in it. Next, let's use another function push and add 7 in it. Now we will try to insert 1 at the beginning. So we will use push again. Comma 1. Now let's try to insert 4 at the end. So far the list looks like 1, 7, 6, 4 null. Now let's try to insert 8 after 7. To do that we will use insert after. As argument we will use head next as 7 is present next to the head, comma 8. Now let's try to print this linked list. cout created linked list linked list add return 0. Let's execute this. As you can see, we have created the linked list in the correct order. Let's get back to our slides. Now, let's talk about deletion. First up, deletion at the beginning. To execute this, we have to change first node's next address to null. Next up, deletion at the end. To execute this, we have to change the second last node's address to the null. Next up, deletion at the specific position. We will change the previous node's reference address to the next node's address. Now, let's try these operations in a code editor. We will start by creating a class node. In this class, we will declare the members as public int data and the node pointer next. Now, to insert the data in the node, we will use a function push as argument. We will give pointer to pointer node head and integer new data. We will allocate a new node we will give this new node the data as new data and new nodes next as head. Now we will write a function to delete the node. As argument, we will give a node pointer to pointer head and int key. Now we will store head in a temp node. and we will create a node prev as null. If head node itself holds the key to be deleted, we will use if temp is not equals to null and temp data is equals to key. Then head equals to temp next. Now we will free the old node. Else we will search for the key to be deleted. Else while temp is not equals to null and temp data is not key, so prev equals to temp and temp will be iterated to its next. If the key is not present in the linked list, then we will just return the function else we will unlink the node from the linked list. And delete. Now we will write a print list function to print the list. Its argument will be a node pointer node while a node is not null. Cout less than node data then we will iterate this node using node equals to node next. Now we will move on to the main block. We will start with the empty list node star head equals to null. Now we will add the element to this list. So push ampersand head comma 7. Next, push ampersand head comma 2 push ampersand head comma 5. Next, push ampersand head comma 9. Now see out created list print list head now we will use delete node function. Delete 2. We will use argument as ampersand head comma 2. Now we will check the linked list. Of 2. Print list let's try and execute this. As we can see, we have deleted the 2 from the linked list. Let's get back to our slides. At last, let's sum up what we have learned in this session. First up, we have recognized singly linked list as dynamic data structure. Next up, the singly linked list offer faster insertion and deletion operation. Next, singly linked lists are unidirectional linked lists. That is, you can only traverse it in one direction. Finally, a single linked list is an asset in implementing other data structures like stacks and queues. And this was all for today's session. Hey everyone, I'm Vaibhav Khandelwal and I welcome you all to Simplilearn's YouTube channel. In this session, we will talk about Doubly linked list. We shall begin our session by introducing Doubly linked list. Then we will try to implement it in the code editor. After that, we will try various operations on them like insertion and deletion. Finally, we will sum up what we have learned from this session. But before we begin, make sure you have subscribed to our YouTube channel and clicked on the bell icon so you never miss an update from Simplilearn. So without any further ado, let's get started with an introduction to Doubly linked list. A doubly linked list is a linear data structure made up of nodes. This linked list is a bidirectional linked list, that is, we can traverse it in both directions. These nodes consist of 3 parts. First up, data, reference to the next node, and reference to the previous node. Now let's try to implement the doubly linked list in the code editor. As you know, a linked list is made up of nodes. So we will start by creating a node. To create a node, we need a class node. Its members should be defined as public. Int data, node pointer, next, and node pointer ref. Now we will write a function to insert a node at the beginning of the doubly linked list. Void push. Argument will be a node pointer to pointer, add, and int new data. Now let's allocate a node star new node equals new node. Now let's put in the data into the new node. Since we are adding at the beginning, its previous is always null. Now we will link the old list of the new node. Now we will change the previous of the head node to the new node. We will check if head is not null. Then head's previous is equals to new node. Now let's move the head to the point to the new node. Now let's write a function to print the given doubly linked list. Its argument will be a node we will iterate it until the node is not null. Out node data and node equals to node next. Now let's write a code for the main block. We will start with the empty list. Now we will use a push function to push values in the function. Another push function add comma 3, push function ampersand head comma 5, push function head comma 7. Now out doubly linked list then we will call the print list function print the doubly linked list. Let's execute this program. As you can see, we have successfully created our first doubly linked list. Let's get back to our slides. We have now introduced doubly linked list. Now let's discuss some of the operations we can perform on a doubly linked list. We can perform 3 operations on a doubly linked list. First, traversal, insertion, and deletion. We can perform a traversal in 2 ways, a normal traversal and reverse traversal. And we can perform insertion and deletion in 3 different situations: at the beginning, at the last, and at a specific position after a node. Let's discuss these in detail. First up, normal traversal. We can traverse a doubly linked list using a next pointer starting from head to all the way up to tail node. Reverse traversal. Similar to the normal traversal, we will use previous pointer. We will start from the tail node to go all the way up to head node. Now let's try to traverse the doubly linked list in the code editor. Let's start by creating a class node. We will define its members as public, int data, node pointer, next, and node pointer ref. Now we will write a function to insert a node at the beginning of the doubly linked list. Void push. Its argument will be a node pointer to pointer head and integer new data. Now we will allocate a node star new node new node parenthesis. Now we will put in the data since we are adding at the beginning, so its prev is always null. Now we will link the old node to the new node. Now we will change the previous of the head node to the new node. Now we will move the head to the point to the new node. Now we will write a function to traverse the linked list normally. Void traverse node pointer while loop node is not null, therefore cout node data node equals to node next. Now we will write a function to reverse traverse it. Its argument will be a node pointer to pointer head we will create a node tail equals to head while tails next is not null. This loop is enabling us to reach to the tail node so that we can traverse it from backside. Now, while loop until tail is not equals to head, cout, tail, data, tail equals to tail trev. Cout, tail, data, handle. This last cout statement is only because we are not traversing till the head pointer. Now let's go to the main block. Let's start with an empty list. Node star head equals to null. Now let us create a linked list to test the function. So we will use push function head comma 2, another push function ampersand head comma 3, push head comma 7. Since we are inserting at the beginning, so the actual linked list looks like 7, 5, 3, null. Now we will print the original linked list first. Cout original traverse head cout reverse traversal reverse traversed linked list Now let's try and execute this program. As you can see, we have traversed it in the normal way as well as the reversed way. Let's get back to our slides. Next up, insertion at the beginning. We will create a node with the previous pointer pointing to a null and the next pointer pointing to the head node. Then we will change the head node's previous pointer to the new node, and we will change the new node to the head node. Next up, insertion at the end. We have to give the new node's address to the last node's next pointer and change the new node's previous pointer to the last node. Next up, insertion at a specific position. We will change the previous node's next pointer to the new node and the new node's previous pointer to the previous node and the next pointer to the next node and vice versa. Now let's try these operations in a code editor. We will start by creating a class node public node pointer ref node pointer. Now we will write a function push, insert a node at the beginning of the list. Its argument is node pointer to pointer head into new data. We will first allocate a new node star, new node equals new node parenthesis. Now we will put in the data node arrow data is equals to new data. Now we will make the next of the new node as head and previous as null. And new node previous is equals to null. Now we will change the previous of the head node to the new node. First we will check if the head node is null. Then star head previous equals to new node. Now I will move the head to the point to the new node. Now let's write another function to insert a node after a specific position. Void insert after argument will be node pointer rev node int new data. We will first check if the given previous node is null. If yes, then we will give it cout the given node can't be null. And we will return to the function. Or else we will allocate a new node equals to new now we will put in the data now we will make the next of the new node as the next of the previous node equals to ref node now I will make the next of the prev node as new node and make the prev node as the previous of the new node. Now I will change the previous of the new node's next node. If new node next not null, then new node next prev is equals to new node. Now let's write another function. Insert a node at the end of the list. Void append its argument will be a node pointer to pointer head int new data. First we will allocate a new node equals to new parenthesis now we will create another node last equals to head now we will put in the data new node data equals to new data. Now since this new node will be the last node, so its next will be null. Head is equals to null. New node rev equals to null, and star head is equals to new node. Return. Or else we will traverse till the last node, while last, next is not null. Last equals to last, next. Now we will make the last node as the previous of the new node. Return. Now we will write a print list function to print this list. The argument is the node pointer node. While node is not null, out. Node data node is equals to node, next. Now let's write the main block. We will start with an empty list. We will start by inserting 6, so the linked list becomes 6 null, and ampersand head comma 6. Now we will insert 7 at the beginning. push ampersand head, comma 7. Now we will insert 1 at the beginning also. Now we will insert 4 at the end. Till now the linked list looks like 1, 7, 6, 4, null. Now we will insert 8 after 7. So insert after head next, comma 8. Now let's print this linked list. Let's try and execute this. As you can see, we have created our linked list in the correct order. Let's get back to our slide. Next up, deletion. First up, deletion at the beginning. We have to change the first node's next to null and second node's previous to null. Next up, deletion at the end. We have to change the second last node's next pointer to null and delete the previous node to free up the space. Next up, deletion at a specific position. We will change the previous node's next pointer to the next node and next node's previous pointer to the previous node. Now, let's try these operations in a code editor. We will start by creating a class node public int data node pointer next node pointer ref. Now we will write a function to delete a node in a doubly linked list. Void delete node. Its argument as pointer to the head node. Repeat. Its argument as pointer to the head node pointer. And pointer to the node to be deleted. Now we will check the base case condition, that is if head is null or the node to be deleted is null, then return now if the node to be deleted is a head node, then head is equals to del now if next node of the del not null, that is if the node to be deleted is not the last node, then else next previous equals to else previous. Now we will change prev only if node to be deleted is not the first node. So if del prev not equals to null, then del prev next equals to del's next. Finally, we will free the memory occupied by the del. Free del now let's write a function to insert a node at the beginning of the doubly linked list. Void pointer to the head node pointer and int new data. We will allocate the node now we will put in the data Since we are adding at the beginning, so prev is always null. Now we will link the old list of the new node. Now we will change the prev of the head node to the new node. Now we will move the head to the point to the new node. Now let's write printlist function. Node pointer node while node is not equals to null, cout node data node equals to node next. Now let's get started with the main block. We will start with the empty list. Now we will create new nodes. Push %head, comma 2, push ampersand head, comma 4, push ampersand head, comma 6, push ampersand head, comma 8. Now let's print this list. Cout original list original list. Now we will call the printlist function head. Now we will delete the node from the doubly linked list. Here we are deleting the first node. Next, let's delete the last node. Now the modified list should look like 4, 8, let's try and print this. Cout modified list head. Let's try and execute this. As you can see, we have deleted all the nodes except for 6 and 4. Let's get back to our slides. At last, let's sum up what we have learned in this session. First up, we have recognized doubly linked list as dynamic data structures. Next, the doubly linked list offers faster insertion and deletion operation. Next up, doubly linked lists are bidirectional linked list. That is, we can traverse it in both directions. Finally, a doubly linked list is faster at reverse traversal. And this was all for today's session. Hey everyone, I am Vaibhav Khandelwal and I welcome you all to Simplilearn's YouTube channel. In this session, we will talk about circular linked list. We shall begin our session by introducing a circular linked list. Then we will try to implement it in the code editor. After that, we will try various operations on them like insertion and deletion. Finally, we will sum up what we have learned in this session. But before we begin, make sure you have subscribed to our YouTube channel and clicked on the bell icon so you never miss an update from Simplilearn. So without any further ado, let's get started with introduction to circular linked list. A circular linked list is a linear data structure made up of nodes. It is like a singly linked list except its last node points at the head node. These nodes consist of two parts, data and reference to next pointer. These nodes can be traversed using the next pointer. Now let's try to implement it in the code editor. We will start by creating nodes. To create a node, we need a class node. We will define its members as public, int data, and node pointer next. Now let's write a function to insert a node at the beginning. Void push we will use arguments as a pointer to node pointer head and int data. We will define a node, new node equals to new node parenthesis head. Now we will put in the data into the new node. Since we are inserting at the beginning of the linked list, that's why this new node's next should be the head pointer. If linked list is not null, then set the next of the last node as head. While temp next is not equals to head, the temp is equals to temp arrow next. Now temp next is equals to new node. Else new node next is equals to new node. Star head equals to new node. Now let's write a function to print this linked list. Void print list node star head node star temp is equals to head. If head is not equals to null, then do cout temp data temp is equals to temp next. Now while temp is not equals to head, this condition is important to stop this loop so that it doesn't go infinitely. Now let's go to the main block. Let's initialize this list as empty. Node star head equals to null. Now let's insert some nodes in this linked list. Push ampersand head comma 2 push ampersand head push ampersand head comma 11 ampersand head comma 5. Now this linked list looks like 5, 11, 9, 2. Then it will again go back to 5. Now let's try to print this. Cout circular list head. Now let's try and execute this. As you can see, we have successfully created our first circular linked list. Let's get back to our slide. We have now introduced the circular linked list. Now let's discuss some of the operations we can apply on a circular linked list. We can perform two operations on a circular linked list. First up, insertion. We can perform insertion at three different situations: at the beginning, at the last, and at a specific position after a node. Next up, deletion. We can perform deletion at the three different situations. First up, at the beginning, at the last, and at a specific position after a node. Let's discuss these in detail. First up, insertion at the beginning. We have to give the first node's address to the new node's next pointer to execute this. Next up, insertion at the end. We have to give new node's address to the last node's reference pointer. Next up, insertion at a specific position. We will change the previous node's reference address to the new node's address and the new node's reference pointer to the next node's address. Now, let's try these operations in a code editor. So far, we have implemented a linked list using classes. Now, let's try to implement it using structures. We will start by creating a struct node with its element as int data and struct node next. Now we will write a function which can only insert a node to an empty list. Struct node star add empty. Struct node star last comma int new data. Now since this function is only for the empty list, so we will have to check if the linked list is empty or not. If last is not equals to null, then we will return last. Now let's create a node dynamically. Struct node start temp equals to struct node star malloc size of struct node. We will copy this statement because we will need it in the future functions. We will assign the data to this new node. Temp data is equals to new data. Last is equals to temp. Now we will create the link. To do that, we will use last next is equals to last. Since we are in an empty list, so the first node will always point to itself. Return struct node star. We are creating a function to insert at the beginning of the linked list. Struct node star add begin as argument. We will use struct node last comma int data. If last is equals to null, then we will return add empty last comma data. Now we will create a node dynamically. I've already copied this statement for the ease. Now we will put in the data. Data is equals to data temp next is equals to last next last next is equals to return last. Now we will write a function to insert a node at the end. Struct node star add and struct node star last int data. If last equals to null, then return add empty last, comma, data. Now we will dynamically create a node and put in the data. Temp data is equals to data. Temp next is equals to last next. Now last next is equals to temp and last equals to temp. Return. Now we will write a function to insert a node after a specific node. So struct node star add after struct node star last, comma, int data int item. This item is a node after which we have to insert the node. If last equals to null, then return null. Struct node star temp, comma, star p. P is equals to last next. Now do if equals to item temp equals to we will dynamically create a node here. Temp is equals to struct node star malloc size of struct node. Now we will put in the data. So temp data is equals to data temp next is equals to next. Now p next is equals to temp. If p is equals to last, then last is equals to temp. Return last. Equals to p next. While not equals to last next. Cout item not present in the list. Return last. Now we will write a function to print this list. Void print list struct node star last struct node star p. Now if last is equals to null, then cout list is empty and return. Else we will point to the first node of the list. So p is equals to last next. To traverse the list, we will use do while loop. So do cout data is equals to p next. While p is not equals to last next. Now let's write a code for the main block. We will start with an empty list struct node star last equals to null. Now last is equals to add empty last, comma 6. Last equals to add begin last, comma 4. Last equals to add begin last, comma 2. Last equals to add end last, comma 12. Last equals to add after last, comma 10, comma 4. Print list. Let's execute this. As you can see, we have created the linked list in the correct order. Let's get back to our slides.
Now, let's talk about deletion. First up, deletion at the beginning. We have to change the first node's address to the null to execute this. Next up, deletion at the end. We have to change the second last node's address to null to execute this. Next up, deletion at a specific position. We will change the previous node's reference address to the next node's address. Now, let's try these operations in the code editor. Let's get started with creating a node. To create a node, we need a class node. We will declare its members as public, int data, node pointer, next. Now we will write a function to insert a node at the beginning of the list. Void push a pointer to the node pointer head and int new data. Now let's create a node and make head as next of it. Node star new node equals to new node parenthesis. Let's put in the data new node data is equals to new data and new node next is equals to head. If linked list is not null, then set the next of the last node as the first node. If star head is not null, then we will find the node before head and update next to it. So node star temp is equals to star head, while temp next is not equals to head, temp is equals to temp next. Now temp next equals to new node. Else new node next is equals to new node, and star head is equals to new node. Now let's write a function to delete a given node from the list. So void delete node. Its argument is a pointer to the node pointer, head, and int key. Now if linked list is empty, then we will simply return it. If star head is equals to null, then return. Otherwise, if head head data is equals to key and head next is equals to head, then free head head is equals to null, return. Now node last is equals to star head comma star d. Now if head is to be deleted, then star head data is equals to key, then while last next not equals to star head, then last is equals to last next. Now we will point the last node to the second node of the list. Now we will free this head. Star head equals to last next. Now, if either the node to be deleted is not found or the end of the list is not reached, then while the last next is not equals to head and last next data is not equals to key, then last equals to last. If node to be deleted was found, then if last next data is equals to key, then d is equals to last next and last next is equals to d's next. Now we will free d. Or else see out no such key found. Now let's write a function to print this list. Void print list node star head node star temp is equals to head if head not null, then do cout temp data temp is equals to temp next, while temp is not equals to head. Cout Now let's write a code for the main block. We will start by empty list. So node star head equals to null. Now we will push ampersand head 2, push ampersand head 5, push ampersand head 7, push ampersand head 8, and push ampersand head 10. Now we will print the list before any deletion operation. Cout list before deletion print list head now let's delete ampersand head. Let's delete 7. Cout list after deletion print list head. Let's execute this. As you can see, our deletion function is working perfectly. Let's get back to our slides. At last, let's sum up what we have learned in this session. First up, we have recognized circular linked lists as dynamic data structures. Next, the circular linked lists offer faster insertion and deletion operation. Next, a circular linked list are unidirectional in nature. That is, we can only traverse it in one direction. Finally, a circular linked list traversal is quite tricky as we have to stop the loop as soon as we revisit the first node. Otherwise, it will traverse it indefinitely. And this was all for today's session.
Hello everyone, welcome to Simplilearn's YouTube channel. Today, we will be discussing about stack data structure. But before we begin, let me tell you guys that we have daily updates on multiple technologies. If you are a tech geek in a continuous hunt for latest technological trends, then consider getting subscribed to our YouTube channel and don't forget to hit that bell icon to never miss an update from Simplilearn. Now, without further ado, let's get started with the agenda for today's discussion. So, at first, we will discuss what exactly are stacks. Followed by that, we will understand the representation of stack data structure using arrays and linked lists. Advancing ahead, we will understand the basic operations on stacks. And finally, we will understand the applications of the stack data structure. I hope I made myself clear with the agenda. Now, let's get started with our first topic. What is a stack? So basically, stack is a linear data structure just like arrays and linked lists. The only difference is that it follows a specific order when an operation is implemented on it. So what is the specific order that it follows? That is LIFO, last in first out, or FILO, first in last out. In the next parts, we will understand this order in a much better way. All operations can be done only at the one end of the stack, that is on the top. Now we will discuss much about that in the operations part of the stack. Now let us understand the first fundamental, that is the representation of stack. That is, how do you represent a stack normally? So a stack can be represented using two different methods, that is using an array or using a linked list. So in an array we will be using the continuous memory. And in stack, we will be using a non-continuous memory, and the stack will behave like a dynamic stack or a dynamic data structure. Now the first method, that is the array method. So in this method, an array is used to represent the stack. As you can see in the image below, we have a stack. So the name of the stack is stack itself, and you can see two more things here, that is top is equals to 2 and max is 4. So the max is the value of the array or the length of the array, the maximum length of the array, and top is the position where the last element of the stack is present. Here in this case, 56 is the last element in the stack, and top is inclined, or it is addressing to that particular address, that is 2. And now let us discuss about the linked list representation of stack. So in this method, a dynamic data structure, that is a linked list, is used to represent the stack. This representation leads to a dynamic stack. It does not need to define the maximum number of elements present in the stack. Remember, in arrays, we had to define the max value. In the previous example, we had the max value as 5, but in here, you need not to assign the max value, as the stack itself is dynamic. The pointers links are used to store the address of the upcoming nodes, and the variable used in this method is top. So the top is holding the address of the topmost element in the linked list representing the stack. Now moving ahead, we shall understand the basic operations on stack. Now here we will understand the previously discussed definition, that is push, pull, etc. in a much better way. So the basic operations on a stack are push, pop or pull, and peek. Now let us discuss each one of them in a detailed way. The first one is push operation. So the push operation is the mechanism of inserting a new element into the stack. As you can see, we are trying to insert the elements from the top. So the push operation basically involves the following steps. Check if the stack is either full or not. So basically, whenever you're trying to insert an element into the stack, you need to make sure that the stack is empty or it has some space. If it is full, you cannot insert an element into the stack. Step 2. If the stack is full, produce an error and exit. That's what I was talking about. Now the step 3. If the stack is not full, increment the top by 1. That is, when you're inserting an element, then you need to update the top value. For example, in the previous slide, when we had the array representation of a stack, we had the top value as 2. So if you try to include an element into the stack, then you need to update the top value from 2 to 3. That is incremented by 1. Now the fourth step, add data elements to the stack where the top is pointing. And finally, success. The push operation has been successful. So this is how you insert or push an element into the stack. Now followed by push operation, we have pop or pull. So the pop operation is a mechanism of eliminating or deleting or removing one data element from the existing stack. So we shall understand the pop operation in a much more detailed way. The operation involves checking the stack is empty or not. If in case the stack is not empty, then you can carry forward the pop operation. But in case if the stack is empty, then you have to provide an exit status and exit the control and leave the stack. So if the stack is not empty, approach the data element at the top, that is at the top position. For example, in the previous array example, remember, right, we had the top position pointing towards 2. So you need to take the control to the top position and pick out the element and pop it. And finally, decrease the top by 1. So when you eliminate the top element, then the top value from 2 will be decremented to 1. So this is how the pop operation is carried over on a stack. Next one is the peek operation. The peek operation involves returning the topmost data element from the stack without moving it. So here you can see the top is pointing to the element number 4 and you're peeking the element number 4 and you're not removing it from the stack. You're just returning the topmost data element. You're passing the value of the top element. So to understand the push, pop and peek operations on stack in a much more better way, let's carry out a practical example. Now we are on the practical mode and here you can see on my screen we have the code example for the stack. Now first we'll be checking if the stack is empty as per the steps mentioned in the previous discussion. We will check if the stack is empty or not. If it is empty, then we will return, else we will continue. And again, another step, we also check if the stack is full. If the stack is full, we will exit, else we will continue with the operation, whatever it is, peek, pop or push. And here we have an example for the peek operation that we discussed previously, and followed by that we have a pop operation. We are trying to exclude an element from the stack. And another one, we have the push operation where we'll be trying to push the elements into the stack. So these are the three functions for push, pop and peek. Now we'll try to push in the elements and also pop and try to involve some functions on it or run some operations on the stack. Now let's run this code and see the output. So you can see that the code has successfully executed and we have the statements here. The first one says the stack is not full, that is false, and stack is empty, that is true, right? And after that you can see that the elements which we tried to push into the stack, that is 11, 76, 71, 15 and 66 are been pushed into the stack. And if you clearly observe it, we have the element 11 in the bottom, 76 upon that, 71 upon that and 15 and last 66. So the order is first in, last out, that is the first element was pushed first, and when you are trying to eliminate the elements from the stack, then you will first pick out 66, followed by that you will pick out 15, followed by that you will pick out 71 and so on. So this is the rule what stack follows. Now I hope I made myself clear with the example. Now we shall continue with the applications of stack. So these are the few applications of stack. The first one is expression conversion. So you can see we have the infix notation, prefix notation and postfix notation. So the infix notation is no rocket science. There is only one thing here to learn, that is we have two operands A and B and we have one operator, that is the addition operator in between those two operands. And when you use the prefix notation, you will have the operator located at the first place, then you will have the operands followed by it. And in the postfix one, you will have the operands first and followed by the operands you will have the operator. So basically all the infix, prefix and postfix notations give out the same results, but the only difference is the representation of those operands and operators. Now let us understand this in a much more detailed way. So conversion of expression from one form to another form is the main application of stack. So we have the first one, that is infix to prefix and infix to postfix. Now let us see an example. Here you have 1 plus 2 star 3 plus 4. So this is the normal infix notation. And when you try to present the same expression in the form of prefix notation, so this will be the result, and this is the result for postfix. The next one, prefix to postfix and prefix to infix. And this is the way you write the prefix notation, and if you want to convert that to infix, this is how you can write it, and this happens to be the result of postfix notation. And finally, postfix to prefix, postfix to infix, and these are the results. Now, followed by expression evaluation, the next important application of stack is checking parentheses. And you can see if the parenthesis is set properly, the expression gets evaluated. If not, it will not be evaluated. Now the last one, memory management and function call. The very useful thing of using a stack is the memory will not be allocated to your stack elements unless the function is called. Here you can see it is the main function, and these are the elements that you wanted to declare into your stack. And unless you make a function call, the elements will not be declared their memory, or the elements will not get the memory allocated for them. Now another good application of stack is the backtracking problem, or the n-queen problem. The n-queen problem is an example of backtracking problem. The n-queen solution to this problem is to position the queen in such a way that the opponent queen cannot attack your queen. Now another example is string reversal. You can see on my screen we have a string that is A, B, C, D, and E. Now using stacks, you can reverse this. Right? So you're basically eliminating an element and relocating it to the first place. And finally, after reversing your string, this will be your result, A, B, C, D, and E. Followed by that, we have conversion evaluation. So stack is used to evaluating the expression, as shown in the example. Since parenthesis has the highest precedence, 5 plus 4 gets evaluated first, and it will result in 9. Then multiplication and division have the same precedence. Now the associativity comes into picture. So the associativity is always from left to right. So first, 4 into 9 will be executed, which will result in 36, and then 32 divided by 4, which will give us 8. Now we have 36 minus 8, which will give us an answer that is 26. Now the last application is the Tower of Hanoi. So the Tower of Hanoi is a mathematical puzzle consisting of 3 rods and n discs. This puzzle consists of some rules. The first rule states that one disc can move only at a time. The second rule is that the disc can only be moved when it is at the uppermost position on the stack. The third one, no disc is allowed to place on the top of the smaller disc. So this is how the Tower of Hanoi works.
Hello and welcome everyone. Today we are going to discuss queues in data structures. But before we begin, make sure to subscribe to our YouTube channel and hit the bell icon so you never miss an update from Simplilearn. Primarily, let's have a look at our plan for this session today. We will start this session with an introduction to the queue. Later, we will discuss the structure of the queue in detail. After that, we will deal with different operations that can be performed on queues. Advancing further, we will understand various types of queues and their structures. And finally, we will discuss different applications of queues to understand how queues are used to manipulate data. On that note, without further delay, let's get started with Introduction to Queue. You know that all of us depend on messaging applications like WhatsApp, Facebook Messenger, Instagram chats to communicate with our friends and family members. And while using them, you must have observed that the person you are trying to communicate with receives messages in the same order as you have sent them. Now the question that arises here is, how is this happening? How are these applications maintaining the order of these text messages? And the solution to these questions bring us to queue. Basically, in these applications, a queue is maintained for each user, containing the messages to be delivered to the user. When the user connects to the network, all the text messages in the queue gets delivered, and once the messages are delivered, empty queues get deleted. This example clearly illustrates the importance of data structures. So let's dive further and understand the structure of the queue in depth. But before doing that, let's look at a real-life example of queues to understand it more clearly. The most common and relevant example of a queue is a movie ticket counter. In the movie ticket counter, you must have observed that both of its ends remain open. Also, these ends are fixed with the help of barricades, and that is why no one can enter in between these ticket lines. Additionally, the person who enters first receives a ticket first, and the person who enters last will obviously get served at last. Queues in data structure resembles all these properties of a movie ticket counter, which makes them better at creating virtual first-come, first-served systems. Basically, they are defined as a linear collection of different data types that allow insertion at one end and deletion at another. Unlike any other data structure, the queue ends remain open, allowing it to have different functionalities at both ends. The end at which insertion takes place is called rear, and the end at which deletion takes place is known as front. Furthermore, there are two approaches to consider the structure of the queue, and both of them depend on the approach of the programmer. That means, being a programmer, if you consider the left end as front, then your rear node will be at right end. Otherwise, if you consider the left end as rear, then the right end will be your queue's front node. Unlike arrays and linked lists, elements in the queue cannot be operated from their respective locations. Here, they can only be operated from the front or rear position. Moving on, let's discuss the operations in queue data structures one by one. The first operation is enqueue. It is used to store the elements in the queue. Next up is dequeue. This operation is used for removing them. Further, we have isFull and isNull operations. IsFull function scrutinizes if the queue is full or not, and the isNull operation evaluates if the queue is empty. We also have a peek operation that helps you get the element from the front of the queue without removing it. Let's now understand how these operations work with the help of the following examples. Here we will look at enqueue5, enqueue1, enqueue-2, then isFull, then dequeue, peek, and isNull. But before explaining these operations, it's essential that we initialize the queue data structure by assigning some random size to it. For example, int queue of 3. By this declaration, we are assigning only 3 spaces for insertion in queue. Also, at this phase, there is no element in the queue as it's empty. So both the front node and rear node will point to the same location with null memory space in the storage system. Let's consider that null index to be -1 for ease of our convention. Now the first operation on our list is enqueue of 5. As we discussed previously, enqueue operation is nothing but the insertion of data into a queue data structure. It begins with checking if the queue is full or not. If the queue is full, then the previously assigned memory is completely filled with data elements. So insertion would not be possible. This is also known as overflow error in terms of programming. But as our queue is empty, so the insertion can be performed here. For that, we have to increment the rear pointer to index 0 from index -1. And once we do that, the data element 5 will be added to the queue. Also for front insertion, both front and rear will point to the same location as there is only one element present in this queue. Let's insert 2 more elements into this queue with the operations enqueue1 and enqueue-2. For that, we have to increment the rear pointer to the next index, which will be 1. Now, as the pointer is incremented, so the data will be entered into this position. Next up is enqueue-2. Again, we have to follow the same process of incrementing the rear pointer. We will increment the rear pointer to point towards the next index, that is index 2, and hence the data element with value -2 will be entered here. The next operation on our list is isFull. In this operation, if the rear pointer points to the max size, then the queue is considered to be full as there is no space left for insertion. In our case, the max size of our queue is 12 bytes. Additionally, we are considering to enter only 3 integer elements. And one integer data element takes 4 bytes of the memory space. That means 3 integer elements will take 12 bytes. Hence, this function will prompt queue is full on the screen. Now we will discuss the dequeue operation. If we want to access data from a queue, we have to perform 2 subtasks. The first one is access the data where the front is pointing, and another is to remove the data after access, and this complete process is called as dequeue operation. The first step of this operation is to check if the queue is empty. If the queue is empty, then there is no element available for deletion. This is a case of underflow error. But as our queue is not empty, we can proceed with the next steps. We will be accessing data from the front node, and later we will be incrementing the front pointer in order to remove the link to the previous node so that the data gets removed. Now, front will point to the index 1. Thus, the data value 5 will be removed from the queue and will also be prompted on the screen. Therefore, this function comes with an integer return type. Next up is peek operation. In this operation, element at the front node will be accessed without deleting it. The algorithm for this operation begins with checking if the queue is empty or not. If the queue is not empty, then data at the front node will be accessed with temporary variable and printed on the screen. Advancing further, let's perform two more dequeue operations here. First is dequeue of 1 and another one is dequeue of -2. The data at a front node will be accessed primarily, and the front pointer will be incremented to point to the next data element. When we do the pointer incrementation, the link to the previous node gets removed, which results in data deletion. Similarly, we will perform a dequeue of -2 operation here. Now, the front will be pointed to null memory space as there is no element left in our queue, and the data -2 will be removed. The last operation on our list is empty. This function checks if the queue is empty or not. In the previous procedure, we mentioned that if the front points to the null memory space, then the queue is empty. And in our case, the front is already pointing to -1. So the output of this function will be queue is empty. This is all about operations in the queue. I hope that you all are clear with these operations. Next, we will discuss different types of queues and their structures at a glance. Basically, there are 4 types of queues: linear queue, circular queue, priority queue, and double-ended queue. The structure which we have discussed till this time is that of a linear queue, so now we will move on to circular queue. The circular queue is almost similar to the linear queue, except that the last node of this queue is connected to the first. It is also known as ring buffer as all the ends are connected to another end. Additionally, this circular queue is a better version of the linear queue as it removes the drawback of insertion in the linear queue. The empty space available in a circular queue can be filled with the new element by simply incrementing the value of the rare position. We will learn about this in detail in our further sessions. A priority queue is another special type of queue data structure in which each element has some priority assigned with it. Based on the priority of each element, the elements are arranged in a priority queue. If the elements occur with the same priority, then they are served according to the first in, first out principle. In the priority queue, the insertion occurs based on the arrival, while the deletion occurs based on the priority. The above figure shows that the highest priority element comes first, and the elements of the same priority are arranged based on the first in, first out structure. The last type of queue is dequeue. Dequeue is a linear data structure in which the insertion and deletion operations are performed from both the ends. We can say that dequeue is a generalized version of the queue. Dequeue can be used as stack as well as queue as it allows the insertion and deletion operations on both the ends. If the insertion takes place at one end and deletion at another, then that dequeue is known as a linear queue. And if both addition and deletion are performed at a single end, then that dequeue is called stack. Advancing further, let's discuss some applications of queues to gauge an insight into the importance of queues. The queue data structure is used in computers, printers, and applications to utilize the benefits of the first come, first served technique. In computers, whenever you work on documents or PPTs, you must have observed that whichever key you press on the keyboard appears in the exact same order on the screen. But when your processor is too busy with other tasks, you might notice that the keys you press appear on the screen with some delay after you press them. Basically, those keys are stored in queue, and when the processor becomes free, it processes in the order the keys are pressed. That means the key pressed first will be written in a Word document first. So this is how computers use a queue to eliminate deadlocks when multiple processes are in a ready state. Next up is printers. A queue data structure is used in printers to maintain the order of pages while printing. That means the pages are stored in a queue in the order that you want to print them, and once the page is removed from an ordered queue, it gets printed. Another most common application of queue data structure is their usage in web or mobile apps. Applications like Domino's, Swiggy uses a queue for maintaining food order status. If you place an order from an online portal, your order ID enters the queue, and once the previous orders before your order ID gets catered, then your order will be catered as well. From these examples, we can clearly say that queues are used whenever there is a need for an FCFS strategy in software development. So whenever you work on projects that need a first-come, first-serve approach, then remember that you have to implement a queue data structure to complete it successfully. Finally, let's have a look at some key takeaways that we discussed in this session. We started this session by examining the structure of the queue. We learned that the queue is a linear data structure. After that, we talked about different operations of queues, in which we learned enqueue and dequeue are responsible for data manipulation in a queue. Later, we discussed different types of queues as well. Finally, we discovered some applications of queues and how they fulfill the need of FCFS systems. We have also made it clear that queues can handle multiple data types as well. So with this, we come to the end of this video.
Hello everyone, welcome to Simplilearn's YouTube channel. Today we will be discussing about Dequeue in data structure. In today's video, we have an interesting quiz for you guys. So stay tuned and do leave your answers for the quiz that's going to pop up on your screens in next few minutes. But before we begin, let me tell you guys that we have daily updates on multiple technologies. So if you are a tech geek in a continuous hunt for latest technological advancements, then consider getting subscribed to our YouTube channel and don't forget to hit that bell icon to never miss an update from Simplilearn. Now without any further ado, let's get started with the plan for today's discussion. We'll start this discussion by understanding what is double-ended queue in data structure. Followed by that, we'll understand the properties of dequeue in detail. Advancing ahead, we'll deal with the different types of dequeue. After that, we'll understand the representation of dequeue using circular queue. And further, we'll discuss different operations that can be performed on dequeue. Once finished with that, we'll implement a dequeue using circular queue. And finally, we'll cover applications of dequeue to understand its importance. I hope I made myself clear with the agenda. Now let's get started with our first topic, what is dequeue? Dequeue is an abbreviation for double-ended queue, and as the term double-ended queue suggests, it is a type of queue with some advanced features at both of its ends. But previously, we have learned that the basic queue data structure must perform insertion from one of its ends and deletion from another or opposite end. So what new limitation or feature does this particular type of queue brings? Well, the dequeue extends the concept of a linear queue by implementing insertion and deletion at both of its nodes. By that, what I mean is the dequeue data structure is acquainted with the possibility to insert and delete new elements at any node. That is why dequeue is concerned as more generalized version of queue data structure. Now, moving ahead, we shall understand the key properties of dequeue. The first property of dequeue states that the dequeue can use the LIFO principle for inserting or removing elements. The last in first out principle is used while implementing stack data structure, and according to this principle, the queue elements must be inserted from one end and should also be removed from the same end. For instance, we are storing some elements inside this queue structure which is performing both insertion and deletion from one end. However, when deletion begins, the element inserted at last will be removed first, whereas the element stored at first will get removed at the end. This property clears that the dequeue can inherit all the properties of stack data structure. The next property of dequeue states that the dequeue can use the FIFO principle for performing both insertion and deletion operations. That means the element which enters inside the queue at beginning will also leave the queue at first. Further, the element which entered at last can leave the queue at last. Both of these properties displays the uniqueness of this particular type of queue data structure. Now in upcoming slides, we will understand different types of the Dequeue. The first type of Dequeue we have is termed as input restricted queue. This terminology itself suggests that this particular type of Dequeue will have some restrictions while performing enqueue or insertion operation. In this type of Dequeue, the insertion can only be performed from one end, where deletion can be performed at both of its ends. The representation of Dequeue shown below explains how the operations in this type of Dequeue will get accomplished. The next type of Dequeue is output restricted Dequeue. This term makes clear that this type of queue will have some restrictions while performing deletion operations. In this specific type of queue, the removal of elements can only be performed from one end, where the insertion can be performed at both of its ends. This particular structure of a queue explains how the different operations will take place in this type of Dequeue. Now here is the interesting question that we want you all to answer. Based on the properties of Dequeue that we have discussed till now, which of the following data structure will be more ideal for implementing Dequeue in data structure? What I mean by ideal is the time and space complexity for implementation strategy that you decide should be minimum. The options that we have are circular array, singly linked list, and doubly linked list. It will be interesting to see how many of you guys will get this right. So guys, do leave your answers to this question in comment section below. In a week's time, we'll be announcing the right answer and you all can check it out. On that note, let's dive further and understand the representation of Dequeue using circular queue. And yes, circular queue is one of the answers for previous questions. We'll understand why it is best in upcoming slides. But please check the complexity analysis of other two strategies to decide your answer for the previous question, as multiple answers can be accurate for that question. Now let's understand what a circular queue is. Well, a circular queue is nothing but the extended notion of linear queue, as it follows the first in first out principle, with the exception that the last position of this particular queue is connected to its first position, making a circular link. This circular link is responsible for naming of this queue as circular queue or ring buffer. Let's understand how a circular queue operates with the help of simulation. This is the illustration of a circular queue having size 5. As the position of rear pointer keeps increasing, a new element will be inserted in this queue until the rear pointer reaches the end of queue. But what if we perform dequeue operation now? If we perform the deletion, then the empty space will get created at front of queue. However, this space can further be utilized in this particular type of queue by making circular incrementation of rear pointer or circular link. So, if we increment the rear pointer from its index 5 to index 0, we can utilize empty space by making new insertions. Using this feature of circular queue, we can implement both insertion and deletion at both the ends of queue. Let's understand how we can do that in upcoming slides. The first type of insertion is a pretty ordinary one. In this insertion, we'll increment the position of rear pointer to insert a new element. The arrow shown in blue is rear pointer and the arrow shown in orange is the front pointer. So as you can see, once we increment the rear pointer, new elements get inserted. This is how the insertion using rear node happens. Now, what if we want to perform insertion using front end? In order to perform the insertion using front node, we'll have to make front pointer reach to the end of queue. The only possible way to achieve that is to set front pointer equal to max size -1 manually. This command will allow a front pointer to reach the end of queue for performing insertion. And for further insertions, we'll just have to decrement the front pointer location for inserting new elements. This is all about insertion. Now that we have implemented insertion from both ends, let's move on to the deletion operation. Primarily, we'll look into the deletion using front node. In order to delete elements using front node, we'll have to increment the front pointer until it reaches the end of queue. and once it reaches the max size, we'll use circular incrementation to bring the front pointer to the beginning of queue. While performing these incrementation, meanwhile the elements will be removed from the queue. Next up is deletion using rear end. For performing deletion using a rear pointer, we'll have to decrement its location. Once we decrement the rear pointer location, the element will get removed from the queue. Now moving ahead, we'll look into the different operations that can be performed on a double-ended queue. Basically, there are 4 primary operations in the Dequeue which we have already understood in the representation of Dequeue using circular queue. These operations are insertion and deletion at the front and insertion and deletion at the rear. Additionally, the circular queue implementation of Dequeue cost us big O of 1, which is the most optimal complexity that we can hope for. Having said that, let's dive into the implementation of these operations using a circular queue. We'll implement a double-ended queue using circular queue. In order to do that, we'll use C programming language and one-dimensional arrays. So without wasting any time further, let's move to the code editor. Now, in order to get started with implementation of Dequeue, we'll have to create array and pointer variables. So let's do that. Int, we'll name this array as Dequeue and we'll provide 100 as initial size. Next, we'll create pointers and rear is equal to -1. Now, we'll also define the maximum size for our queue using define call. Size as 5. After done with this initialization process, we'll start working on insertion from front node. We'll declare a function named as void front insert. So let's do that. Void front underscore insert. And inside this function will pass an argument int z to insert an element. Now, while performing insertion, we should always check if the queue is full or not, because if it is full, then the insertion won't be possible. So for that, we'll write condition if front is equal to 0 and rear is equal to size -1 inside and braces or front is equal to rear plus 1 printf Dequeue is full insertion it's not possible. Okay. Otherwise, if both the front and rear node are pointing to null memory index or -1, we'll manually set our front pointer to index 0 to make the first insertion into the queue. And we will insert the element at new location or index 0 where the front pointer is pointing. So for that, what we'll do is we'll write another condition with else if block. Else if front is equal to -1 and rear is equal to -1, then make front is equal to rear is equal to 0. and Dequeue front is equal to Z. Now, if we want to insert the element at the last node of queue, then we need to set front pointer to the max size minus 1 location. To do that, we'll write this condition, else if front is equal to 0, then front is equal to size minus 1 and Dequeue front is equal to Z. If all these above mentioned conditions fail, then the front pointer is already at the last part of queue and it just need to decrement its location for inserting element in empty spaces as discussed previously. So to do that, we'll write one more condition using else block. So let's do that. Else front is equal to front minus 1 and Dequeue front is equal to Z. Now we have successfully implemented our front insert function. So let's move forward and work on another function that is called as void rear underscore insert, and we'll pass Z as an argument to insert an element. Now, as done previously, we will first check if our queue is full or not. So let's do that using if condition. If front is equal to 0 and rear is equal to size minus 1 inside braces, or front is equal to rear plus 1, then printf Dequeue is full. Next, if there is no element in an array, we'll manually set the rear pointer to index 0 for new insertion. So for that, we'll write condition else if front is equal to minus 1 and rear is equal to minus 1, then set rear is equal to 0 and insert Dequeue rear is equal to Z. Otherwise, if rear pointer is already at the end of queue, then we will bring it to the beginning of queue. So for that, we'll write condition else if rear is equal to size minus 1, then bring rear to index 0 and Dequeue rear is equal to z. If all these mentioned conditions fail, then what we'll do is we'll write else condition and we'll simply increment our rear pointer to make an insertion. So for that, what we'll do is we'll create else block and we inside it we will do rear plus plus and we will set dequeue rear is equal to z. With this, we have successfully implemented void rear insert function. So now let's move into deletion functions. First, we'll create void front dequeue function, void front underscore dequeue. And there is no need for any argument for this function. To begin with this function, first we'll have to check if dequeue is empty because we cannot delete elements if there is no element to delete. So for that we'll write if condition, if front is equal to minus 1 and rear is equal to minus 1, then printf there is no element to delete inside this dequeue. In the next condition, we'll check if there is only one element inside the dequeue. If there is only one element, then we'll set both front and rear to minus 1 manually. For that, what we'll do is we'll create else if condition, else if front is equal to rear, then printf we'll add /n to take this to the next line. The deleted element from the front is modulus d, comma dequeue front. And we will set front is equal to minus 1. Similarly, rear is equal to minus 1. Now, if both these above mentioned conditions fail, then we will delete the element from our front node. The first removal will be in a case when the front pointer is at the end of queue. So for that, we'll write condition else if front is at end of queue, that is size minus 1. And what we'll do is we will printf /n the deleted element from the front is modulus d, comma dequeue front, comma. And another condition will be when the front pointer is at the beginning section of a queue. For that, we'll write else condition, printf /n the deleted element from the front edge modulus d, comma dq front. With this, we have successfully implemented our front dequeue function. Now let's move towards next function, that is deletion from the rear end. For that, we'll create new function named void dequeue underscore rear. And this function also does not need any argument. So next, what we'll do is we'll create condition to check if the queue is empty or not. So if front is equal to -1 and rear is equal to -1, then printf /n, there is no element to delete inside the queue. Now let's move to the next condition. In next condition, we'll write else if front is equal to rear, then printf some statement and set front is equal to -1 along with rear is equal to -1, and that statement will be the deleted element from the dequeue using rear node edge modulus d, comma dequeue rear. Now, if both these above mentioned conditions fail, then we'll have to delete the element from our rear node. The first removal will be in a case when rear is at the beginning portion of a queue. For that, let's write a condition else if rear is equal to 0, that is at the beginning part of queue, then printf some statement and rear is equal to size -1, that is setting it to the max size of queue, and the statement that we will return is \n, the deleted element from the rear node edge modulus d, comma dequeue rear. In other cases, we'll just have to decrement the size of rear pointer and delete the element. So for that, we'll write else condition printf some statement and set rear is equal to rear -1, that is decrementing the size of rear pointer, and the statement that we'll write is \n, the deleted element from the rear node edge modulus d and comma dequeue rear. Well, here is one spelling mistake, so let's remove it. Okay. So with this, we have successfully implemented our void dequeue function. Now we will implement one more function to display the state of our dequeue. The name of that function will be void display, and this function also does not need any argument. So we'll begin with implementation of this function. For this, we'll create an iterator element and we'll set it to the front pointer, and we'll printf \n elements inside the double ended queue are next line. We'll enter into while loop to print those element. I not equal to rear printf modulus d comma dqi, and we'll increase the value of I by I plus 1 modulus size, and outside this while loop we will printf modulus d dq rear. Okay. With this, we have implemented all the required functionalities for our dequeue. So let's work on driver method, that is main function, in order to check the output of our program. So let's work on this main function. First, we will insert few elements into our queue. So I will insert first element using front insert. Next, let's insert one more element from front node using function front insert, and this element will be 23. Next, we'll insert elements using rear node underscore insert, and we'll pass 17 now. Next, we'll insert .12 and we'll insert one more element using this rear node only, insert 47. Now we will display the state of our queue after performing all these operations. And next we will dequeue few elements. So for that we'll use front dequeue function, and next we will dequeue from rear node. So dequeue rear, and after performing deletion operations we'll also display the state of our queue. So let's call display once again, and let's add one more command, return 0. Okay, so with this we have successfully implemented our program for dequeue implementation. So let's run it and check if it is working fine or not. Okay, so we are getting output here, but our display function is printing output in weird manner. So let's work it out. So all we have to do is we'll have to add space before modulus t here and here as well. So once done with this, let's recompile our code. Okay, so now our output is clear. So let's check if it is perfect or not. So the first insertion that we made was -5. Second was 23 from the front end. So 5 should be getting inserted before 23. So -5 is getting inserted before 23, but as we are inserting it using front pointer, so 23 is remaining at the front now. After these two insertions, we are performing insertions using rear pointer. The first rear insertion was 17, then 12, then 47, and these elements are getting inserted. So let me show you how they are getting inserted in exact same order. So look here. So elements inside the double-ended queue are 23, -5, 17, 12 and 47. That means the insertion is in right order. After that, we deleted the element from front node. So the front node is at 23, so 23 is getting deleted. After that, we deleted the element using rear node. So 47 is getting deleted from the rear node. We are still getting 23 here. That means the dequeue function is incomplete, so we'll have to change it. So let's go to the dequeue function, and I guess it was from front end, so we'll need to change code for our front dequeue. So okay, so in this case we haven't brought our front pointer to index 0, so let's do that here. And once we do this, let's recompile our code again. Okay, so now you can see that the 23 is getting deleted. With this, we have successfully implemented our dequeue function. Now let's move back to the PowerPoint and understand few applications of dequeue. The first application that we are going to discuss in detail is palindrome checker. You all must have heard about the term palindrome. The palindrome is a specific word or number which reads the same backward as forward. For example, the word radar. It reads the same from both the ends. So using the Dequeue, we can implement the palindrome checker program with complexity big of 1. The string which you need to check will be inserted into a Dequeue, and after that it will read from both sides. If the reading is the same, then that string will be considered as palindrome. The next application of Dequeue is its use in multiprocessor scheduling. But what precisely is multiprocessor scheduling and why do we need it? Well, the system implemented in the old days used single processor scheduling to manage the computing processes. When multiple processes need to be executed by a single core or CPU, then the process takes more time to implement, and thus the system lacks computing power. But the multiprocessor scheduling implemented in modern computers resolves that problem using a double-ended queue. Suppose we have three processors in our system and each processor has some processes to execute. Each processor maintains a D queue that contains threads that are ready to execute. The processor executes a process, and if a process creates a child process, then that process will be inserted at the front of the D queue of parent process. Suppose the processor P2 has completed the execution of all its threads. Then it steals the thread from the rear end of processor P1 and adds it to the front end of the processor P2. The processor P2 will take the thread from front end. Therefore, the deletion takes from both the ends. This is also known as A-still algorithm in process scheduling. So, with this, we came to the end of this video.
Hey everyone, welcome to Simplilearn's YouTube channel. In this session, we will learn about linear search algorithm, its complete logic, and how to program and implement it in real time. Let us take a quick look on the agenda for today's session. So we will begin with understanding what exactly is searching. Then we will learn what is a linear search algorithm. Followed by that, we will get into learning how does a linear search algorithm works in real time. Then we will look into the pseudocode for linear search algorithm. Followed by that, we will understand the complexity of linear search algorithm. And finally, we will wind up the session by understanding few important applications of linear search algorithm. I hope I made myself clear with the agenda. Before getting started, let me tell you guys that we have daily updates on multiple technologies. If you are a tech geek in a continuous hunt for latest technological trends, then consider getting subscribed to our YouTube channel. And don't forget to hit that bell icon to never miss an update from Simplilearn. Now let's get started with our first topic. Now let us try to understand what exactly is searching. Searching in data structure refers to the process of finding the desired element in the set of items. The selected item is called the target element. Any data structure such as an array, linked list, tree, or graph can be used for searching a set of elements. In data structures, searching can be categorized into two types. First type is the sequential search, in which we check the elements in a data list or an array one by one. In data structures, searching can be categorized into two ways. The first type is a sequential search, in which we check the elements in a data list or an array one by one. An example for sequential search is linear search. Now, let us learn about the next type of searching approach. The next type of searching approach is the interval search approach. Interval search divides the search in half by repeatedly targeting the center of the dataset. The binary search algorithm can be an example for interval search. We will go over the binary search algorithm in detail in our upcoming video. After understanding the logic of search and the types of search, we will get into understanding what is linear search algorithm. The linear search method is a simple search technique. In this type of searching approach, we perform a sequential search across all objects one after the other. Every element is examined, and if there is a match found, then the specific element is returned. Otherwise, the search will continue until the data gathering is complete. Let us go through an example for better learning experience. On my screen, we have the following elements: 50, 10, 20, 30, 70, 40, 90, 60 as randomly distributed elements. Let us imagine that our target element is 70. We found that our target element was 70 using linear search strategy. So, how does it work? In the next segment, we will look into the working terms of linear search algorithm. The simplest method of searching the data collection is the linear search. Starting from the beginning of the dataset, each element is examined until no match is found. The linear search is completed after the item has located. In the first stage, we compare the first element, that is 50, to the searched element, that is 70. We will go on to the next element because 50 and 70 are not matched. We will compare the second element, which is 10, to the search element, that is 70, in the next step. And once more there is no match found. Then we have the element 30 as the next comparison, and 70 and 30 are not matched. We have the next element, that is 20, in the fourth phase, and there is no match when we compare 20 with 70. Moving on to the following stage, we have the data element 70, and after comparing 70 with the search element, there is a match. We will now have the searching and display index as 4, and this index contains the searched element. We now comprehend the pseudocode of the linear search algorithm after learning the working terminology of linear search algorithm. First, we have a function called linear search, which has two variables in its parameters: the array's name, which is an array, and the search variable, which is the value. Then, using a for loop, we must search for our target variable by analyzing all the data elements in the dataset with the condition that is the searched item is identical to any set's value. We must return its index value. Now we must stop searching once the searched value has been discovered. Then we will close our if and for loop as well as the linear search function. We will now look into the complexity of linear search algorithm after comprehending the pseudocode. The complexity of linear search algorithm is divided into three categories. The best case, which is the big O of 1, the average case, which is the big O of capital N, and the worst case scenario, which is same as the average case, which is the big O of N. Here, N is the number of data items to be sorted. Let us look into how all these complexities of linear search algorithm play out in detail. First, we have the best case, which is big O of N. As a result, the best case scenario happens when the searched element is found in the dataset's first block. As a result, the search takes a constant amount of time. Here is an example of an array with 50, 10, 40, 20, 30 as the elements. Now, our search element is 50, which is located in the first location of the array. Then, there's the typical case of linear search algorithm, which has big O of N and occurs when the search element is in the middle of the dataset or any point of the dataset. With the array containing the same search element 50, we can easily see that the element 50 is present in the center of the array at the location number 2. Finally, we have the worst case, which is big O of N, which is same as that of the average case of the linear search algorithm and happens when the search element is in the last block of the dataset. As a result of the number of searches required is proportional to the number of elements. As demonstrated in this example, the search element 50 is found in the last block of the array index, which is 4. In the next segment, we will look into some real-world instances of linear search algorithms. According to the first application of the linear search algorithm, linear search is particularly efficient when it comes to discovering a particular string. Next, we will look into the second application of linear search algorithm. When a data set has only few elements, linear search is the simplest to implement. The final real-world application of the linear search algorithm is with the help of telephone directory. You may find out the name of a person with the phone number 123. This can be implemented easily using linear search algorithm. Now, let us have a look at the linear search algorithm working in practical demonstration. So on my screen, we have an example for linear search algorithm. We have included three libraries: standard input output, standard library, and console input output library. Then we have entered the main function where we have declared an array with maximum size of 50 elements, a counter variable I, a variable named target where we would store our searched element, and finally num variable where the number of elements in the array is recorded. Then we have a printf function to ask the user how many items are there in the array, and then we use a scanf function to allow input from the keyboard. So we have added %d format specifier to the scanf function, which is used for numeric values and num variable. Then using a for loop, we will try to print all the items in the array starting with 0 and ending with num variable, which is the last element. Then we will enter our search element, which we want to find among all the elements of the array. And as previously said, we'll store the found element in the target variable. Following that, we will use the for loop to examine all the elements in the array. Then we use the if statement to check for the element is identical to our searched element or not. If the element is found, we exit the for loop and we will break the keyword. And if the target value's location is less than the number of elements in the array, then we will return the location. Otherwise, if the value location is greater than the number of elements in the array, then the search will be unsuccessful and we won't be able to find the searched element. Now we will compile this code and see the output. So there you go, the code got successfully compiled. Now it is asking for the number of elements in the array. Let me give us 5 elements. Now let us enter the elements into the array. Let us enter some random elements. Now we have entered the 5 elements. Let me provide the searched element as 2. Now we have found the target element to be found in the location 2. That is 0, 1 and 2. Yeah, 2 is located in the second index location. So with that, we have come to an end of this tutorial on linear search algorithm. Hello everyone, welcome to Simplilearn's YouTube channel, and in this session, we will be discussing the tree data structure. Before we begin, let me tell you guys that we have daily updates on multiple technologies. If you are a tech geek in a continuous hunt for latest technological trends, then consider getting subscribed to our YouTube channel and don't forget to hit that bell icon to never miss an update from Simplilearn. Now without further ado, let's get started with the agenda for today's discussion. So we will be discussing what exactly is a tree data structure. Followed by that, we will understand why we need a tree data structure. Then we will learn the tree terminologies. Followed by that, we will understand tree node. Then we will see the types of trees. And followed by that, we will understand the tree traversal. And finally, we will see some applications of trees in real time. I hope I made myself clear with the agenda. Now let's get started with the first topic, that is, what is a tree data structure? So what exactly is a tree data structure? The tree is a non-linear data structure that consists of nodes and is connected by edges. I know it's a little difficult to understand just by the definition, so let me show you the pictorial representation. As you can see, we have the elements, that is 10, 20, 30, 40, 50, 60 and 70, and all these are stored in the tree data structure. They are stored in a non-linear structure. If we had used arrays, it would have been in a linear consecutive way where 10 starts first and 70 ends at the last position. Now, in the next section, we will discuss why we had made to a switch to the tree data structure when we already had a linear data structure, that is array. Now the next topic, that is why we need tree data structure. So there are many reasons why we had switched into tree data structure, and one of the reasons is a linear data structure always stores the elements in a sequential form, that is one after the other. And in operations to be performed in linear data structure, the time complexity increases as the data size increases. You can see here that, as discussed before, the elements are stored in a linear form, that is 10 at the first place and 70 at the last place. Imagine you wanted to access the element 70. Then using the traversal, you had to start from the first position, that is 10, 20, 30, 40, and slowly at the end is 70. So accessing that particular element is really time consuming. We are facing this just for 70 elements. Imagine if we had 700 elements, right? So that is exactly why we had made a switch to tree data structure. And using tree data structure, we have many advantages, as the tree data structure is completely non-linear and it allows easier access and quicker access of the data elements. How is that possible? We will look into it into the next segment where we will discuss about the traversal of trees. Now, before we understand the traversal of trees, we should understand another important topic, that is the terminologies of tree. So the first one is the node. Node is the entity that contains the keys and pointer to its child nodes. So here you can see that the elements A, B, C, D, E, F and G are the elements. So each and every element, or the blue dot, is called as a node. And the blue dots here are 1, 2, 3, 4, 5, 6 and 7. So we have 7 blue dots. So we have 7 elements here. So you can see the line between each elements, right? So this particular line is called edge. Now we'll discuss about the edge in the next part. So the connecting links between any two nodes are called as edges. So we discussed about the nodes, right, where the element is stored. The blue dots are the nodes and the lines connecting between the elements or nodes is called as the edge. So out of all the nodes, this first node, that is the element A, is called as the root node in a tree data structure. So indirectly, root node is also called as the parent node of all the nodes. Now we will understand what are parent nodes and children nodes. So in a tree data structure, the node, that is the node's predecessor, is called as parent node. So here we have discussed that A, or the root node, is the parent of all nodes. So for A, B and C nodes are children nodes, and for B and C nodes, A happens to be the parent node. Similarly, D and E are the children nodes of B, and F and G are children nodes of C. And the nodes D and E have B as the parent node, and the nodes F and G have C as the parent node. Now followed by that, we will understand the descendant node. So as discussed before, the descendant node is the node that comes after the parent node. Here, the B and C are the descendants of A, and D and E are descendants of B, and similarly F and G are the descendants or children of the node C. So in a tree data structure, the node which does not have any child is called as the leaf node. Now at the end we have D, E, F and G. So these particular nodes do not have any children nodes like B and C. So these particular 4 nodes which do not have any children are called as the leaf nodes. In a tree data structure, the node with at least one child node is called as the internal node. So here the internal nodes are B and C, which have at least one child. In a tree, the total number of children of a node are called as the degree of that node. So in this particular diagram, the degree of a root node is 2 because it has 2 child nodes, and the degree of B is 2 as it has 2 child nodes. Similarly, the degree of C is 2 because it has 2 child nodes. But when it comes to D, E, F and G, the degree is 0 because they do not have any child nodes. In a tree data structure, the root node is said to be at level 0, and the children of the root node are said to be at level 1, and the children nodes of the level 1 are at level 2. So to understand this, let's go through the diagram. As you can see, this particular root node is called as level 0. And followed by that, we have the children nodes of A, that is B and C, and that level is called as level 1. And followed by that, we have level 2. And if this tree goes forward, the levels also increase accordingly. Now, in a tree data structure, the total number of edges from a leaf node to the particular node is the longest path, and this particular path is called as the height of that node. Now here we have our general tree data structure, and here you can see the height of node A is 2. And the height of node B and C together is at 1. And the height of the last leaf nodes happens to be 0. Next, in the tree data structure, the total number of edges from the root node to a particular node is called as the depth of that node. Now in this particular tree data structure, the depth of the root node is 0. And the depth of B and C together is 1 because the number of edges connecting to the node A from B is just 1, and similarly the number of edges connecting the node C from A is just 1. So the depth of both B and C is 1. Now if we consider the last leaf nodes, then the depth is 2 because if you see, G is connected to A using 2 different edges. Similarly, F is connected to A using 2 different edges, and E and D also have 2 nodes to connect to A. So the depth is 2. Now in the next segment, we will understand the tree node. So the tree data structure has data part and references to its left and right child node in the tree data structure. So here you can see this is the node, and the node has 3 segments, that is data element and the references to its left child and the references to its right child. Now there are 4 different types of trees. The first one is the binary tree, followed by that we have the binary search tree, then we have AVL tree, and finally we have the B tree. Let us discuss each one of them. The first one is the binary tree. A binary tree is a tree data structure in which each parent node at most has 2 children. So in this particular tree, we'll have at most 2 children. That means it might have 1 or more than 1, but not more than 2 children per node. Moving ahead, we have the binary search tree. So a binary search tree or a BST is a tree data structure in which each node has a maximum of 2 children. All nodes of the left subtree are less than the right node. All nodes on the right subtree are more than the root node. So here you can see the image or the GIF which represents the image of a binary search tree. So here all the nodes of the left subtree are less than the root node and all the nodes of the right subtree are more than the root node. The next type of the tree is the AVL tree. The AVL tree got its name after inventory Georgi Adelson, Welsky and Landis. AVL tree is the self-balancing tree in which each node maintains a balance factor whose value is either 1, 0 or -1. Balance factor is equals to height of the left subtree minus height of the right subtree, or height of the right subtree minus height of the left subtree. So in this particular image, you can identify it is an AVL tree. And now the last type of tree, that is the B tree. B tree is a special kind of self-balancing search tree in which each node can contain more than one key and can have more than 2 children. B tree is also known as the height-balanced M-way tree. Now in this particular GIF, we can see how a B tree looks like. Now followed by this, we will discuss the tree traversal. So traversing a tree helps to visit required node in the tree to perform specific operations. Tree traversal can be performed in 3 different ways. The first one is the pre-order traversal, where we visit the node and visit all the nodes from the left side, then visit all the nodes from the right side. So this particular GIF is an example for pre-order traversal, where we visit all the left side nodes first, then we visit the right side nodes. Now we will move ahead into the next type of traversal. That is the in-order traversal. First, we visit all the nodes from the left side, then we visit the root node, and then we visit all the nodes from the right side. So this particular GIF will be an example for the in-order traversal, where we visit all the left side nodes, then we visit the root node, and followed by that we will visit the right side nodes. And the last type of traversal is the post-order traversal, where we visit all the nodes from the left side first, then we visit all the nodes from the right side, and finally visit the root node. So this particular image on the right side is an example for post-order traversal. Now before we get into learning the applications of trees, we will try to execute one example based on the post-order, pre-order and in-order traversals in tree data structure. So you can see that we have an example on my screen right now. So here we have the node structure, then we have the in-order traversal function, followed by that we have the pre-order traversal function, and finally we have the post-order traversal function. Now let's quickly run this program and see the output, and don't worry about the code. This particular code document will be attached in the description box below and you can have access to it. Now we have the run option over here and the program got successfully executed. You can ignore this warning, and here we have the in-order traversal of the tree and the first output. Then we have the pre-order traversal of the tree, and finally we have the post-order traversal of the tree. Now let's discuss the last part, where we will learn the application of trees. So the application of trees are as follows. Binary search trees are used to quickly check whether an element is present in the set or not. Then we have the most popular database usage of B tree, which is a variant of tree data structure. Then we have the modified version of trees called as tries, which is used in the router to store routing information. And finally, the compiler uses a syntax tree to validate the syntax of every program you write. So with that, we have come to an end of this tutorial on tree data structure.
Hey everyone, welcome to Simplilearn's YouTube channel. In this session, we will be learning about tree traversal in data structures. So let's take a look at the agenda for today's session. First, we will begin with understanding what exactly is tree traversal in data structures. Next, we will understand the data structure used for implementing tree traversal. After that, we will learn the types of tree traversals in data structure. And lastly, we will discuss the different applications of tree traversal in data structure. But before we begin, let me tell you guys that we have daily updates on multiple technologies. If you are a tech geek in a continuous hunt for latest technological trends, then consider getting subscribed to our YouTube channel and don't forget to hit that bell icon to never miss an update from Simplilearn. Now, without further ado, let's get started with our first topic, that is, what is tree traversal in data structure? Tree traversal is a process of visiting each and every node in a tree data structure. So right here on my screen, we have a tree with different nodes, that is A, B, C, D and E. So here we will be visiting all the nodes one after the other using the tree traversal methods. Now that we have a brief understanding of what exactly is a tree traversal process, let's get into the next topic of our discussion for today, that is the data structure used for tree traversal. In a tree data structure, there are primarily two data structures utilized for tree traversal. The first one is the stack data structure and the second one is the queue data structure. A stack is a linear data structure that operates on the last in, first out, LIFO principle. There is only one pointer in the stack, that is the top pointer, which points to the stack's topmost element. Only the top of the stack is used for insertion and deletion. Now the next one is the queue. A queue, unlike stacks, is open on both the ends. The one end is always open and used only for input and the other is only used for deletion or elimination. The principle followed in queue is first in, first out or FIFO approach. Followed by that, we will look into the different types of tree traversals in data structure. Tree traversal can be done in the following ways. The first one is breadth first search and the second one is the depth first search. First, let us have a look at the breadth first search algorithm or breadth first search traversal. We follow level order traversal in breadth first search. Breadth first search traverses nodes by level instead of subtrees. First, we visit the root node. Followed by the root node, we visit the left subtree of the tree. Then, followed by the left subtree, we finish the right subtree of the entire tree. After that, we go until the leaf nodes of the entire tree is found. The second one is the depth first search. In depth first search, we traverse tree data structure in three ways, that is pre-order traversal, in-order traversal and post-order traversal. Let us take a look at how these traversals are carried out. First, let us discuss the pre-order traversal. We traverse the root node first in the pre-order traversal. Then we traverse through the left subtree and finally we traverse through the right subtree. Then there is in-order traversal. In-order traversal involves traversing of the left subtree first, followed by that we enter the root node, then we visit the right subtree. Lastly, we have the post-order traversal. So post-order traversal involves traversing of left subtree first, then the right subtree, and finally we visit the root node. Now next, we will have a look at some of the important applications of tree traversal in data structure. So we use tree traversal in data structures to build a prefix expression or Polish notation from expression trees. Then utilize the pre-order traversal and then traverse the expression tree in a pre-orderly manner. A binary tree's postfix representation or reverse Polish notation can be generated using post-order traversal. Because it returns values from the underlying set in order, according to the comparator setting up the binary search tree, in order traversal is often employed on binary search trees. A complete binary tree can be deleted or released when deleting or freezing nodes and values in the post-order traversal. Now, next we will see an example based on tree traversal in data structures.
So on my screen we have an example for tree traversal in data structure. To begin, we have included the enum or user specified data type traversal. It mostly used to give integral constant names which make a programmer easier to comprehend and maintain. We defined three variables in the enum data type, that is pre-order, in-order and post-order traversal. We can define the type that can take one of the two values by using the typedef and enum keywords. We have a traversal data type with trav variable and a node data type with node variable. Then we define the node using the data structure type as struct node. We declare one variable x and two nodes as a left and a right nodes respectively in this node section. We then attempted to create a node using the create node function, passing the root node as an argument. In this code, we use a malloc function to create a node, assign data to x and null to both the right and left nodes before returning to the root node. If node t is not equal to null, we simply return it. Otherwise, we will use the released tree function to release the left and right nodes. And if neither is a root node, then we will use the free function to release the node t, which will behave as the root node. Then we define the display tree function, which takes the trav variable and the root node as parameters. There is a condition in this function, that is, if the root node is not null, we will return the root node. Then, using the switch case scenario, we attempted to traverse the tree using all three types of traversals. We utilize a trav variable in the switch function, so if any of the in-order, pre-order or post-order variables match the trav variable, the traversal will be executed. Then, we created a tree using the createTree function, which takes a data variable as input. In the createTree function, we used a malloc function to create the root node, and we first assigned null to the left and right nodes, as well as the data to the variable x before returning to the root node. We first traversed the root node, then the left subtree, and finally the right subtree in the pre-order traversal case. In order traversal case, we first traverse the left subtree, then the root node, and finally the right subtree. And in the post-order traversal case, we traverse the left subtree, then the right subtree, and finally traverse through the root node. And finally, we exit the display tree function and moved on to the main function. We assign the values 5 as the root node, then 10, 20, and 30 as the left nodes, and similarly 15, 25, and 35 as the right nodes, and then we call the three tree traversals, that is pre-order, in-order, and post-order, to traverse the tree. And finally, we release the root node. Now, let us try to execute this program and see the output. So there you go. The program got successfully executed, and you can see that the output has been displayed on my screen. So the pre-order traversal is 5, 10, 20, 25, 15, 30, and 35. Followed by the pre-order traversal, we have the in-order traversal, that is 20, 10, 25, 5, 30, 15, and 35. And finally, we have the post-order traversal, that is 20, 25, 10, 30, 35, 15, and 5. And with that, let me give you a simple question. So what is the pre-order and post-order traversal of this binary search tree? So the elements are 1, 2, 3, 4, 5, 6, and 7. You need to find out the pre-order and post-order traversal of this binary tree, and you can let us know the answer in the comment sections below. With that, we have come to an end of this tutorial on tree traversal in data structure. Hey everyone, welcome to Simplilearn's YouTube channel. In this session, we will learn about binary trees in data structures. But before we begin, let me tell you guys that we have daily updates on multiple technologies. If you are a tech geek in a continuous hunt for latest technological trends, then consider getting subscribed to our YouTube channel, and don't forget to hit that bell icon to never miss an update from Simplilearn. Now without further ado, let's get started with the agenda for today's discussion. So we shall begin our session by learning a binary tree and some basic terms related to binary tree. Then we will try to implement it in the code editor. After that, we will discuss its properties. Then we will discuss different types of binary trees. Then we will try various operations on them like traversal, insertion, and deletion. And finally, we will take a glance on what are our final key takeaways from this session. But before we begin, make sure that you have subscribed to our YouTube channel and clicked on that bell icon to never miss an update from Simplilearn. So without further ado, let's get started with our first topic, that is, what exactly is a binary tree? So it is a tree data structure in which each node can have at most 2 child nodes. These nodes are referred to as left child node and right child node. Next, let's discuss about some terms related to binary tree. First up, a node. A node consists of data and a link to its both child nodes. Next, the root node. Root node is the first node of the tree. Next, leaf nodes. These are the nodes which has no child. Next, parent node. Apart from the root node, Any node which has at least one child is called as parent to that child node. Next up, a child node. Any node with a parent is called as a child node. Next up is the internal node. Any node with a child and a parent is called as an internal node. Next up is the height of the binary tree. The longest path from the root to any leaf node is called as the height of the binary tree. Next up is the depth of the binary tree. The depth of the node is the total number of edges from the root node to the target node or the last child node. Now let's try to implement the binary tree in the code editor. As you can see, now we are on the code editor and the code on my screen is an example for binary tree. Now here you can see that we have created a structure for node, followed by that we have a function where we will print the tree, and this is our main function. Now don't worry about the code, this particular code segment will be available in our description box below and you can always have access to it and try to edit and run this code on your own local system to have a better learning experience. Now without further ado, let's try to run this program quickly and see the output. So there you go, the code got successfully executed and here you can see the output of this particular binary tree. Now let's get back to the theory part. So as discussed before, followed by the implementation part, we will learn about the properties of a binary tree. Now let's discuss the properties of the binary trees. First up, maximum number of nodes at a level L is 2 to the power L. Next up, maximum number of nodes in a binary tree of height h is equals to 2 to the power of h minus 1. Next up, minimum possible height in a binary tree with 2 nodes is equals to log of L plus 1 base 2. Next up, the minimum possible level in a binary tree with n nodes is equals to log of L plus 1 base 2. Finally, a binary tree with L leaves has at least log L base 2 plus 1 levels. Now, let's discuss about the different types of binary trees. First up, we have the full binary tree. Followed by that, we have the complete binary tree. Then we have the perfect binary tree. Followed by that, we have the balanced binary tree. And lastly, the degenerate binary tree. Let's discuss about these in detail. First up, full binary tree. A full binary tree is a unique tree data structure in which a node can have either 2 children or no child. Next, a complete binary tree. So a complete binary tree is another specific binary tree where each node on all levels except the last level must have 2 children, and at the lowest level, all leaves should reside possibly on the left side. The next one is the perfect binary tree. A binary tree is perfect if every node must have 2 children and every leaf is on the same level. The next one is called as the balanced binary tree. A binary tree is balanced if for each node the height of the left subtree and the height of the right subtree varies at most by just 1. At last we have the degenerate binary tree. A binary tree is said to be degenerate if every internal node has only one child. We have now discussed the binary tree, some terms and properties related to binary trees, and types of binary trees.
Now we will look into the operations that needs to be performed on the binary tree. So there are basically 3 types of operations that can be performed on binary tree, which are traversal, insertion, and deletion. So first we'll look into the traversal operations. There are 3 different types of traversal operations possible on binary tree, which are pre-order traversal, in-order traversal, and finally the post-order traversal. Now let's get back into the text editor mode and try to execute our example. So right now we are on the text editor and this particular code is for the traversal operations on our binary tree. And here you can see we have the structure for node and we have also the in-order function, pre-order function, and post-order function. And don't worry about the code, this particular code will be available in the description box below. And after you have written the code, we have some standard input over here. You can see that we are giving the number of edges as 4, and the left subtree elements are 2 and 1, and the right subtree elements are 2 and 3, and another left subtree elements are 3 and 5, and lastly we have 5 and 6 for another left subtree. Now let's try to execute this code. Now we have already executed the code, and we also have the output over here, and here you can see we have entered the number of edges as 4, and the traversal is in order traversal, which is 1, 2, 6, 5 and 3, and the pre-order traversal output is 2, 1, 3, 5, 6, and the post-order traversal is 1, 6, 5, 3 and 2. Now let's get back to the PPT. Now we have the insertion operation. And now let's get back to our text editor and try to see an example for insertion operation as well. So on my screen you can see an example for insertion operation. So here we have the insert function. As I said, this particular code will be available in the description box below. Now let's provide the standard input. So the standard input will be 4 edges, and we have 2 and 1 as the left subtree, and 2 and 3 as right subtree, 3 and 5 as left subtree again, and 5 and 6 as the left subtree. Now let's quickly run this code, and there you go, the program got successfully executed, and here we have the output. The nodes got inserted, and it has provided an in order traversal, that is 1, 2, 6, 5 and 3. Now let's get back to the presentation, and the last type of operation is the deletion operation. Let's quickly execute an example based on deletion operation as well. Now as you can see, we are on the text editor again. Now here the example is for deletion operation. We have the delete function over here. Now for this particular program we don't need any standard inputs, so just let's run the program. So there you go, the program got successfully executed, and we have the output over here. And in order traversal before deletion, and in order traversal after the deletion of an element. So the deleted element is element 11. Now with that, let's get back to the presentation mode again. So that's how the element got deleted. Now we have reached to the last part of this session, that happens to be the final key takeaways. So what are the final takeaways? So binary tree is faster at search operations than other type of tree, and it is easier to find maximum and minimum elements in the binary tree. Binary tree does not allow duplicate values, and graph traversal is done using binary tree. It is used to convert the postfix expressions into the prefix expressions. So these were the final takeaways. Now with that, we have come to an end of this session on binary trees.
Hey everyone, I'm Krushkal and I welcome you all to Simplilearn's YouTube channel. In this session, we will talk about binary search trees. We shall begin our session by introducing binary search trees. Then we will discuss some of the properties of binary search trees. After that, we will try various operations on them like insertion and deletion. Finally, we will sum up what we have learned from this session. But before we begin, make sure you have subscribed to our YouTube channel and clicked on the bell icon below so you never miss an update from Simplilearn. So without any further ado, let's get started with introduction to binary search tree. Binary search tree is a set of nodes organized in such a manner that they all have the same binary search tree characteristics. A key and a value is assigned to each node. The requested key is compared to the keys in binary search tree. So during search, if the key is found, then the corresponding value will be retrieved. Next up, properties of binary search tree. First up, the left subtree of a node contains only nodes with keys lesser than the parent node. Next up, the right subtree of a node contains only nodes that are greater than the parent node. The left and the right subtree each must also be a binary search tree. Next, let's discuss what are the operations we can perform on a binary search tree. First up, insertion. Last, deletion. Let's discuss them in detail. First up, insertion.
We can insert a node in such a way so that we obey binary search tree rules. That is, the new node should be either less than the parent node if it's on the left subtree, or if it's on the right subtree, it should be greater than the parent node. Let's execute this in the code editor. We will start by creating a class for the binary search tree. So class bst int data and bst pointers left, comma, right. Next, we will define some functions publicly. Public first default constructor, and a parameterized constructor. A function to insert the value. And a function to traverse the node. Now let's write default constructor's definition. So bst Now let's write the parameterized constructor's definition. Bst int value data is equals to value and left is equals to null and right equals to null. Now let's write the definition for the insert function. So bst bst star root, comma, int value. Now we will check if the tree is empty or not. So if root, then we will insert the first node. So we will return new bst value. Otherwise we will insert the data. So if the value is greater than root data, then we have to insert it in the right subtree. So root right is equals to insert root right, comma, value. Else the value should be inserted in the left side. So root left is equals to insert root left, comma, value. And then we will return root. Now let's write the traverse function. So void tst traverse tst star root if root then we will return otherwise we will first traverse left side, then we will print the root data. And then we will traverse the right side root right. Now let's write the main block. So we will start with an empty tree. So bst b, comma, star root is equals to null. The root is equals to b dot insert root, comma, 50. B dot insert equals to root, comma, 10. B dot insert gonna be root, comma, 30. B dot insert gonna be root, comma, 50. Sorry, we already used 50, so we will use 60. B dot insert root, comma, let's use 20. Let's try to traverse this. So B dot traverse route. Let's execute this. As you can see, we have successfully created and traversed our first binary search tree. Let's get back to slides.
At last, deletion. We will delete a node following the binary search tree rules. That is, the value of the left subtree should be less than the parent node, and the value of the right subtree should be greater than the parent node. Let's try these in the code editor.
Let's start by creating a node. This time we will use structure. So struct node int key struct node star left comma star right. Now we will create a utility function to create a new binary search tree node. So struct node star new node int item. Struct node star temp equals to struct node star malloc size of struct node. Next, temp will be assigned the key is equals to item. Temp left equals to null and temp right is equals to null. Now let's write a function to traverse the tree. Traverse struct node star root. So if root is equals to null, so traverse root left cout root e traverse root right. Now let's write a utility function to insert the new node with the given key in the binary search tree. So struct node star insert struct node star node comma int key. So if node is equals to null, then we will return new node key. Otherwise, we will recur down the tree. So if key is less than the node key, then we will insert in the left subtree. So node left is equals to insert node left comma key. Else node right should be inserting key. Now let's return the node. Now we have given a non-empty binary search tree, so we have to return the node with the minimum key value found in that tree. So we will start struct node star min value node struct node star node struct node star current is equals to node. So we will loop down to find the leftmost leaf. So while current and parents left is not equals to null, so current should be equals to current to return current. Struct node star delete node struct node star root comma int key. if root equals to null, return root. Now, if the key to be deleted is smaller than the root's key, then it lies in the left subtree. So we will check if key less than root key, then root left will be equals to delete node root left key. Comma key. Now, if the key is deleted is greater than the root's key, then it lies in the right subtree. So else, if key is greater than root, root right is equals to delete node root right comma key. Else, if roots dot left equals to null and root dot right is equals to null, then return null. Else, if root left equals to null, then struct node star temp is equals to root right and free root. Return temp. Else, if roots right is equals to null, then struct node star temp is equals to root tree root return temp. Now node with the two children get the in-order successor smallest in the right subtree. So struct node star temp is equals to min value node root right. Now we will copy the in-order successors content to this node. So root is equals to temp. Now we will delete the in-order successor. So root right equals to delete node root right comma temp t. Now we will return root. Now let's write the main block. We will start with an empty tree. Struct node star root is equals to null. Now root is equals to insert root comma 2 root is equals to insert root comma 5 root is equals to insert root comma 3 root is equals to insert root comma 4 root is equals to insert root comma 7 and root equals to insert root comma 6. Let's try to traverse this. So see out traversal of the given tree. traverse route. Now first we will delete a value. So C out, delete 2, now root is equals to delete node root comma 2. Now C out, traversal after deleting the traverse route. Let's execute this. As you can see, we have successfully deleted 2 and traversed the tree again. Let's get back to our slides.
At last, let's sum up what we have learned from this session. First up, left side nodes are always lesser than the parent's node, and the right side node are always more than the parent node. Next, it is easier to search and sort elements in a binary search tree. Finally, a binary search tree offers faster insertion and deletion operations. And this was all for today's session.
Hello everyone. Welcome to Simplilearn's YouTube channel. Today we will be discussing about recursion in programming. In today's video, we have an interesting quiz for you guys. So stay tuned and do leave your answers for the quiz that's going to pop up on your screens in next few minutes. But before we begin, let me tell you guys that we have daily updates on multiple technologies. So if you are a tech geek in a continuous hunt for latest technological advancements, then consider getting subscribed to our YouTube channel and don't forget to hit that bell icon to never miss an update from Simplilearn. Now without any further ado, let's get started with the agenda for today's session. We will start this session by understanding what is recursion. Followed by that, we'll find out how recursion gets executed in memory area. Once done with that, we'll look into different types of recursion. And finally, we will implement a program that demonstrates the concept of recursion. I hope I made myself clear with the agenda. Now let's get started with our first topic, what is recursion? Well, recursion is a process in which a function repeatedly calls itself either directly or indirectly. Those calls are majorly done by explicitly calling function by its name. However, it can also be accomplished by implicit calling as well. The fundamental idea behind calling the function over and over again is to break a larger problem into smaller subproblems. We do this for reducing the computational complexity of a larger problem by breaking it into several pieces. This tactic is also called as divide and conquer approach in programming. So now you must be thinking about how we can break the larger problem into smaller subproblems. Well, to do that, we break the given problem statement into two parts. The first one is base case and the second one is recursive step. The base case is nothing but the simplest instance of a problem that consists of condition which holds the recursive function. Given the function call's argument, this base case computes the output of our program right away. Whereas in the recursive step, we compute the result using one or more recursive calls to the same function, but with the inputs decrease in size or complexity. To understand this breakdown, let's have a look at mathematical aspect of recursion. Suppose you have to formulate a mathematical function for computing the sum of n natural numbers. That means the function that you are going to create must calculate the summation of all natural numbers in the range 0 to n. Mathematically, it can be represented as summation of all numbers from k is equal to 0 to k is equal to n. Now the critical question here is, how can we actually represent this in form of recursive function? The answer is quite simple. All we need to do is break this larger problem into small fragments. We can represent this problem as n plus sum of all natural numbers till n minus 1. This process of traversing in function f n minus 1 times is called the recursive step of our problem statement. Whereas the base case is a condition which is stopping the recursion when k is reaching value 0. In terms of programming, it can be represented using if block. Now I hope you guys have understood how we can break a larger problem into smaller subproblems. Moving further, we are going to understand how recursion gets executed in memory area. In order to do that, we'll take this C program as an example. In this program, we have two methods. The main method contains one variable and the statement that invokes a function named fun. This function fun is making a recursive call in its function body. We have both base case and recursive step inside this function's body. Now, whenever a function is called, its activation record will be maintained inside the stack. So for this program, we are going to look into its control flow. As we know, the main function gets invoked primarily by an operating system. Thus, we'll include the main function at first in our memory stack. This activation record will consist of local variables of function, parameters, and the record of return address to the caller. But here, for the sake of simplicity, we are just maintaining the local variables inside the activation record. After this step, as you can see, the main function is activating method fun with argument 3. Once activated, it will prompt 3 on screen and will invoke fun 3 minus 1. That is fun 2. Now again, as 2 is greater than 0, the control will invoke fun 2 minus 1. That is fun 1. After this, the control will activate fun 0. This time, once the control enters an if block, it will execute a return statement, and activation record 0 will get popped out of the memory stack. Further, every function inside the memory stack will get popped out from it, which will result in generation of output. The output that will get printed on the console for this particular program is 321. Now, here is the interesting question that we want you all to answer. Based on the properties of recursion that we have discussed till now, which of the following statements seems right to you? The options that we have are: recursion is always better than iteration. Option B. Recursion uses more memory compared to the iteration. Option C. Recursion uses less memory compared to the iteration. It will be interesting to see how many of you guys will get this right. So guys, do leave your answers to this question in comment section below. In a week's time, we'll be announcing the right answer and you all can check it out. Now moving ahead, we'll discuss different types of recursion in programming. There are basically 4 types of recursion. The first one is direct recursion, the second one is indirect recursion, the third one is tail recursion, and the fourth one is non-tail recursion. So let's discuss direct recursion. A function is called direct recursive if it calls itself in its function body over and over again. To better understand this definition, let's look at the structure of a program that is direct recursive in nature. In this program, we have a method named fun which is calling itself again and again in its function body. Thus, we can say that it is direct recursive in nature. Next up is indirect recursion. The recursion in which the function calls itself via another function is called as indirect recursion. For example, in this program, you can clearly see that the function fun1 is explicitly calling fun2, which is invoking fun1 again explicitly. Hence, we can say that this is an example of indirect recursion. Further, we have tail recursion. A recursive function is said to be tail recursive if the recursive call is the last execution done by the function. Let's try to understand this definition with the help of an example. If you observe this program, you can see that the last line ADI will execute for method fun is recursive call, and because of that, there is no need to remember any previous state of our program. Finally, we have a non-tail recursive function on our list. A recursive function is said to be non-tail recursive if the recursion call is not the last thing done by the function. After returning back, there is something left to evaluate. Let's consider one example. In this function, you can clearly observe that there is another operation after the recursive call. Hence, our ADI will have to memorize the previous state inside this memory block. That is why this program can be considered as non-tail recursive. Now finally, let's implement a program to demonstrate the recursion. The program that we are going to implement is solution to the problem statement that we discussed earlier. According to that problem statement, we have to calculate the sum of n natural numbers given the number n. Now in order to address this problem, we are going to use C programming language. So without any further ado, let's head over to the code editor. Now, in order to get started with coding implementation, first we'll create an utility function to calculate sum of n natural numbers. So let's do that, and we'll pass an argument int n. Now we have arrived inside the body of function sum. What we'll first do is we'll calculate sum of n minus 1 natural numbers by making a recursive call to function sum. So let's do that, sum n minus 1, and we'll store this value inside a temporary variable. Now we'll add this temporary variable's value to n in order to return it as a result. The statements that we just wrote are called as recursive steps. But if you observe this statement, we are not putting any limitation to our recursive call. So that is why we'll have to add base case to our function. So let's do that. If n equal to 0, then return 0. With this, we have successfully implemented our sum function. So let's work on our driver method to generate the result. In this driver method, first we'll create a variable n, and after that we'll write a printf statement. Enter the natural number n to calculate the sum of n numbers. Semicolon, and in next line we'll write scanf statement in order to take input from our user. So inside this we'll write modulus d, comma, ampersand n, and semicolon. And in next statement we'll make a call to our sum function in order to calculate sum of n natural numbers. So how we can do that? Well, we can add modulus d here, comma, sum n, semicolon, and I hope our code works fine now. So let's check it by compiling. Here the console is asking us to provide with value of variable n, and I'm going to provide value 5 here. So let's provide value 5 and enter. So the output that we are getting is 15 here. That means our code works fine. With this successful coding implementation, we came to the end of this video.
Hey everyone, I'm Baba Khandelwal and I welcome you all to Simplilearn's YouTube channel. In this session, we will talk about AVL trees. We shall begin our session by what is an avial trees. Then we will discuss various rotations we can perform to balance avial trees. Then we will discuss the complexity of avial trees. After that, we will try various operations on them like insertion, deletion. Finally, we will sum up what we have learned from this session. But before we begin, make sure you have subscribed to our YouTube channel and clicked on the bell icon below so you never miss an update from Simplilearn's YouTube channel. So let's get started with introduction to avial trees. An avial tree is a height balanced binary search tree. For each node, we have to make sure that the height of the left subtree and the right subtree can differ by at most 1. We can calculate this balance factor by subtracting the height of the left subtree from the height of the right subtree. Now let's discuss various rotations we can perform on avial trees. First up, LL rotation. Next, RR rotations. Next, LR rotation. At last, RL rotation. Let's discuss them in detail. First up, LL rotation. It is a clockwise rotation when a node is inserted on the left subtree of a node. Then we apply this rotation to balance the tree. It is applied on the node below the balance factor 2 node. That is, we will apply right rotation on the green node. Next, RR rotation. When a node is inserted into a right subtree of a node, then we perform RR rotation. It is an anti-clockwise rotation which is applied on the node below a node having balance factor -2. That is, we will apply it on the green node. Next up, LR rotation. When a node is inserted into right subtree of the left subtree of a node, then we perform LR rotation. It is a combination of RR and LL rotation. First, we will apply RR rotation on green and yellow node. After this, red node is still unbalanced, so we will perform LL rotation on the yellow node. Finally, RL rotation. When a node is inserted into the left subtree of a right subtree of a node, then we perform RL rotation. It is a combination of LL and RR rotation. First, we will apply LL rotation on green and yellow nodes. After this, the red node is still unbalanced, so we will perform RR rotation on the yellow node. Now, let's discuss complexity of avial trees. First up, space complexity is a big O of n. Next up, avial tree offers a complexity of big O of log n for searching. Next up, avial trees offer a complexity of big O of log n for insertion. Finally, avial tree offers a complexity of big O of log n for deletion. We have now introduced an avial tree and rotations on it. Now, let's discuss some of the operations we can perform on avial trees. First up, insertion and deletion. Let's discuss them in detail. First up, insertion. We will insert a node following binary search tree rules. Then we will check if the nodes are balanced or not. If they are not, then we will balance it by using suitable rotations. Now let's try these operations in a code editor. Let's start by creating a node. To create a node, we need a class node. We will create its member as public. Int key node star left node star right int height. Now let's write a function to get maximum of two integers. So int max int a comma int b.
Now let's declare a utility function to get maximum of two integers. So int max a comma int b. Now let's write a function to get the height of the tree. Int height node star n. Now if n is null, then we will return 0. Else we will return n calls height. Now let's write that function to get maximum of two integers. Int max int a comma int b. We will return if a is greater than b, then we will return a, else we will return b. Now let's write a helper function that allocates a new node with a given key and null left and right pointers. So node star new node int key. Node star node equals to new node. So node key will be equals to key node left will be equals to left. Node left will be equals to null and node right will be equals to null and node height will be equals to 1. And return node. Here we have kept height as 1 because at the new node is initially added at leaf. So by default it will always be at 1. Now let's write a utility function to right rotate subtree rooted with y. Node star right node star y. Now node star x is equals to y's left and node star e2 is equals to x right. Now we will perform rotation. So
x right will become y and y's left will become t2. Now we will update the heights. So y height is equals to max of height of y left comma height of y right plus 1. Now x height equals to maximum of height x left comma height of x right plus 1. Now return x Now let's write a utility function to left rotate subtree rooted with x. So node star left rotate node star x node star y will be equals to axis right and node star t2 will be equals to axis y's. Now we will perform rotation. So y left will be equals to x and x right will be equals to t2. Now let's update height. So x height is equals to maximum of height of axis left comma height of axis right and y's height equals to maximum of height of y's left comma height of y's right. Return y. Now let's write a function to get balance factor of node n. So int get balance argument as node pointer n. If n is equals to null, then we will return 0. Otherwise, we will return height of n's left minus height of n's right. Now let's write a recursive function to insert a key in the subtree rooted with node and returns the new root of the subtree. So node star insert node star node comma int key. Now we will perform the normal BST insertion. So if node is equals to null, then we will return new node key. Now if this key is less than node's key, then node left will equals to insert node left comma key. Or else we will insert that in the right. Node right is equals to insert node right comma key. Now we will return node. This if else will make sure that we will reach to the leaf node and then we will insert the key. Now we will update the height of this ancestor node. So node height is equals to 1 plus max height of node left comma height of node right. Now we will get the balance factor for this ancestor node to check whether this node became unbalanced. So int balance is equals to get balance Now if this node becomes unbalanced, then there are 4 cases. So if balance is greater than 1 and key is less than node left key, then we will return right rotate node. This if statement for the left case, so or LL case. Now let's write it for the right case or RR case. So if balance is less than -1 and E is greater than node right key, then we will return left rotate node. Now write for the left right case or LR case. So if balance is greater than 1 and key is greater than node left key, then node left is equals to left rotate node left. Now return right rotate. Now let's write the right left case or RL case. So if balance is less than -1 and key is less than node to the right key, then node right will be equals to right rotate node to the right, and we will return left rotate. Now we will return this node. Now let's write a function to print pre-order traversal of this tree. So void pre-order node star root. So now if root is not null then cout root key and now pre-order root and pre-order Now let's write the code for the main block. We will start with an empty tree. Node star root is equals to null. Now we will try to construct tree. So root is equals to insert root comma 10. Now root is equals to insert root comma 5. Root is equals to insert root comma 2. Root is equals to insert root comma 3. Root is equals to insert root comma 7 and root is equals to insert comma 9. Now let's try to print this tree. So cout avial tree is equals to tree in tree order tree order root. Let's execute this. As you can see, we have successfully created our first avial tree. Let's get back to slides. At last, deletion. We will delete a node following a binary search tree rules. Then we will check if all the nodes are balanced or not. If they are not, then we will balance it by using suitable rotations. Now let's try these operations in a code editor. Let's start by creating a node. To create a node, we need a class node. We will define its members as public int key node star left node star right int height Now let's write a utility function to get height of the tree. So int height node star n. If n is equals to null, then in that case we will return 0. Otherwise we will return n's height. Now let's write a utility function to get maximum of two integers. Int max int a comma int b. So we will return if a is greater than b, then a, else b. Now let's write a helper function that allocates a new node with a given key and null left and right pointers. So node star new node int key. So node star new node is equals to new node parenthesis. Now new node will get key as key. New node left is equals to null, and new node right is equals to null, and new node's height is equals to 1, because new node is initially added as leaf. That's why it is always be given as 1. Now we will return this node. Return node. Now let's write a utility function to right rotate a subtree rooted with y. So node star right rotate node star y node star x is equals to y left node star t2 is equals to x right. Now we will perform rotation. So x right is equals to y left is equals to t2. Now we will update heights. So y height equals to maximum of height of y's left comma height of y's right plus 1, and x height is equals to maximum of height of x's left comma x's right plus 1. Now we will return this new root. So return x. Now we will write node star left rotate node star x node star y will be equals to axis right and node star t2 will be equals to y's left. Now we will perform rotation. So y left equals to x and x right is equals to t2. Now we will update these heights. So x height is equals to maximum of height of x left comma height of x right plus 1 and y's height is equals to max of height of y's left comma height of y's right plus 1. Now we will return this y. Now we will write a function to get balance factor of node n. So int get balance node star n. So if n is equals to null, then we will return 0. Otherwise we will return height of n's left minus height of n's right. Now let's write a function to insert a node. So node star insert node star node comma int key. Now we will perform normal BST rotation. So if node is equals to null, then we will return new node key. So now if key is less than node key, then node left will be equals to insert node left comma key. Now if key is greater than node key, then node right is equals to insert node right comma key. Else we will return node because equal keys are not allowed. Now we will update the height of the ancestor node. So node height equals to 1 plus max height of node left comma height of node right. Now we will get the balance factor of this ancestor node to check whether this node becomes unbalanced. So if int balance equals to get balance of this node. Now if this node becomes unbalanced, then there are 4 cases that could be possible. First up, LL case. So if balance is greater than 1 and key is less than node left key. Return right rotate node. Now let's write right case. So if balance is less than -1 and key is greater than node right key, then we will return left rotate node. Now let's write left right case. So if balance is greater than 1 and key is greater than node left key, then node left will be equals to left rotate node and we will return right rotate node. Now let's write the case for right left case. If balance is less than -1 and key is less than node write. So node write is equals to write rotate node write. Now we will return left rotate. Node. Now let's return the unchanged node pointer. So return node. Now let's write a function to find minimum value node. So node star min value node. Node star node. So node star current equals to node. So while current left is not equals to null, current is equals to current at left. Now we will return current. Now we will write a recursive function to delete a node with the given key from subtree with the given root. So node star delete node. Its arguments are node pointer root, comma, int key. For starters, we will perform standard BST delete. So if root is equals to null, then we will return root. Now, if the key to be deleted is smaller than the root key, then it lies in the left subtree. So, if key is less than root key, then root left will be equals to delete node root to the left, comma, key. Now, if key to be deleted is greater than the root key, then it lies in the right subtree. So else if key is greater than root key, then root right equals to delete node root right comma key. Now if the key is same as the root key, then this is the node to be deleted. So else if root left equals to null or root to the right is equals to null, then node star temp is equals to root left now if temp is equals to null, then temp will be equals to root and root will equals to null. Else root will be equals to star temp and free temp. Else node star temp is equals to min value node root right Now we will copy the in-order successors data to this node. So root e is equals to temp key. Now we will delete this in-order successor. So root right is equals to delete node root comma temp key. Now if root is equals to null, Then we will return root. Now we will update the height of the current node. So root height is equals to 1 plus max of height of roots left, comma, height of comma, height of root right. Now we will get the balance factor of this node. So int balance is equals to get balance root. If this node becomes unbalanced, then there are 4 cases. First up, LL case. So if balance is greater than 1 and get balance of roots left is greater than equals to 0, then we will return right rotate. Now if balance is greater than 1 and get balance of root left less than 0, then root left will equals to left rotate root left. Now we will return right rotate root. Now let's write right case. So if balance less than -1 and get balance is less than equals to 0, then we will return left rotate now we will write right left case. So if balance is less than -1 and get balance of root right is greater than 0, then root right is equals to right rotate of root right. Now we will return left rotate and we will return this root. Now let's write a function to print pre-order traversal of this tree. So void pre-order node star root so if root not equals to null, then cout root e a pre-order root left and pre-order root right. Now let's write a code for the main block. We will start with an empty tree. So node root is equals to null. Now root is equals to insert root comma 2 root is equals to insert root comma 10 root is equals to insert root comma 9 root is equals to insert root comma 7 root is equals to insert root comma 5 root is equals to insert root comma 3. Now let's try and print this available tree. So cout created AVL pre-order pre-order now we will delete a node. So root is equals to delete node root comma 10 Now let's again try and print this. So cout modified behavior tree pre-order after deletion of 10. Layout handle pre-order root. Repeat. Now let's execute this. As you can see, our deletion function is working perfectly. Now let's get back to our slides. At last, let's sum up what we have learned from this session. First up, AVL trees is a self-balancing binary search tree. Next, every node must have a balance factor of either -1, 0 or 1. Next, after every rotation, we must verify if each node is balanced or not. Finally, AVL trees offers fast insertion and deletion operations. And this was all for today's session.
Hey everyone, welcome to Simplilearn's YouTube channel. In this session, we will learn about bubble sort, its complete logic, and how to program and implement it in real time. Let us take a look at the agenda for today's discussion. And meanwhile, be kind enough to get subscribed to our YouTube channel and don't forget to hit that bell icon to never miss an update from Simplilearn. First, we will begin with understanding what is bubble sort algorithm. Next, we will understand the working procedure of bubble sort algorithm. After that, we will understand the pseudocode of bubble sort algorithm. Later, we will learn the optimized bubble sort algorithm, and next, we will see some varieties of bubble sort algorithms. After that, we will understand the complexities of the bubble sort algorithm, and finally, we can wind up the session with application of bubble sort algorithm. I hope the agenda was clear. Hoping we are good to go, let's get started with our first topic. Let's try to understand what is a bubble sort algorithm. The bubble sort algorithm is one of the fundamental and simplest forms of algorithm used to sort a collection of elements. The collection of elements can be either a set of numbers or characters. The control iterates through a sequence of numeric or character type elements in the bubble sort algorithm and rearranges them into ascending or descending order. The bubble sort algorithm rearranges one element at a time. The bubble sort algorithm is also known as the sinking algorithm. Here we have some random distributed elements which are 30, 10, 20, 50 and 40. And after performing the bubble sort algorithm, all the elements are sorted as 10, 20, 40 and 50. So how is it done? We will see in the next segment where we will understand the working terminologies of bubble sort algorithm. The bubble sort algorithm will not get implemented on the entire array in one go. Instead, it compares two adjacent pairs of elements in an array. If the elements are not in the correct order, then they are swapped, so the largest of the two moves towards the right. And this process continues until the most significant element, or bubble, is moved towards the highest position. After the first process is finished, the search for the next most significant object starts. And the swapping continues until the whole array is in correct order. This process is employed when you want to arrange the elements in ascending order. To understand the logic in a better way, let's go through an example. The example on my screen consists of 5 elements. According to the bubble sort algorithm logic, we need 4 iterations to sort all the elements in the ascending order or in descending order. The elements in the array are as follows. They are 3, 8, 4, 2 and 12. So in this array, the index begins with 0 and ends with 4. And each time, the bubble sort algorithm goes through the data element list and it is known as a pass. Let us analyze the total number of comparisons required to sort the array in the correct order. According to the formula, if n is the total number of elements in an array, then the total number of comparisons needed to sort the entire array can be calculated by a simple formula shown on my screen. That is, n is equals to n minus 1. So in this scenario, we need 5 minus 1, that is 4 comparisons or passes to sort the entire array. In the first pass, there are 4 steps. Let us select the first 2 elements, that is 3 and 8. According to the requirement, we need to sort this array in the ascending order. Hence, when we compare 3 and 8, clearly we get 3 as the least number, so we do not need to swap them. Next is the step 2. Comparing the second and third elements, which are 8 and 4. Here, we need to swap these 2 elements because 8 is always greater than 4, and it requires placing the elements in the ascending order. Now moving ahead, we have step 3. Moving on to the third and fourth elements, which are 8 and 2, and here again we need to swap 8 with 2 because 8 is greater than 2. And in the step 4, we have the last elements, which are 8 and 12. There is no need to swap because 8 is already less than 12, so you can see it clearly. So now we enter into pass 2, and in pass 2 we need 3 steps. So the first step, in the second pass, let us select the first 2 elements, which are 3 and 4. No swapping is necessary as they are already in order. Next we have step 2. In step 2, we need to select the elements 2 and 4. As you can see, 2 is always less than 4, so there is no swapping required. Next we have step 3. In step 3, we need to compare the elements 4 and 8. And here, we may not need any switching because 4 is already less than 8. Now here you can see that we are not comparing 8 and 12 because the last element is already sorted. Now, we have come to the last pass. And here, there is only one step. The step is to compare the first 2 elements, 2 and 3, and then swap them as 3 is greater than 2. Now, the array is finally sorted and we do not need to do any more comparisons. After understanding the working process of the bubble sort algorithm, we will see its pseudocode. In this pseudocode, there is a function named as bubble sort. The bubble sort function includes an array of collections of sortable elements. Let us consider n as the length of the array. After that, we have to repeat comparisons for the first element to the last element of the array. If the first element is greater than its next consecutive element, then we must swap both the elements and place them correctly. We do not need to switch after closing this repeated statement and getting out of the loop. This bubble sort function will end. After understanding the pseudocode of the bubble sort algorithm, let's learn about the optimized bubble sort algorithm. So we can optimize the algorithms in a loop by programming it to avoid the comparison at n-1 position after every iteration, since the nth element is already sorted in the previous iteration. More generally, more than one element may be placed in their final position on a single pass. All the elements after the last swap are sorted in every pass and do not need to be rechecked. Optimized bubble sort algorithm allows skipping over many elements. This results in a worst case, that is 50% improvement in comparison count, and adds little complexity because of the new code subsums the swapped variable. Next, we will learn variations of the bubble sort algorithm. So, there are 2 variations of the bubble sort algorithm. They are odd even sort and cocktail shaker. So, odd even sort is a parallel version of bubble sort for the message passing system, whereas cocktail shaker is a sort of bidirectional bubble sort that first goes from beginning to the end and ends to the beginning. After knowing the variation of the bubble sort algorithm, now we will see the complexity of bubble sort algorithm. So the best case of the bubble sort algorithm is big O of n, where n is the number of elements being sorted, and worst and average cases of the bubble sort algorithm are big O of n into n, and lastly, the space complexity of the bubble sort algorithm is big of 1. Here, N is the number of data elements being sorted. Let us understand, when this complexity occurs, the best case of bubble sort algorithm is O of n, which occurs at all the data elements in an array are already sorted. Here we have an example with some data elements in an array which are already sorted, that is 10, 20, 30, 40 and 50. Next, talking about the average and worst case. The worst case and average case of the bubble sort algorithm is O of n to the power 2, that is n squared or n into n. It occurs when all the data elements in an array are reversely sorted. Again, we have an example that consists of data elements that are reversely sorted, that are 50, 40, 30, 20 and 10 in an array. Lastly, we have space complexity. The space complexity of bubble sort algorithm is O of 1 because only one additional variable is required to implement bubble sort algorithm, that is temporary variable. We came to the last topic where we will understand 4 main applications of bubble sort algorithm. First application of bubble sort algorithm states that this sorting technique is used to sort the elements in a specific order. The bubble sort algorithm uses less storage and is the second application of bubble sort algorithm. Third, the real life application states that the bubble sort algorithm is used to sort the students based on their height in a line. Lastly, bubble sort is used to create a stack, pile up the elements based on their height. After covering all the bubble sort algorithm topics, we will now see a practical demonstration of bubble sort algorithm. Now, on my screen, we have an example for bubble sort algorithm. So, let us get started with the code. In this code, at the first position, we have some header files, that is standard input, output, standard library, etc. After that, we will define the main function. In the main function, we will declare an array with maximum size of 50. So here, you can see that we have the first array variable that size is 50. Size will be defined with declaration only because we cannot change the array size in the runtime. After that, we will declare 4 variables, that is a, b, num and temp. Num variable will store the number of elements of an array. After that, we will ask the user how many elements are required for the array using printf function. So here is the printf function where we will be asking the user to enter the number of elements in an array. And the user will enter the elements and this will be done using scanf function. Then finally, we will print all the elements that the user wants to store in an array using another printf function. We will have 3 loops. Firstly, there will be a loop from the first element to the last element of the array. So this is the first for loop we need. Then second, the for loop will use the variable a for the rotation purpose. As we know, rotation equal to number of elements minus 1. So it will make a loop from index 0 to number minus 1. The last loop is used for how many passes will be required for the implementation. And we already pass equally to the number of elements minus number of rotations minus 1. So there is the loop from index 0 to number minus a minus 1. Then there will be the if condition, stating that if the first element of an array at index b is greater than the element at the index b plus 1, then we will make swap. Then we will come out of the loop and we will print all the array elements after performing the bubble sort algorithm. Now, let's quickly execute this program and see the output. So you can see the program got successfully executed. Now, let us enter the number of elements. Let me choose 5. Now, let us enter the elements in a random order. So this was the array input 3, 2, 4, 1 and 5, and here after executing the bubble sort algorithm we have the sorted array, that is 1, 2, 3, 4 and 5. And with that we have come to an end of this tutorial. Hope the video was helpful and informative.
Hey everyone, I'm Vibhav Khandelwal and I welcome you all to Simplilearn's YouTube channel. In this session we will discuss insertion sort algorithm. We shall begin our session by introducing insertion sort. Then we will discuss insertion sort algorithm. After that, we will implement the insertion sort algorithm in the code editor. Finally, we will sum up what we have learned from this session. But before we begin, make sure you have subscribed to our YouTube channel and clicked on the bell icon below so you never miss an update from Simplilearn's YouTube channel. So without any further ado, let's get started with an introduction to insertion sort. Insertion sort is basically a sorting algorithm in which each item in the final sorted array is sorted one at a time. And it is significantly less efficient than more sophisticated algorithms like quicksort, heap sort, or merge sort on larger datasets. Now, let's discuss the algorithm of insertion sort. Let's say we have an array. We will start with traversing the array from index 1 to n-1. While traversing, we will compare elements at the current index to its predecessor. If the data at the current index is smaller than its predecessor, then we will compare it with the element before that. After that, we will shift bigger elements to an index up to make space for swapped elements. Then we will shift the bigger elements to an index up to make space for the swapped element, and then we will iterate the same steps again to sort the complete array. We have now introduced the insertion sort and its algorithm. Now let's implement this algorithm in the code editor. We will start with creating a function to sort an array using insertion sort. So void insertion sort we will give it argument as int array arr comma int size. We will declare variables int I comma key comma j. Now we will create a loop, for loop, from I is equals to 1 to I less than size I plus plus. Here we are traversing this array from index 1 to the size n minus 1. So key is equals to arr at I and j is equals to I minus 1. Now we will move the elements of arr 0 to I minus 1 that are greater than the key to one position ahead of the current position. So while j is greater than equals to 0 and arr at j is greater than key then we will swap these. So arr at j plus 1 is equals to arr at j and j will be equals to j minus 1. And then we will assign arr j plus 1 is equals to key. Now we will write a function to print this array of size. Void print array. We will give its argument as int array and size. We will declare int I is equals to 0. For loop I is equals to 0, I less than size I plus plus. See out ARR ARR bracket I and say out handle. Now we will write the main block. So int ARR is equals to 12, 11, 15, 9, 6, 7. And size is equals to, we will find the size using size of, so size is equals to size of ARR divided by size of ARR at index 0. Now we will print this array without sorting. So cout unsorted array and we will print array ARR, size. Now we will call insertion sort ARR, size. Cout, we will print this array sorted Now we will again call print array argument as ARR, size. Now let's print this. As you can see, our function is working flawlessly. It has sorted this array. Let's get back to our slides. At last, let's sum up what we have learned from this session. First up, insertion sort is efficient for arrays with small datasets. Next up, insertion sort requires a constant amount of extra memory. Next, insertion sort can only sort a single element at a time. And finally, insertion sort has the worst complexity of big O of n square. And this was all for today's session. Hope you guys found it informative and helpful.
Hey everyone, I'm Baba Khandelwal and I welcome you all to Simplilearn's YouTube channel. In this session, we will discuss selection sort algorithm. We shall begin our session by introducing selection sort. Then we will discuss selection sort algorithm. After that, we will implement selection sort algorithm in the code editor. Finally, we will sum up what we have learned from this session. Before we begin, make sure you have subscribed to our YouTube channel and clicked on the bell icon below, so you never miss an update from Simplilearn's YouTube channel. So without any further ado, let's get started with an introduction to selection sort. The selection sort algorithm is an in-place comparison-based method that divides the list into two halves, with the sorted portion on the left and the unsorted half on the right. Then the smallest element from the unsorted array is chosen and swapped with the leftmost element, and that element is added to the sorted array. Now let's discuss the selection sort algorithm. Let's say we have an array.
First, we will divide this array in two subarrays, unsorted array and sorted array. Then, we will divide the minimum element from the unsorted array and swap it with the leftmost element of this unsorted array. After that, we will add it to the unsorted array. We will keep repeating this process until there are no elements left on the unsorted array. We have now introduced selection sort and its algorithm. Now, let's implement this algorithm in the code editor. We will start by creating a function swap. The argument will be integer pointer x, comma, integer pointer y. We will declare an element temp to store the value of pointer x. Then we will store pointer y's value in x. Then we will store temp's value in y. And that's how we can swap them. Next, we will write the definition of selection sort function. Void selection sort. Argument will be int array arr, comma, int n. We will declare variables int I, j, and a min underscore idx variable to store the minimum index. Now we will one by one move boundaries of unsorted subarrays. So for loop I is equals to 0, where I is less than n minus 1, I plus plus. We will find the minimum element in this unsorted array. So min underscore idx is equals to I. Now for j is equals to I plus 1, j less than n, j plus plus. If array element at jth location is less than array at the min index, then min idx will be updated with j. Now we will swap the found minimum element with the first element. So we will call swap function with argument as ampersand arr at min idx, comma, ampersand arr at ith location. Now we will write a function to print this array. So void print array, argument as int arr, and its size int n. For loop int I is equals to 0, I less than n, I plus plus, out arr at I out and Now we will write the code for the main block. So int arr is equals to 4, 2, 1, 8, 3. We will find the size of this array. So int n is equals to size of array arr divided by size of this array's first element. Now we will call selection sort function. Argument as arr, n. Then we will try to print this. So cout sorted array and we will call the function print array to print this array arr, n. Now let's try and execute this program. As you can see, we have successfully sorted this array using selection sort algorithm. Let's get back to our slides. At last, let's sum up what we have learned in this session. First up, the selection sort algorithm is a comparison-based in-place algorithm. Next, the selection sort algorithm is not appropriate for used datasets. Next up, selection sort have the worst complexity of big O of n square. Finally, it can be beneficial when memory write is an expensive procedure. And this was all for today's session. Hope you guys found it informative and helpful.
Hey everyone, welcome to Simplilearn's YouTube channel. In this session, we will learn about merge sort in data structures. Now, let us quickly look into the agenda for today's session. We will first begin with understanding what exactly is divide and conquer algorithm. Next, we will try to define the merge sort algorithm. After that, we will understand the working of merge sort algorithm. Later, we will learn the pseudocode of merge sort algorithm. After that, we will understand the complexities of merge sort algorithm. Next, we will see some of the real-time applications of merge sort algorithm. And finally, we will wind up the session by understanding some of the important drawbacks of merge sort algorithm. But before we begin, let me tell you guys that we have daily updates on multiple technologies. So if you are a tech geek in a continuous hunt for latest technological trends, then consider getting subscribed to our YouTube channel and don't forget to hit that bell icon to never miss an update from Simplilearn. So without further ado, let's get started with our first topic, that is, what exactly is divide and conquer algorithm? A divide and conquer algorithm iteratively divides a problem into two or more subproblems of the same or relative type until they are simple enough to be solved directly. The subproblem solutions are then integrated to solve the original problem. There are three steps involved in the divide and conquer principle, that is, divide, conquer, and combine. The first step is to divide the significant problem into smaller subproblems. The second phase is to conquer the solutions to all divided subproblems. Then, the final step is to combine and merge all of the solutions to create a definite solution. We will understand this by an example right here on my screen. Suppose we have a large problem. We can use divide and conquer technique to divide it into n number of subproblems such as problem 1, problem 2, problem 3, problem 4 and so on until we reach the problem n. Then we conquer all the solutions to the specified subproblems as solution 1, 2, 3, 4 and so on. And finally, we merge all the solutions to get one definitive solution. Now that was divide and conquer algorithm. Followed by that, let us get into merge sort algorithm. So merge sort is one of the most efficient sorting algorithms. It is based on divide and conquer strategy. Merge sort continuously divides a list into numerous sublists until each sublist contains only one entry, then merges all those sublists into a sorted list. There are 4 elements on my screen. We have 7 and 3 in the left half and 5 and 2 in the right half. After dividing the 4 elements in half, we combined all the items in ascending order, that is 2, 3, 5 and 7. In the next segment, we are going to understand how it happened and we are going to learn the working procedure of merge sort algorithm. There are 2 approaches to implement the merge sort algorithm. The first method is top-down approach and the second method is bottoms-up approach. The first method, that is the top-down approach, implies that it begins with the large picture. From then, it's broken into smaller chunks. Now the second method, that is the bottom-up technique, which starts with a specific number of jobs and works its way up to the general. Let's have a look at how to implement the merge sort algorithm using top-down approach. The top-down merge sort approach is the methodology that uses a recursion mechanism. It starts at the top and proceeds downwards, splitting the array into 2 halves, making a recursive call and merging the results until one gets to the bottom of the array. For a better understanding of the top-down approach method, consider the following scenario right here on my screen. We have an example of an array of size 6 consisting of elements 7, 3, 9, 5, 6 and 4, starting with 0 and ending with 5. Using the following formula, we'll divide the array by its middle. That is, middle is equals to left plus right divided by 2. We have 3 elements on the left and 3 elements on the right near the middle. So according to the top-down strategy, we divide the given array in half, resulting in 3 elements, that is 7, 3 and 9 on the left and 5, 6 and 4 on the right. Next, we sort all these elements in ascending order. By doing so, the first half will be 3, 7 and 9 and the right half will be 4, 5 and 6. And after merging all of them, we will have the sorted array, that is 3, 4, 5, 6 and 9. Next, we will understand the bottoms-up approach. An iterative process is used in bottoms-up merge sort approach. It starts with a single element array and then joins 2 neighboring items while also sorting them. The combined sorted arrays are combined and sorted again only until one single unit of the sorted array elements remains. Now let us look at an example right here on my screen. In the first iteration, we will merge pairs of array sizes by 1, sorting each of the 2 elements. When you iterate the array by size 1, the elements 7 and 3 become 3 and 7. Similarly, 9 and 5 become 5 and 9. And finally, 6 and 4 become 4 and 6. We will merge the pairs of array size by 2 in the next iteration with the bottoms-up method. As a result, the elements 3, 7 and 5 will become 3, 5 and 7, and the same way 9, 4 and 6 will become 4, 6 and 9. In the last iteration, merge pairs of array size by 3 so that after sorting 3, 5, 7, 4, 6 and 9 becomes 3, 4, 5, 6 and 7 as sorted arrays. After understanding the working procedure of merge sort algorithm, we will now see the pseudocode of merge sort algorithm. We have a function called merge sort in this pseudocode, and parameter of the function contains an array named as array and 2 variables named as left and right. If the number of elements in the left is greater than the number of elements on the right, we will get a middle using formula left plus right divided by 2. The merge sort is called and this function now has an array, a left variable and right variable. By calling merge sort, we have array left as middle plus 1 and right variable. And finally, by calling merge sort, we have left, middle and right variables. In our upcoming segment, we will implement the merge sort method in a practical demonstration. In the next section, we will discuss the complexity of merge sort algorithm. First, we will look into the time complexity of merge sort algorithm. As we all know, Time complexity in data structures is divided into best case, average case, and worst case. The best case of merge sort algorithm is big O of n into log n. Average case of merge sort algorithm is big O of n into log n. And the worst case of merge sort algorithm is big O of n into log n. The number of elements being sorted is given by n. Merge sort's time complexity is big O of n star log n in all three situations, that is worst, average, and best, because it always divides the array into two halves and merges the two halves in linear time. It takes up the same amount of space as the unsorted array. As a result, it is not a good idea to use it to search big unsorted arrays. Moving on to the space complexity of the merge sort algorithm, the space complexity of the merge sort algorithm is large O of n. In the merge sort algorithm, we store the left and right parts of the merged array in the temporary arrays and then utilize the original array to keep the entire merged array. In the worst case scenario, the left and the right sub arrays will each be n by 2 in size, and then the total auxiliary space will be big O of n, resulting in a space complexity of big O of n. Following that, we will look into several applications of the merge sort algorithm. So the first application is merge sort is an efficient way to sort linked list in big O of n log n time. Subsequent application of the merge sort algorithm is for linked lists. Merge sort implemented without taking up more space. Followed by that, the merge sort method is used to count the number of inversions in a list. Last application states that in internal sorting, the merge sort is employed. Now let us look into some of the drawbacks of merge sort algorithm. So some of the drawbacks of merge sort algorithm are: for smaller assignments, merge sort algorithm is slower than the other sorting algorithms. For temporary array, the merge sort technique requires an additional memory space, that is, space of big O of n. Now let us look into a practical demonstration of merge sort algorithm.
On my screen, we have an example for merge sort algorithm. To define constants or micro substitution, we use the hash define as preprocessor directive with a constant variable max of 10. Following that, two arrays, array 1 and array 2, are declared. We declare array 1 and initialize it with elements like 8, 4, 7, 6, 2, 3, 5, 9, 10, 4 and 1. Array 2 is used for temporary array. Then, to implement the merge sort concept, we declare a merge sort function. We specify three variables in this function parameter, that is left, right and middle. The left variable is used to display the left part of the array 1, the right variable is used to display the right part of the array 1, and middle variable is used to indicate the middle or center of the array in this function. We utilize the for loop in this function, setting the left to level 1, the middle plus 1 to level 2, and the left to variable I with the condition that level 2 is less than or equal to the middle and level 2 should be less than or equal to the right of the array. We have a condition in this for loop that if level 1 of array 1 is less than or equal to level 2 of array 1, we will initialize all the consecutive elements of level 1 of array 1 to array 2. Else, we will initialize all the successive elements of level 2 of array 1 to array 2. Out of for loop, all subsequent elements of level 1 of array 1 will be initialized to array 2 until level 1 is less than or equal to the middle. All successive elements of level 2 of array 1 will be initialized to array 2 until level 2 is less than or equal to the right of the array. Using the loop, which will run from I equal to the left of I is less than or equal to right, we initialize all the items of array 2 to array 1. We have declared one more function in this code, namely sorting. Out of the merging sort function, in which only the left and right variables are defined, we specified the middle function in the sorting function with the condition that if the left is less than the right, the middle will be calculated as left plus right divided by 2. Then we called the sorting function passing left as middle as right, and then another sorting function passing left as middle plus 1 and right. Finally, we use the merge sort function passing left, middle and right to the sorting array 1, otherwise we would return nothing. We entered the main function out of the sorting function where we declared the counter variable I and printed the array before sorting using the printf function in for loop where I will run from index 0 to the array's maximum size. After that, we invoked sorting method passing left as 0 index number and right as the array's maximum value. Finally, after doing the merge sort process, we will print the array using the printf function and for loop. We will run from 0 to the array's maximum value. Then, we compile the program and run it. Now, let's try to quickly execute this program and see the output. So, there you go. The program got successfully executed and the list before sorting is 8, 7, 6, 2, 3, 5, 9, 10, 4 and 1. And the list after sorting is 1, 2, 3, 4, 4, 5, 6, 7, 8, 9 and 10. And with that, we have come to an end of this session on merge sort algorithm.
Hey everyone, I'm Weber Khandelwal and I welcome you all to Simplilearn's YouTube channel. In this session, we will discuss quicksort. We shall begin our session by introducing quicksort. Then we will discuss quicksort algorithm. After that, we will implement quicksort in the code editor. Finally, we will sum up what we have learned from this session. But before we begin, make sure you have subscribed to our YouTube channel and clicked on the bell icon below so you never miss an update from Simplilearn's YouTube channel. So without any further ado, let's get started with an introduction to quicksort. A quicksort is a highly efficient sorting algorithm and it is based on partitioning an array into smaller subarrays. And then we will sort these two resulting subarrays in the same manner. This algorithm is quite efficient for large size data sets as its average and worst case complexities are big O of n square. Now let's discuss algorithm of quicksort. Let's say we have an array. First, we have to select a pivot. We can select either the first element or the last or medium or any random element as pivots. This pivot will dissect the array into two subarrays. Then we will shift all smaller elements than the pivot element to the left. Then we will again apply the same operation for the left subarray and take pivot like we did for the main array. We will perform the same for the right subarray as well. We have now introduced the quicksort and its algorithm. Now let's implement this algorithm in the code editor. We will start by creating a function swap. So void swap int star x comma int star y int temp is equals to star x is equals to star y is equals to temp. Now we will write a function which will partition this array. This function will take the last element as pivot and the pivot element at its correct position in sorted array and places all smaller elements to the left of the pivot and all greater elements to the right of the pivot. So int partition int arr comma int low comma int high. So int pivot equals to arr high now int I is equals to low minus 1. So for
int j is equals to low, j less than equals to high minus 1, j plus plus. Now if current element is smaller than the pivot, so if ARR at j is less than pivot, then we will increment the I. Then we will swap ampersand array at I comma ampersand array at j, then we will swap ampersand array at I plus 1 comma ampersand array at high. And then we will return I plus 1. Now we will write the main function that implements quicksort. So void quicksort int arr bracket comma int low comma int high. So if low is less than high, int pi is equals to partition arr comma low comma high. Now we will separately sort elements before partition and after partition. So quicksort arr comma low comma pi minus 1 and quicksort arr comma pi plus 1 comma high. Now we will write a function to print this array. So void print array int arr comma int size int I. So for loop I is equals to 0, I less than size I plus plus cout array at I cout and L. Now we will write the main block. So int array and comma 7 comma 8
Now we will find the size. So int n is equals to size of array is divided by size of array element at 0. Now we will call quicksort for array comma 0 comma n minus 1. Now we will print this. So cout sorted array now print array arr comma n. Now let's execute this. As you can see, we have successfully sorted our array. Let's get back to our slides. At last, let's sum up what we have learned in this session. First up, quicksort follows the divide and conquer principle. Next up, quicksort has an average space and time complexity of big O of n log n. Next, all pivots should be selected in the same manner as the first pivot. Finally, quicksort is an unstable sorting algorithm, so even a single mistake can crash our program.
Hey everyone, welcome to Simplilearn's YouTube channel. In this session, we will be learning about graphs in data structures. But before we begin, make sure that you have subscribed to our YouTube channel and don't forget to hit that bell icon to never miss an update from Simplilearn. Now without further ado, let's get started with the agenda for today's discussion. So we will be discussing a brief introduction to graphs first. Followed by that, we will understand the graph terminologies. Up next, we will see the types of graphs available in data structures. After that, we will understand the representation of graphs. Then we will look into the graph traversal. And finally, we will understand the application of graphs. I hope I made myself clear with the agenda. Now, let's begin with the first topic, that is a brief introduction to graphs. So what exactly is a graph? So a graph is a data structure like any other data structure, example linked list, arrays, etc. So graph is a little different from the other types of data structures such as linked list and arrays. They are linear data structures, whereas graph is a non-linear data structure that consists of finite sets of vertices and a bunch of edges connecting with them. So what are these vertices and edges? So let us understand that a graph is usually represented by a set of vertices and edges. So a vertex is the node present in a graph. Imagine that you are a group of 5 friends. So each one of you is considered as a vertex and the network connecting you guys is known as an edge. So the overall graph of you people can be considered as G and it is represented by vertices and edges set, where vertices is you and the network connecting you guys is called as an edge. So here you can see it clearly. Each one of the friend is called as a vertex and the network connecting them is called as an edge. And the entire graph is represented using a set of vertices and edges. Now moving ahead, we will understand the graph terminologies. Now at first we have the adjacency vertices and adjacency edges. So what are adjacent vertices? If there is an edge between two vertices, that is one vertex or one node is connected to another node directly using just one single edge, then those vertices are called as adjacent vertices. Now what are adjacent edges? If there is one common vertex between two edges, then those two edges are called as adjacent edges. Let's imagine this way. let us imagine that we have 3 vertices and these 3 vertices are connected using 2 edges. So here we have one vertex which is common between these 2 edges. So such type of edges are called as adjacent edges. Next we have the degree. In an undirected graph, number of vertices adjacent to the vertex is called as a degree. Next is the path. The path is considered as a sequence of distinct vertices such that 2 consecutive vertices are adjacent to each other. Up next we have the cycle. A path that has only one repeated vertices are called as first and last vertices. Followed by that we have the walk. The term walk is self-explanatory. A walk is the sequence of vertices and edges in the graph which is used to traverse through one vertex to another vertex. Now we have entered the next segment of this particular tutorial where we will be discussing the different types of graphs available. So at first we have the finite graph. So what exactly is a finite graph? A graph is said to be finite when the number of vertices and the number of edges are in a finite number or in a countable number. Now the next type of graph is the infinite graph. So what exactly is the infinite graph? So the infinite graph is a typical opposite of the finite graph. So this particular graph will not have countable number of edges and countable number of vertices. The image here is an example for a typical infinite graph. Now followed by the infinite graph, we have the trivial graph. So what is a trivial graph? A graph is said to be trivial if there is only one single vertex without any edges. So this particular type of graph will only have vertex that is only one single vertex, not more than one, and there will be no edge. If you have just one vertex, then there is no possibility of having an edge, unless if you have one single loop type of edge, which is connecting to itself. But in a trivial graph, we don't even have that. We just have one single vertex. So followed by trivial graph, we have a simple graph. So what exactly is a simple graph? A graph is said to be simple if there is only one and one edge between each vertex. So this particular example can be considered as a simple graph. So here, each and every set of vertices have one single edge between them. Now followed by the simple graph, we have the multigraph. So if there are multiple edges between the pair of vertices, then this particular type of graph is known as a multigraph. So here you can see that we have 2 vertices, A and B, and we have 2 edges connecting them. Not one, but 2. But in a simple graph, we were supposed to have just one edge connecting the vertices. So this is the difference between simple graph and a multigraph. So followed by multigraph, we have a null graph. So what is a null graph? A graph is said to be null if there are only vertices and no edges between them. So remember the trivial graph, right? We just had one single vertex but no edges. But here we do have multiple vertices but no edges connecting them. So this type of a graph is considered as null graph. So followed by null graph, we have the complete graph. So what is a complete graph? A graph is called as a complete graph where each vertex must be connected with the other vertices using the edges. So the meaning of this particular type of graph is all the edges are connected to all the other edges using at least one single edge. So here you can see A is connected to B, D and C all together with at least one edge, and similarly all other vertices are connected to each other with at least one single edge. Now followed by the complete graph, we have the pseudo graph. So what is a pseudo graph? A pseudo graph is a graph where at least one vertex will have self-looping type of edge. So remember the self-loop or self-edge we have discussed in the trivial graph type. So this particular type of an edge where it connects to itself is called as a loop or kind of self-connecting edge. So any graph that has this kind of a edge is called as a pseudo graph. So followed by the pseudo graph, we have the directed graph. So what is a directed graph? Any graph is called as a directed graph where each edge has a direction associated with it. So far we have just discussed the edges which are connecting to one or the other vertex, but there was no direction. But here you can see that this particular edge has a direction, that is from B to A, not from A to B, it is from B to A. This type of edges which are directing the traversal of the graph are known as the directed graphs. Now followed by the directed graphs, we have the regular graph. So a graph is a regular graph where each vertex of the graph has the same degree. Now here you can see all the vertices have the same amount of degree, that is the connection between all the other vertices. So the degree of A is 3, so the degree of B is also 3, and the degree of D is C, and similarly the degree of C is also 3. So what I mean to say is all of these vertices have the same degree, that is 3. Now we have the weighted graph. So what is a weighted graph? A weighted graph is where each edge holds some weight that denotes the traversal cost through those edges. Now here you can see that all the edges have a different weight. The edge from A to B has the weight 5, and the edge from A to C has the weight 9, and the edge from C to B has 2, and the edge A to D as 8, and finally C to D as 7. So all these values are the weight or the cost to traverse from A to another vertex. So from A to B we have the cost 5, and A to C we have the cost 9, and similarly C to D we have 7, and so on. Now followed by the weighted graph, we have the connected graph. So what exactly is a connected graph? A graph is said to be connected where each pair in the graph is connected. Followed by a connected graph, we have the disconnected graph. So it is a typical opposite of the connected graph. A graph is said to be disconnected where each pair in the graph is not connected to each other. Now next we have the cyclic graph. So a graph is said to be cyclic if it contains at least one cycle in a graph, that is one complete traversal connection. So A can be traversed again from traveling A to C, C to D, D to B, and B to A again. So this type of a graph is called as a cyclic graph. Now next we have the acyclic graph. So it is the typical opposite of the cyclic graph. So here you cannot traverse to A again by traversing from A to C, C to D, and there is no connection between D to B. So the complete cycle is not available here. This type of graphs are called as acyclic graphs. So moving ahead, we have the graph representation. So generally there are two different ways to represent the graph data structure. They are using adjacency matrix and adjacency list. So what is adjacency matrix? So adjacency matrix is a sequential representation. Adjacency matrix is used to represent which nodes are connected to which node. If there is an edge between two vertices, then the value of the corresponding element of the graph is 1, otherwise 0. If there is any weighted graph besides, then zeros and ones, we can store the weight of the edge as that particular number. Suppose that there is a connection between A and B, and it is represented as a weight of 5. Then there is a connection, so we will use the connection as true, but we will not represent it as 1. Instead, we will use the weight, that is 5, to represent it as 5, not as 1. If there is no weight, then we will represent it as 1, and if there is no connection, then we will represent it as 0. Now, undirected graph representation. So here you can see how we have represented a graph. So there is no connection between A to A, that is there is no loop, so the value will be 0. If there was a loop and if it was represented with a weight, then we could have written a weight here. Since we do not have weight, then the no connection is represented as 0 and a connection is represented as 1. We have a connection from A to B, so we have represented it as 1, and similarly to A to C, so and so on. Now, directed graph representation. So the simple difference between the directed and undirected graph representation is we did not have a direction in the previous segment, but here we do have directions. So B is connected to A, but A is not connected to B. So we will write it as 0 because the control is traversing from B to A, but not from A to B. So we need to take care of the traversal of control. So we are representing as 0, and you can see from D to B, we have one connection and the traversal is in the direction of D 2b. So we will have 1 there. So here we have D and B. So we have 1. So in that way, we represent the directed graphs. Next, undirected weight graphs. So this was what we discussed before. Instead of zeros and ones, we will represent the weight here. So we do not have a connection between A to A, so that is 0 as usual, but we do have a connection from A to B, so we have represented it with a number that happens to be the weight of the edge. And remember, we do not have the direction here. This is undirected weighted graph. Now, if it were the directed weighted graph, then we could have seen the direction and represented the number with the weight. Now, after this, let us look into the adjacency list. So what is adjacency list? Adjacency list is a linked representation. In this representation, we maintain the list of its neighbors for each vertex in the graph. Every vertex of the graph contains the list of adjacency vertices. Array of vertices which have vertices indexed by each vertex number for every vertex. The array element points to the linked list of the neighbors of the vertex. So this might be a little complicated to understand, so let us understand this using an example. So directed graph representation implemented using linked list. So this is the directed graph we are using. So you can see that A is not connected to anything, so we have ended the address of next location as X, but B is connected to A and C is connected to A. Similarly, D is also connected to A. So that is how we represent the directed graphs using linked list. Next, we have directed graph representation using array. So A is not connected to anything, so we have represented as 0, and B is connected to B as well as A, so we have 1 there, and C is connected to B, so C is also connected to A, so we have 2 there. D is connected to A, C and B, so we have 3 there. Now we have the graph traversal. So graph traversal refers to the process of examining each edge and vertex in a graph. Graph traversing can be performed in 2 ways. The first one is breadth first search or BFS algorithm. BFS starts traversing the graph from root node and explores all the neighboring nodes. Then it selects the nearest node and explores all the new nodes. Queue data structure can be used in BFS algorithm. So the following image depicts the BFS algorithm working. It chooses the nearest node first, then it traverses to all the other nodes. So followed by BFS algorithm, we have the DFS algorithm, that is the depth first search algorithm. DFS starts traversing a graph from the initial node of the graph and then it goes deeper and deeper until it finds the node has no child. Then backtrack from the dead end towards the recently explored nodes. Stack is used for BFS algorithms. So this particular GIF image can be considered as the graph traversal which is performed using DFS algorithms. So if you don't know much about DFS and BFS algorithms, don't worry about that. Those particular tutorial videos are added in the description box below. You can go through it and understand BFS and DFS algorithms in a much better way. Now we will go through some of the applications of graphs. So some of the major applications of graphs are used in the websites, Google Maps, and social media websites like Facebook, and some security systems, and also software programming.
Hello everyone, welcome to Simplilearn's YouTube channel. Today we will be discussing about Krushkal's algorithm in data structure. In today's video, we have a challenging activity for you guys. So stay tuned and do participate in formulating answer to the question that is going to pop up on your screens in next few minutes. But before we begin, let me tell you guys that we have daily updates on multiple technologies. So if you are a tech geek in a continuous hunt for latest technological advancements, then consider getting subscribed to our YouTube channel and don't forget to hit that bell icon to never miss an update from Simplilearn. Now without any further ado, let's get started with the agenda for today's discussion. We will start this discussion with introduction to Krushkal's algorithm. Followed by that, we'll understand how we can create a minimum spanning tree for a given graph using Krushkal's algorithm. And finally, we will cover the coding implementation of Kruskal's algorithm using disjoint sets. I hope I made myself clear with the agenda. Now let's get started with our first topic, Introduction to Kruskal's algorithm. The Kruskal's algorithm is used to find the minimum spanning tree for a given graph. But what exactly is a minimum spanning tree or MST? Well, a minimum spanning tree is a subset of graph G having the same number of vertices as of graph G and edges equivalent to number of vertices minus 1. Along with these properties, it also has a minimum cost for the summation of all edge weights included in a minimum spanning tree. If you want to learn more about spanning trees, then please consider watching our video, which you can find in the I button section right away. Now coming back to the Kruskal's algorithm, the Kruskal's algorithm sorts all edges in increasing order of their edge weights and keeps adding nodes to the tree only if the given edge does not form a cycle. Also, it picks the edge with minimum cost at first and the edge with maximum cost at last. Hence, we can say that the Kruskal's algorithm makes a locally optimal choice intending to find global optimal solution. That is why it is also considered as greedy algorithm. The data structure that we are going to use for implementing this Kruskal's algorithm is union find. But now you must be thinking, what exactly is this union find data structure and how it works? Well, union find is a data structure that keeps tracks of elements that are split into one or more than one disjoint sets, where a disjoint set is collection of two distinct groups or clusters that do not have single common element. The union find features two important operations named as find and union. The operation find returns the set or group to which provided element belongs. Basically, it constructs a bijection between the object provided and its set, whereas the union function joins two distinct disjoint sets to create a single subset. Let's understand how this data structure works with the help of real-life example. Let's say we have some singing magnets placed on table with a higher magnetic affinity towards each other. All these singing magnets present on the table are color coded with sky blue color. Now, due to the high magnetic attraction, the magnets A to E will form a strong magnetic field which will cause the bonding or connection of all these magnets. As a result, all these magnets will be grouped together. We will now color code this set with red color. Along with that, we'll also call this set as red. After that, the magnet F to I are also closer to each other. Thus, they will also form a connection. We'll call this set as green. Finally, this last set of magnets will also formulate a connection with each element inside a group. We will call this group as set purple. All these distinct magnets got distributed into three different disjoint sets. But as the magnetic attraction between these groups increases significantly, hence all these clusters of magnets will end up connecting with each other. This scenario can be related to the union function. Union function merges different sets into a single subset where the find operation helps in extracting the group of element to which the particular element belongs. Similarly, in this scenario, a particular magnet can be traced back to its group with the help of color code that we have maintained alongside the magnets. The use of union find in Kruskal's algorithm can be related to this example. While implementing Kruskal's algorithm, we are going to maintain three distinct disjoint sets. The first set will store edge weight values for all edges in a graph, whereas the second set will store tree hierarchy for a different nodes. The last set will store the ranks for all nodes included in an MST. By using the union find structure and its operation, we can justify the entry of each edge into the spanning tree, which we will explain in the implementation of this algorithm. But let's understand the functioning of this algorithm primarily. The Kruskal's algorithm begins with sorting all edges into increasing order of their edge weights. This sorting is done to include edges with the least edge weight primarily into the tree structure. After that, we'll pick the first smallest edge and we'll check if it generates any cycle in the tree structure or not. If it does not form any cycle, then we will include that edge into our spanning tree. Otherwise, we will discard it. We will keep repeating this process until mod of v minus 1 edges are included into our MST, where v is number of vertices. Now moving ahead, let's discuss how we can create a minimum spanning tree using Krushkal's algorithm. This given graph GVE contains 12 edges and 6 vertices, and we are supposed to find out G dash such that the number of vertices is equal to 6 and the number of edges is equal to V minus 1, that is 6 minus 1, which is equal to 5. The one more condition that the formulated structure must abide by is that the summation of all included edge weights must be the minimum possibility for this spanning tree. Going forward, we'll discuss how we are going to create MST for this graph using Krushkal's algorithm. The first step that we need to perform is removing all the loops or parallel edges from our graph. Hence, primarily, we'll remove these two present loops. The next step that we are going to perform is arranging all the edges in increasing order of their weights. The reason behind maintaining the sorted list is to make sure that the first edge for insertion is of a minimum cost. Here, I have maintained the sorted list for all the edges that are part of our graph. So according to this sorted list, the first edge that we are going to insert in our MST is edge EF, as it has minimum weight cost, that is 2. The next edge that we have in our sorted list is edge FD. It also has an edge weight equal to 2. Hence, we'll include it in our spanning tree. The third edge in our sorted list is edge BC with weight 3. The inclusion of this edge does not formulate any circle in our tree structure, hence we'll add it to our MST. The next edge is edge CF, having a edge weight 3. So we'll include it in our MST structure. The fifth edge that we are going to pick is edge CD, having weight 4. But the inclusion of this edge inside our spanning tree will create a loop, and the structure that contains a loop can never be considered as tree. Hence, we have to exclude this edge. The next edge is edge BF, and the inclusion of this edge will also generate a cycle in our spanning tree structure. So, we will exclude this edge as well. The next edge is edge BD. This edge has weight value 6. The inclusion of this edge can also create a loop in our structure, so we'll have to discard this edge as well. The next up is edge AB with a weight value 7. Even though this edge has higher weight value than previous edges, but it does not formulate any cycle in our MST, so we'll include it in our tree structure. By doing that, we have generated V-1 edges for our spanning tree. Thus, we won't iterate further in our sorted list. This generated MST has minimum possible cost for our graph GVE, which is 17. I hope that you guys have understood the MST implementation process using Krushkal's algorithm. Cause in the next slide, I have a problem for all of you guys to assess your understanding of Krushkal's algorithm. The graph shown on your screen contains 10 vertices and 18 edges. And for this graph, you are supposed to generate a minimum spanning tree such that it contains 10 vertices, 9 edges, and minimum construction cost. In order to do that, you can take out your pen and paper to draw the spanning tree structures based on the step that we have discussed till the time. I'm aware that this graph is quite strangely structured. However, if you can solve this problem, you will undoubtedly be able to solve other difficult problems out there. And of course, if you are confused about any step, then you can reiterate through the session. But here I am going to give you guys a little moment to figure out your answers. Well, Now that you guys must be ready with your solution, so let's check if it is true. The highlighted part of this graph is possible structure for a spanning tree with minimal cost. By removing all the edges, the MST will look something like this. I hope you guys have got the right answer. On that note, let's dive further and discuss the implementation strategy for Krushkal's algorithm. While implementing the Krushkal's algorithm, primarily we'll generate a C structure for keeping track of the source and destination node along with its weight. After that, we'll sort all that edges of a graph in increasing order of their edge weights. Moving ahead, we'll create three distinct sets to maintain nodes of a graph, their hierarchy in tree, and corresponding ranks for every node. For each insertion of an edge in MST, we'll update the rank and parent of each node. If the two nodes have the same parent node, then we will not insert the edge joining them, as it will generate the cycle in tree structure. Let's understand all these steps with the help of an example. This is the graph structure for which we'll try to generate a minimum spanning tree using C programming language. As discussed earlier, primarily we'll create a sorted list of all edges in increasing order of their edge weights. The list will contain the source node, destination node, and corresponding edge weight for that particular edge. Along with that, we are going to maintain disjoint sets to carry out union operation. Those disjoint sets are parent and rank, and they will include rank value and parent value for every node in our graph. Initially, all the nodes are in their own different sets. Hence, we'll set their parent values to -1. Also, the ranks for these nodes will be initialized to 0 at the beginning because we haven't included them in our minimum spanning tree. Having said that, let's include the nodes of our graph in our MST. In upcoming slides, we'll traverse through our list of edges to include them in our minimum spanning tree. Now, the first edge that we are going to check is edge DC, which have minimum edge cost, that is 1. In order to insert this edge in our MST, we'll need to find the absolute parent of node D and C as well. So let's check out the parent set to determine the absolute parent value of node D and C. The parent value of node D is -1 and parent value of node C is also -1. Both of them are having same ranks, which means either we can make node D point to C or node C point to D. Here, I'll assume that node D points to node C. So, if node D is pointing to node C, then the parent of node D will become node C. And as C becomes the parent of node D, the rank of node C will change. Remember, whenever two disjoint tree structures are joined together, then the rank of one being pointed to will increase by 1. Hence, the rank of node C will become 1 now. Once the disjoint sets are updated, the union operation will generate the link between node D and C. Now, we'll process the second edge in our list, that is edge CB having weight 2. Primarily, we'll check the parent values of both these nodes. Node B and node C have parent values -1 and -1, which indicates that these nodes are absolute parent of their own sets. Since they have different absolute parents, we can join both of them. However, the rank of node C is higher than node B, thus the connection should point from node B to node C. As node B is pointing towards node C, thus node C will become the parent of node B as well. Hence, we'll update the corresponding absolute parent values for them. Next up is edge BA with the weight value 2. Now the parent value for node A is -1 and the parent value for node B is C. So both of them have distinct parent value, which implies that we can establish a connection between them. For that purpose, we'll have to update the rank field. And as the parent of node B is node C, the rank of C will definitely increase by 1. Once the fields are updated, the edge will get included in our MST. On that note, we have generated our minimum spanning tree. But you must be thinking about how our algorithm will discard the other edges. So to understand that, we'll traverse further in our list of edges. The next edge is edge AC, and the parent of node A is node C itself. Hence, we'll discard this node as well. Now the final edge in our list is edge AD, and again both these nodes have the same parent node. Thus, we'll discard this node as well. Now, you must be thinking about how we can limit iteration of the whole list if we formulate MST using the few topmost edges only. Well, the answer to that is pretty straightforward. We can avoid the complete traversal of the list by using looping condition from E is equal to 0 to E is equal to mod of V minus 1. When we use this condition, the looping will stop when V minus edges get included in our MST. Now the next up is the time complexity analysis of Krushkal's algorithm. The time complexity of Krushkal's algorithm will be big O of E log E plus E log V. The E log E for sorting all edges and E log V for finding the edge from maintained 3 sets. The average time complexity graph for this implementation will be something like this. It will be of parabolic nature. I hope that you all have understood the strategy for implementing Krushkal's algorithm. So, without wasting any time further, let's visit the code editor to develop a program in C programming language for Krushkal's algorithm.
If getting your learning started is half the battle, what if you could do that for free? Visit SkillUp by Simplilearn. Click on the link in the description to know more.
Now, to begin with coding implementation, the first thing that we'll do is we'll create a storing system to represent a weighted edge. For that purpose, we'll use structure in the C programming language. So let's get started with that. Struct edge, and inside this structure we'll create int source, destination, and weight. Now what we'll do is we'll utilize this structure to store the edges of the graph. Moving ahead, we'll also initialize the structure for storing the complete graph. So let's create one more structure and we'll name the structure as graph, and inside this graph structure we'll create node. We'll also create variable e to represent number of edges in our graph. We'll also call the reference of structure edge to this graph. By doing this, we'll be able to include all the edges into our graph structure as well. So let's create that reference struct edge star edge. Now we have successfully created the structure for graph. Now moving forward, what we'll do is we'll assign dynamic memory to the reference of graph structure. For that, what we'll do is we'll write code struct graph star generate graph, and inside this function we'll pass int node and the number of edges, that is e variable. Now we'll write body for this function, and inside body, first thing what we'll do is we'll create the space, that is dynamic memory space for this graph structure. Equal to struct graph star malloc size of struct graph. Graph dot node will be equal to node and graph dot number of edges will be equal to E itself. Next, what we'll do is we'll allocate a memory to each edge. Okay, add an underscore here. For that, what we'll do is we'll use struct edge star malloc size of struct age and finally we'll return the graph. Now we have successfully allocated memory space to our graph and individual edges as well. So moving forward, what we'll do is we'll initialize one more structure to store the parent array and rank array. Basically, these are the disjoint sets whose usage will allow us to generate a spanning tree using union find algorithm. So let's get started with that. We'll create another structure and we'll name this structure as tree underscore maintenance underscore set, and inside this structure we'll create parent array and rank array. Now we have created the tree maintenance set structure, so let's generate an union find algorithm for maintaining MST structure. In order to do that, let's create a function named find disjoint set first. So this find disjoint set function will be of int data type find underscore disjoint set, and inside this we'll pass struct tree underscore maintenance underscore set and its object subsets and a variable int I. Inside this function, we'll use if case to find root and make it as a parent of argument I. Also, if it is -1, then we'll need to update it. For that, we'll keep recurring through this if block by calling the function find disjoint set inside if block. So let's do that. If subsets I dot parent is not equal to I, then what we'll do is we'll get inside this if block and we'll execute subsets I dot parent is equal to find underscore disjoint set, and will again pass same argument subsets comma subsets I dot parent. And finally we'll get out of this if block and will return subsets I dot parent. Now we'll create a function for union operation. Let's name this function as void union underscore disjoint set, and inside this we'll pass struct tree underscore maintenance underscore set and its object subsets, and we'll pass argument x and argument y. Now inside this function we'll create two variables named xroot and yroot, and the xroot variable will store the return data from find disjoint set when the x has been passed to the function, and similarly the yroot will store the return value for find disjoint set given y as an argument. So let's write command for that. Int xroot will be equal to find disjoint set, and objects will be subsets comma x. Similarly int yroot will be equal to find disjoint set and object subsets and variable y. Now, in order to build connection between these nodes, as discussed previously, the node with lowest rank value should always be pointing to the node with highest rank value and vice versa. So we'll have to use this if block in order to put this condition in the connection building block of our program. So we'll write condition for that here now. If subsets xroot dot rank is less than subsets yroot dot rank, then what we'll do is we'll set subsets xroot dot parent to yroot. That means okay. So what we are doing here is we are checking the rank value of x root. If the rank value of x root is smaller than y root, then what we'll do is we'll simply set the y root as parent of x root. I hope you guys are clear with this. Now moving forward, we'll write else if part of this condition, else if subset x root dot rank, sorry, I'll have to add s here, and if subsets x root dot rank is greater than subsets y root dot rank, then what we'll do is we will set subsets y root dot parent is equal to x root. Otherwise, if both above mentioned condition fail, then what we'll do is we'll add one more condition. We'll set subset y root dot parent to x root, and then we set subset x root dot rank to incrementation. There is one mistake over here. Subsets, okay. So now we have implemented the union find algorithm for this Krushkal implementation. Next, we'll create a function to sort the list of edges in our graph according to increasing order of their edge weights. So let's create new function for that. We'll name this function as int my comparator, and inside it we'll pass const void star a and const void star b, and we'll create function body. But before we get started with coding implementation of this myComparator function, I want to talk about arguments of this function. So basically a and b are constant quantifiers. The significance of this quantifier is to tell the user that you cannot modify this pointer and the location it is pointing to throughout the program. So let's get started with the coding part of this myComparator function. What we'll do is we'll create struct age star a1 is equal to struct age star a semicolon, and similarly struct age star b1 will be equal to struct age star b. Next, we'll return the output a1 dot weight. It's greater than b1 dot weight. So basically what this statement will do is, if the weight value of a1 is greater than b1, then it will return a1 as output, and if the weight value of b1 is greater than a1, then it will return b1. I hope you guys are clear with this myComparator function. So moving forward, we'll finally create a Krushkal MST function. The return type of this function will be void, and we'll name this as Krushkal MST, and inside it we'll pass argument struct graph star graph, and we'll create function body. Now the first thing that we'll do here is we'll assess the value of number of nodes in a graph, and after that we'll generate a new reference of structure age for storing our MST. So the first thing, we'll get the node to graph dot node and struct age result node. Along with it, we'll also initialize variable e and variable I equal to 0. So int e is equal to 0 and int I is equal to 0. We'll need to break the indentation here and here as well, and semicolon. So basically these variables will store index values for result and index variable for the sorted list simultaneously. Now moving forward, we'll sort all the edges of a graph. If we are not allowed to change the given graph, then we can create a copy of the given graph. The function named qsort allows us to do that. So let's create that qsort function here. Qsort graph edge comma graph e comma size of graph h 0. So this qsort is nothing but C standard library function that implements a polymorphic sorting algorithm for arrays of arbitrary objects according to a user provided comparison function. And that comparison function is nothing but this myComparison function. And I guess you guys must be with this qsort term. So let's add comma here, and we'll give call to a myComparator function. Now moving forward, we'll break the indentation and we'll call the object of tree maintenance set underscore maintenance set star subsets equal to struct tree underscore maintenance underscore set star malloc node star size of struct tree underscore maintenance underscore set and we'll add semicolon here. So next we'll create subsets equal to number of nodes, and after that we'll make sure that all the elements have the rank value equal to 0, and to do that we'll initialize new for loop. So let's create for loop here. We'll begin it from v is equal to 0 to v is less than node and we'll set this v to incrementation. After that we'll make body for this for loop, and inside it we'll set subsets v dot parent is equal to v and subsets v dot rank is equal to 0. Now moving further, we'll traverse through all the edges in the graph, but we want to limit our traversal to the number of vertices minus 1, and to achieve that we'll create while loop here. While e is less than node, capital node, then node minus 1 and I it's smaller than graph e then create struct age next underscore age equal to graph dot age I plus plus, and here we'll create x and y nodes. So let's do that. Int x will be equal to find underscore disjoint set, and we'll pass subsets comma next age dot source, and for y we'll pass find underscore disjoint sets subsets comma next underscore edge dot destination. Now if including the edge between x and y does not create the cycle in our graph, only then we can include that edge in our MST. For that, what we can do is we'll set if x is not equal to y, then we'll set result e plus plus equal to next underscore edge, and we'll find union disjoint set for subset, and we'll pass x and y as well. With this, we have successfully created our Krushkal MST function. Now what we'll do is we'll also print the structure of our minimum spanning tree. For that, we'll need to create pattern using printf function. So let's do that. The first statement that will print on screen is edges created in MST are as below, and we'll add \n so that our output gets to the next line. We'll add semicolon, and to that we'll add int minimum cost variable, and we'll initialize it to 0. So okay, so what we'll do is we'll create for loop here, and we'll initialize it with iterator element beginning from 0 till I less than equal to e, and we'll iterate this I element. And what we'll do is we'll create pattern for printing the edges. The pattern will go like modulus d dash dash modulus d equal to modulus d slash n, and the parameters that will get printed will be result I dot source comma result I dot destination, and result I dot weight. Okay, so we haven't added comma here. Now this error will get resolved. Now after this, what we'll do is we'll increment this minimum cost variable by adding the values of edges to it. So we'll take this minimum cost variable and we'll add result I dot weight to it. Now we'll get outside this for loop and we'll printf one more statement. The cost for creating MST is modulus D, and we'll print minimum cost. Okay, we have now successfully implemented Kruskal's algorithm function, and we have created code for printing it on console as well. So now moving forward, we'll work on our driver method, and for that let's get into its function body. Here first we'll define the number of nodes that we are going to use for our graph. Those number of nodes are 4. The graph structure that we are going to pass to this Kruskal's algorithm program is the same that we have discussed implementation strategy for. It had 4 edges and it also had 6 edges as well. So we'll add 6 edges here. Now what we'll do is we'll set struct graph star graph equal to generate graph, and we'll pass node comma e, and we'll add semicolon. Now next we'll create graph structure by implementing the edges. So the for first edge we'll call graph dot edge 0 dot source will be equal to 0. That means the first edge will begin from 0 and it will end at destination node, and that will be 1. And the weight for this edge will be equal to 2. Now we'll copy this pattern and we'll paste it below. Okay, and now the edge will be 1, and for this edge 1 the source will be 0 and destination will be 2 and the weight value will be 4. Now let's copy this again, we'll paste it and we'll set edge number to 2. We'll change source and destination. Now source will remain same and destination will be changed. We'll make it 3 and the weight value will also remain the same. That means age between 0 to 2 and age between 0 to 3 have same age weight. Now for next, Control V will remove this indentation, and now we'll change the node number, age number. Here the source will be 1 and destination will be 3, and the age weight value will be 3. After this, we'll add new age. The age number will be 4 now. The source will be 2 and destination will be 3, and age weight will be 1, and the last age will be age 5, and the source will be 1 here and destination will be 2. The age weight will be 2. Now after this, what we'll do is we'll give call to our Krushkal MST function in order to generate minimum spanning tree, and we'll pass this graph structure to it, and we'll add return 0 statement. With this, we have successfully completed our programming implementation for Krushkal's algorithm. So let's run it and check if our code is working fine or not. Okay, so we are getting 3 problems here. The first one is expected token. Oh, so int node will be equal to graph.node, and this node should also be capital here. Okay, so what next error is there? Yeah, so now our code is bug free. Oh, but some exception is happening here. We'll jump this exception. We'll try to jump it. Okay, but we are not having any errors into our system, so I think that's the compatibility issue with our VS Code. So let's copy this code and paste it into the virtual coding environment, and we'll check it if this code is working fine or not. So we'll copy the code and we'll go back to the Google Chrome. We'll go to the online compiler tool, and here we'll paste our code and we'll run it. Okay, so here we are getting our output. So there will be only 3 edges that will get formed in our minimum spanning tree, and the cost for all those edges will be 5. I hope this coding implementation is clear to all of you out there. If you're concerned about this code, then don't be, as we can send it over to you if you drop your email IDs in the comment section below. So drop your email IDs in the comment section below in order to receive this code.
Hey everyone, I am Vaibhav Khandelwal and I welcome you all to Simplilearn's YouTube channel. In this session, we will discuss backtracking algorithm. We shall begin our session by introducing backtracking. Then we will discuss the n-queens problem to understand the backtracking in detail. After that, we will implement the n queens problem in the code editor. Finally, we will sum up what we have learned from this session. But before we begin, make sure you have subscribed to our YouTube channel and clicked on the bell icon below, so you never miss an update from Simplilearn's YouTube channel. So without any further ado, let's get started with an introduction to backtracking. Backtracking is an algorithmic method of alternately solving a problem. To explain the issues, it employs a recursive approach. Backtracking is required to find every possible combination to solve an optimization problem. Backtracking is used in solving various problems like n-queens, knight's tour, the rat in the maze problems, and so on. Now, to get better understanding of backtracking, let's have a brief look at n-queens problem. Let's say we have 4x4 matrix. We have to place 4 queens in that. Every row and column has exactly one queen and none of them falls under the same diagonal. We will start with the leftmost column. Then we will check our base condition that if we have placed all the queens or not. Now we will try every row in this column. If we found a location where the queen can be safely placed, then we will mark it as a part of an answer. And then we will recursively check if placing queen here will lead us to the solution or not. If yes, then we will return true. Otherwise, if false, then we will backtrack and try other rows and repeat these steps. If all rows have been tried and nothing worked, then we will return false to trigger backtracking. Now let's implement this n-queens problem in the code editor. We will define a vector. Inside a vector, it will be an int vector result. Now we will write a utility function to check if the queen can be placed on board. So it will be a boolean function. Bool is safe. As argument we will place a vector inside a vector int board comma int row comma int column. We'll define int I comma j int n will be equals to board size. Now we will check if this row on the left side. So for loop I is equals to 0, I less than column, I plus plus. If board at row I then we will return now we will check upper diagonal on left side. So for I is equals to row comma j is equals to column. j greater than equals to 0 and I greater than equals to 0, I minus minus, comma, j minus minus, if board I, comma, j then return. Now we will check lower diagonal on left side. So for I equals to row, comma, j is equals to column, I less than n and j greater than equals to 0, I plus plus, comma, j minus minus. Now if board at I and j will return, else we will return. Basically, what we have done in this function is we have checked that row and the right diagonal and the left diagonal so that no queen can overlap. Now, next, we will write a recursive utility function to solve n queens problem. So, bool solve nq. Its argument will be vector inside a vector int ampersand board comma int column. Now we will first check our base case if all queens are placed. So int n is equals to board size if column is equals to n. Then we will define a vector int b. So for int I is equals to 0, I less than n and I plus plus. Another nested for loop int j is equals to 0, j less than n, j plus plus. If board at I and j is equals to 1. Then v dot push back j plus 1. Now we will print result dot pushback and we will return true. Now we will consider this column and try placing this queen in all rows one by one. So boolean res is equals to false. Now for loop and I is equals to 0, I less than n, I plus plus. Now we will check if queens can be placed on board I and column call. So if is safe board I call if it's safe, then we will place this queen at that position. So board I call is equals to 1. Now we will make result true if any placement is possible. So res is equals to solve enqueue at board comma call plus 1 or res. Now if placing queen in board I call doesn't lead to a solution, then we will remove the queen from the board I column and backtrack. So board Now if queen cannot be placed in any row in this column, then we will return false. So return plus now this function solves the n-queen problem using backtracking. It is basically using solve enqueue to solve the problem. It returns false if queen cannot be placed, otherwise returns true and print placement of queens in the form of ones. Now, there may be possibility that there are more than one solution. Then this function will print one of the feasible solution. Vector write a vector and queen and n result dot clear. Now we will call vector inside a vector board n comma vector int bracket n comma 0 now if solve nq at board comma 0 is false, then we will return empty set otherwise we will sort result dot begin comma result dot end. And we will return result. Now we will write the main block. So int n is equals to 4. So for vector inside vector int v will be equals to n queens at n. So we will write for loop auto ar v we will call cout then for loop auto itr AR, Cout, ITR, and Cout. And then we will return 0. Now let's run this code. As you can see, we are getting 2 answers. Now this n-queen can be solved with both of these answers. Now let's get back to our slides. At last, let's sum up what we have learned in this session. First up, backtracking is simple to implement and has fewer lines of code. Most backtracking codes are composed of few lines of recursion function code. Next, since we use recursion, the function information is stored on the stack, which has high space complexity. Next, when the branching factor is significant, it is very time consuming in many cases. Finally, many problems such as knight's tour, n-queens, rat in the maze, subset sum problem, and so on can be solved using backtracking.
Hello everyone, welcome to Simplilearn's YouTube channel. Today we will be discussing about spanning tree in data structure. But before we begin, let me tell you guys that we have daily updates on multiple technologies. If you are a tech geek in a continuous hunt for the latest technological advancements, then consider getting subscribed to our YouTube channel and don't forget to hit that bell icon to never miss an update from Simplilearn. Now let's get started with the agenda for today's discussion. We will start this discussion by understanding the importance of spanning tree and with the help of an application. Followed by that, we will deal with what is graph and data structure and their different types. Advancing ahead, we will understand what a spanning tree is and how it works. Once we are done with that, we will look into some essential properties of the spanning tree. And finally, we will cover the applications of a spanning tree to understand how we utilize this data structure in our daily lives. Now, let's get started with our first topic, which is understanding the importance of a spanning tree. We will have a look at an application of the spanning tree to understand it better. Meet Patrick. Patrick works as a head of the network administration department in an IT solution company named as Gray Solutions. Being the head of network administration department, Patrick is responsible for managing his team to keep the organization's computer network up to date and operate it as intended. Network administration department coordinates and connects multiple systems in the company to a single network using multiple routers. This network is called as local area network or LAN, which is created for the sole use of an IT company. But in the last few days, something went wrong in the network management system which came to Patrick's notice. He observed that the network loop is formed in a routing system. A network loop occurs when multiple routes carry information from the same source to various computing devices. And due to this formation of a network loop, the network connectivity started slowing down initially. After a few hours, the network connectivity completely went down and all the operations of the company stopped abruptly. Now Patrick and his team needed to do something in order to resolve this problem permanently. So Patrick started brainstorming to find out an optimal solution to fix this problem. One of Patrick's teammates was good at data structures and he came forward with an idea to implement a spanning tree data structure for managing the routing connections. He suggested replacing the old naive routing strategy with a minimal spanning tree routing. After listening to this idea, the whole network administration team started working on implementing a spanning tree. While doing that, they treated the network connection as a graph. The routers and end devices like computers, fax machines were treated as the nodes of the graph, where the connecting wires carrying network signals were treated as the edges of a graph. But before understanding how Patrick's team was able to solve this problem using a minimum spanning tree, let's first understand the basics of this data structure. This will allow us to get a clear insight into how spanning tree solves network routing problems. So let's start with graph and its different types. Basically, a graph is a structure made of nodes and edges connecting them. And there are 3 types of these graphs based on the types of edges. The first is the undirected graph, the second is the directed graph, and the last is the connected graph. Let's understand these types completely in the upcoming slides. The first type of graph that we are going to discuss is the undirected graph. It is termed as a graph in which all the edges does not point to any specific direction. In simpler words, all the edges of this graph will be bidirectional. As you can see in this particular graph, you can move from any node to any other node and retrieve back as well. Next up is the directed graph. It is a graph in which the edges point to a specific direction. By this, I mean in this type of graph, you can only move towards a single direction. For example, you can traverse this given graph starting from A, then B, then C, then D, and finally E. But here, you cannot traverse back from E to A as this graph is unidirectional. The last type of graph, depending on its edge, is a connected graph. It is defined as a graph with a path from any vertex to any other vertex in the graph. In this particular type of graph, you can reach any vertex from any other vertex in a graph. For example, you can go to node B or D from node A and arrive back at A from either vertex B or D. Now moving ahead, we will understand what a spanning tree is and how we can create it. Mathematically, the spanning tree for any graph G having vertices V and edges E can be represented using superscript notation G' having vertices V' and edges E'. Suppose we intend to create a spanning tree for graph G, then our spanning tree G' must follow a few constraints. The first constraint suggests that the number of vertices for created spanning tree must be equal to the number of vertices of a given graph G. Further, the edges of G' should also be similar to the number of vertices in graph G minus 1. To understand this mathematical formulation clearly, let's have a look at an example. Now, for this given graph G, we have to formulate all possible spanning trees. Remember, a single connected graph can have multiple spanning trees until we fulfill the constraints mentioned earlier. So, for this particular graph G, we have 5 vertices and 5 edges. Additionally, each edge has been assigned with some cost or weight. Let's say this weight represents the distance between the connected 2 nodes. To create the spanning tree G', we need to ensure that G' contains 5 vertices and 5 minus 1, that is 4 edges. Hence, for this graph, we can create a spanning tree like this. You can observe that we have eliminated one node in the spanning tree to remove the loop or cycle in a graph. For this spanning tree 1, we have a cost or value equal to 10. And this cost is nothing but the summation of all edge weights. Now that we have created the first spanning tree for our graph G, I would like to ask all of you to give this a try. For that, I am going to provide you with a short moment to generate all possible spanning trees for the structure that we are discussing right now. You can also pause this video if you need more time in order to do that. So now let's have a look at all possible spanning trees at a glance. We have seen that the value for the first spanning tree was 10. And for this new spanning tree 2, it is 13. In this spanning tree, the edge between vertices B and C is removed. The next spanning tree looks something like this with cost 14. Further, we have spanning tree number 4 with a value 12. And finally, we have the last possible spanning tree 5 with a value 11. Out of all these spanning trees, the value or cost for spanning tree number 1 is the least, which is 10. Thus, this spanning tree will be called as minimum spanning tree. I hope you're clear with the creation of spanning trees. But how can we judge the number of all the possible spanning trees? Well, for that you need to check the structure of your graph. If the graph you have been given with is cyclic, then the number of possible spanning trees will be equal to the number of vertices. The cyclic graph is a graph in which you will have the same number of vertices and edges with a cyclic structure. If the given graph is a complete graph, then the number of possible spanning trees will be equal to v raised to v minus 2. Where v is the number of vertices in a given graph. You can say that the given graph is a complete graph if each pair of vertices is connected by the unique edge. For this particular graph, the number of possible spanning trees will be equal to the number of vertices, that is 4 to the power of 4 minus 2, which is further equivalent to the square of 4. Hence, the number of possible spanning trees for this structure will be 16. Moving forward, let's understand some important properties of spanning tree. We have already gone through some crucial properties while creating spanning trees in the previous section. So primarily, we will list all of them here. The first property of a spanning tree conveys that a connected graph can have more than one spanning tree. The next property states that the number of vertices in spanning trees must be equal to the number of vertices in the given graph, whereas the number of edges is equivalent to the mod of v minus 1. The third property of a spanning tree says that the spanning tree must not contain any cycle. If the structure that you have created as a spanning tree includes a loop or a cycle, then it's clear that you have made a mistake because no tree can contain a cycle. And finally, the fourth property is all about Cayley's formula. If the given graph is a complete graph, then you can calculate the number of possible spanning trees using the formula v raised to v minus 2. The next property of a spanning tree conveys that a spanning tree can never be disconnected. For example, if you create a spanning tree for this given graph which is accurate and you erase one edge, when you do that, the structure will no longer be a spanning tree. It can only be referred to as a disconnected graph. The next property states that if the graph contains more than one similar weight, there is a possibility of having more than one minimum spanning tree. For example, in this particular graph, there are more than one edge having the same weights. Thus, there will be two possible minimum spanning trees with the same cost, that is 7. This is all about the properties of spanning trees. Now that you understood what spanning tree is, you would have also understood how it proves is an effective solution, and that is exactly how Patrick from our story solved his network issue. In a few days, Patrick and his team changed the naive routing into the minimum spanning tree routing. Now, the routing paths are managed by a minimum spanning tree to maintain cost effectiveness and to avoid any looping activity. As we have already understood, MST removes all the loops from a given graph, and we also know that the whole network becomes the graph for which MST will maintain a minimal routing path. Hence, the network system will never experience a network loop again. Due to this amazing initiative, Patrick and his team were appreciated by the whole organization. This example clearly illustrates the importance of a spanning tree and why it is one of the most important algorithms in data structures. Now we will look into the different applications of spanning trees. The first application that we are going to talk about is telecommunication network building. If we want to build a telecommunication network for the whole city and we are putting different connection lines for each customer, then we will have to deal with a huge cost. This naive, ordinary approach is not the best solution to build a connection line. But no worries, this problem can be resolved using the minimum spanning tree data structure. In this case, each customer will be treated as a vertex, whereas the connection line will be treated as an edge. The minimum spanning tree will give us the possible output for generating the telecommunication network. No matter what type of algorithm you are building using machine learning techniques, somewhere down the line you will be using clustering techniques quite liberally. Clustering and data preparation go hand in hand, as many times you will be working at least initially with data sets that are largely unstructured and unclassified. Those data sets cannot be classified using single neuron or classification methods. So you use a clustering algorithm which utilizes a minimum spanning tree to create clusters or groups by mapping distances between data points. The next application of a minimum spanning tree is image segmentation. You must have observed that your face gets detected with the square shape while clicking images in selfie mode. This scenario is happening due to the image detection algorithm developed in the camera system. At the back end, the picture gets fragmented into tiles of similar pixels with the help of a minimum spanning tree. The last application of the spanning tree is its use in calculating the finance factors. A correlation matrix can be created by calculating a coefficient of correlation between any two stocks. This matrix can be represented topologically as a complex network, and a minimum spanning tree can be constructed to visualize the relationships.
Hey everyone, welcome to Simplilearn's YouTube channel. We'll talk about breadth first search algorithm in today's session. Before we begin, make sure that you have subscribed to our YouTube channel and don't forget to hit that bell icon to never miss an update from Simplilearn. So without further ado, let's get started with our agenda for today's session. Our agenda begins with the explanation of what exactly is breadth first search algorithm. Followed by that, we will look into an example of breadth first search algorithm for greater comprehension. First, we'll build a breadth first search algorithm which begins by traversing the root node and then moves on to all the other nearby nodes. The breadth first search approach repeats the procedure for all the nodes until the desired node is found. The queue data structure is the data structure that is used for breadth first search algorithm. For a better understanding, we'll look at an example of breadth first search algorithm. The blue color indicates that the node has been already explored, while the pink color indicates that the node has not been explored yet or visited yet. Next, we'll have our output. We will use a queue data structure to keep track of all the nodes visited and all the nodes that are unvisited. So, to begin, let's look at the algorithm. As a result, we'll have node A, which is added to the output and marked as visited. We must verify all the unvisited adjacent nodes of A, that is node B and node C, and add B and C nodes to the output and enqueue to the queue according to the breadth first search algorithm. Then we'll look at any node between B and C. We'll start with node B. Node D is unvisited adjacent to node B, so we'll add node D to the output and queue. And since node B is now being visited, we'll dequeue it. When it goes to node D, the next unvisited node is node E. Add node E to the output and enqueue to the dequeue. Once node D has completed its traversal, dequeue from the queue. Now, in the case of node E, the adjacent node is node C, which is already visited. Thus, we will dequeue node C from the queue. Now that the pointer is pointing to node C and node F is the next unvisited node after the node C, we will set node F to output and queue. Here, the pointer leads to node F, which has no unvisited adjacent nodes. So, we will dequeue F from the queue and queue is empty. So, we'll come to the halt here. Here's what we got. That is A, B, C, D, E and F. After understanding all the theoretical aspects of BFS algorithm, let's look at the code of BFS algorithm in C programming language. Now, we are on the practical mode. On my screen, you can see an example for BFS algorithm. We have declared a two-dimensional array with maximum row and column size of 10 and two arrays. The first one is a square of a maximum size of 10 and the second one, which is a visited, that stores the maximum size of 10 as well. Some variables n, I, j, and finally we declared front, which is initialized with 0 and rear variables, which is initialized with -1. We perform a loop from index 1 to the size of an array visited in this function, with the condition that if two-dimensional array of column 1 and visited array of index is not 1, we initialize variable I to the front of the queue. Then 1 is set as the front of the queue index of the visited array, and we use the breadth first search function with the vertex as the front of the queue until front is less than or equal to rear. Then we enter the main function, where we define the variable x that stores the graph's vertex, and then we use the printf function to enter the number of vertex that will be stored in variable n. Then we perform a loop from index 1 to queue size and visited array, in which we initialize 0 to the queue and index 1 to the visited array. Then after that, we'll enter the graph value in the form of matrix of two-dimensional array by performing a loop with two variables, I for the graph row and j for the graph column. Then we print the source node, which is saved in the variable x. Then we print the source node, which is saved in the variable x, and we call the breadth first search function or method, which takes a vertex x as parameter, and we print which nodes are reachable by looping from index 1 to the size of the visited array. If index 1 of the array is visited, otherwise breadth first search is not possible. So this was the explanation of the program. Now let's try to execute and see the output. There you go. The program got successfully compiled and now it's asking for the input. Now it is asking for the number of vertices. Let's enter the number of vertices as 3. Now it is asking for us to enter the input in the form of matrix. So the first row will be 1, 2, and 3. So these are the first rows. The next rows will be 2, 3, and 4. So the last row elements are 3, 4, and 5. So we have successfully given all the 3 rows of elements. Now let us select the source node. So the source node would be 2. Now all the nodes that are reachable from the source node 2 are 1, 2, and 3. So there you go. That's how you implement the breadth first search algorithm. Hello everyone. Welcome to Simplilearn's YouTube channel. In this session, we will learn about depth first search algorithm. But before we begin, I would like to tell you guys that we have daily updates on multiple technologies. If you are a tech geek in a continuous hunt for latest technological trends, then please consider getting subscribed to our YouTube channel and don't forget to hit that bell icon to never miss an update from Simplilearn. Now without further ado, let's get started with the agenda for today's discussion. So in this session for today, first we will understand about a brief introduction to depth first search. Followed by that, we will look into an example for DFS algorithm. So I hope I made myself clear with the agenda. Now let's get started with the introduction to depth first search. So what is a depth first search? So basically, a depth first search is an algorithm for traversing or searching the tree or graph data structures. The algorithm starts at the root node, selecting some arbitrary node as the root node in case of graph, and explores as far as possible along each branch before backtracking. So DFS starts with the initial node of the graph, then goes deeper until it finds the goal nodes or the leaf nodes or the nodes that have no children. That is the end part. Here you can see 4 and 7 are the leaf nodes. So the depth first search algorithm runs till the end of all the nodes. That is 8, 10. All these are the leaf nodes or the last goal nodes. In DFS, the backtracking starts once all the nodes are explored. And the DFS algorithm uses stack data structure for its traversal. Now that was a brief introduction to the DFS algorithm. Now for a better understanding, let's go through a practical example. So here we have a graph data structure with elements A, B, C, D, E, and F. So we will be running the DFS algorithm and we will be traversing through all the nodes of this particular graph. And the traversal will be recorded using a stack data structure. And we have 2 different colors which will be used to indicate the element's color. So the black color is for the nodes which are not visited yet, and the blue color will indicate the nodes which are being traversed already. Now this is the stack data structure that we will be using for the traversal, and we have another part which declares or which gives out the output of the traversal of the nodes of this particular graph. Now we will begin with the first one, that is A. Now followed by that we will move ahead to B. Then after B we will go through D. Then after D we have E. Next we have C, and last we have F. So that's how we traverse through the graph using the DFS algorithm. Now for a little more understanding, let's go through a practical example where we will be executing a program for implementing the DFS algorithm. So this particular program on my screen is an example for DFS algorithm. So here we have the structure node. So followed by that we have also the methods which will create the edge and which will also print the graph elements. And finally, we have the main class. Now, don't worry about the code. This particular code segment or the complete code document will be added in the description box below, and you can have access to it and try to run it on your local system and have a better learning experience. Now, without further ado, let's try to run this program and get the output and see how the DFS algorithm gets implemented and traverses through the graph. There you go. The program got successfully executed and we had the graph elements, that is 0, 1, and 2 and 3. So it has visited all the elements, that is 2, 3, 1, and 0 according to the stack data structure, and we have found the output over here. So with that, we have come to an end of this tutorial on DFS algorithm.
Hello everyone, welcome to Simplilearn's YouTube channel. Today we will be discussing about greedy algorithms in data structure. But before we begin, let me tell you guys that we have daily updates on multiple technologies. If you are a tech geek in a continuous hunt for the latest technological advancements, then consider getting subscribed to our YouTube channel and don't forget to hit that bell icon to never miss an update from Simplilearn. Now, without any further delay, let's get started with the agenda for today's discussion. We will start this discussion by understanding the real-life example of greedy algorithm, following which we will deal with the introduction to greedy algorithm. Advancing ahead, we will understand example of the greedy algorithm. Once we are done with that, we will look into the demerits of using greedy algorithms. And finally, we will cover the applications of greedy algorithm to understand how we utilize it in our daily lives. Now, let's get started with our first topic. Here, we will look into the real-life example of greedy algorithm in order to understand it better. This is Alex. He's quite wealthy and intelligent as he works for one of the most reputed IT firms. And this is Alex's best friend Rachel. Rachel is in dire need of $85 right now. However, she needs money in such a quantity that the number of coins is kept to a minimum. So Rachel shared this issue with Alex and asked him for help. Now Alex is thinking about Rachel's issue, which he can easily fix because he has a limitless supply of $50, $20, $10 and $5 coins stashed in various bags. Although this being said, Alex needed to think about the constraint Rachel told him about. He needed to give her money such that the number of coins utilized must be minimal. To do so, Alex began making a list of the various coin combinations in which he could present money to Rachel. However, after a while, he became confused due to the vast number of conceivable combinations. So he decided to use his programming ability to solve real-life problems. Alex developed a program that will provide him with the optimal number of coins that he can present to Rachel. This generated program was iterating through the different possibilities to choose the best solution. At each iteration, the program added the coin of the largest value that was not taking Alex past the amount to be paid, which is $85 in this case. For $85, the largest denomination ID can start giving is $50. Now, ID is still short of $35 to reach the amount so that the next largest coin program can take in as $20. But since the program still requires $15 to meet the threshold, the next highest denomination it can accept is $10, followed by $5. The best part about this program was that it allowed Alex to present $85 in just 4 coins, which is fairly incredible. The vital thing to note here is that after each loop, the program makes a greedy choice, providing the coin with the highest potential value. What I mean here by greedy is that locally optimal choice is picked at every step to reach the global optimum solution. Now moving ahead, we will formulate the idea of greedy algorithms. Basically, a greedy algorithm is based on a problem-solving method that involves making locally optimal decisions at each stage in the hopes of achieving a global optimum. That means at each stage we choose a locally optimal value in the hopes of arriving at the optimum possible end result. Furthermore, this algorithm is an optimization technique that can find either minimum optimum result or maximum optimum result. The best part about this algorithm is that it is simple to understand and implement as well. Additionally, the runtime complexity for this algorithm is pretty reasonable. However, the fundamental disadvantage of this strategy is that we only receive the globally optimum value in a small percentage of cases. Having said that, you must be thinking about when to implement this algorithm for solving particular problems, as it does not always produce globally optimum results. Well, let me tell you guys that we have 2 conditions to judge our problem for implementing greedy algorithms. The first condition is the greedy choice property. This notion states that making locally optimal judgments can lead to the global optimum solution for a given problem. The second condition is about optimal substructure. The problem has an optimal substructure only if an optimal solution to the entire problem comprises the optimal solutions to the subproblems. In simpler words, That means the problem can be split down into multiple subproblems, and the solutions to these subproblems can collectively lead to a solution for the entire problem. If both the above-mentioned properties are satisfied by the problem, then we can create a greedy solution for that particular problem. Moving forward, we will look into the steps for constructing a greedy solution. Finding the substructure or subproblem that can lead us to the final answer is the first step in building a greedy algorithm. Because in this algorithm, we are just trying to operate with local optima to reach the global optimum solution. The second step is about determining the type of solution the given problem can result into. That can be either the largest sum or minimum path. The final step for creating the greedy solution is about creating an iterative process for traversing through local stages and making decisions to reach a globally optimum solution. Now, you might be confused about how we can do that. Well, let's go through an example to understand the approach to implement a greedy solution. The example that we are going to deal with is called the traveling salesman problem, in which a salesman is supposed to reach the destination from a given current location. The representation of cities and paths connecting them is done using graph structure where each node is considered as a city and edges connecting them as paths, having edge weight as the distance between the two cities. Now, in this case, we are supposed to find the minimum path between two cities. So to do that, we will begin from the current arbitrary position. From this node called as starting location, there are 3 possible paths. But the path towards city B has less distance. Hence, we will traverse this edge primarily as it is an optimal local route. We have reached city B now, and from this node we have 2 possible paths, out of which one path directly leads us towards the destination city having distance 20. But the other path leading towards the city F has edge weight value or distance value as 2. Hence, according to the local optimal decision, we will choose the edge connecting cities B and F for traversal. We have reached the city F now. From this node or city, there is only one path leading us to our destination. Hence, we will traverse it. Now we have reached the destination city. The path highlighted in the green shade is the global optimum for this TSP problem. You can verify that by calculating the edge weights for all other possible paths. Since the solution allows us to reach the global optimum by making optimal decisions at the local stage, this strategy to solve the problem will be considered a greedy approach. Now moving ahead, we will look into the demerits of using greedy algorithm. We have learned that the greedy algorithm makes decisions based on local optimum instead of analyzing the broader picture of the whole data. Hence, there is a possibility that the greedy solution might not be the best optimal solution for some problems. For example, consider this traveling salesman problem. In this problem, the highlighted part is a created solution to reach the destination city from the current location using a greedy algorithm. But if you observe this graph, the selected solution is not the global optimal solution for this problem. In contrast, it is the worst generated solution to reach the destination. That is why the greedy algorithm is considered to be prone to correctness issues. Even if the algorithm is correct, proving why it is correct is difficult. Thus, it is deemed to be trickier to solve specific issues. Now, we will discuss about applications of greedy algorithms to understand their importance. The first application of a greedy algorithm is its use for constructing minimum spanning trees. The coding approaches that we use to generate MSTs is based on the greedy algorithm. Both Prim's algorithm and Krushkal's algorithm are known as greedy algorithms as they make decisions based on locally optimal decisions. The next application of the greedy algorithm is its use to implement Huffman encoding and decoding algorithms. The Huffman coding technique is a lossless data compression method. The concept is to give variable length codes to input characters, the lengths of which are determined by the frequency of the related characters. The smallest code is assigned to the most frequently occurring character, whereas the largest code is assigned to the least frequently occurring character. This process is carried out by making local optimum decisions. Hence, it is also considered to be a greedy algorithm. The final application of the greedy algorithm is its use for developing solutions to well-known coding problems. Those problems are the activity selection problem, job selection problem, and fractional knapsack problem. All these problems generate solutions by making decisions at each local stage. So the solutions for these problems can be developed quite easily using the greedy approach.
Hello everyone, welcome to Simplilearn's YouTube channel. Today we will be discussing about Prim's algorithm in data structure. But before we begin, let me tell you guys that we have daily updates on multiple technologies. So if you are a tech geek in a continuous hunt for latest technological advancements, then consider getting subscribed to our YouTube channel and don't forget to hit that bell icon to never miss an update from Simplilearn. Now without any further ado, let's get started with the agenda for today's discussion. We will start this discussion with a brief introduction to Prim's algorithm in data structure. Followed by that, we'll deal with finding MST with Prim's algorithm. And finally, we'll cover the coding implementation of Prim's algorithm using C programming language. I hope I made myself clear with the agenda. Now moving ahead, let's get started with our first topic, which is Introduction to the Prim's algorithm. The Prim's algorithm is used to find minimum spanning tree for a given graph. But what exactly is a minimum spanning tree or MST? Well, a minimum spanning tree is a subset of graph G having the same number of vertices as of graph G and edges equivalent to a number of vertices minus 1. Along with these properties, it also has a minimum cost for summation of all edge weights included in a spanning tree. Prim's algorithm starts with a single node and explores all the adjacent nodes at every step. The edges with minimal edge weights causing no cycles in the graph get selected. Hence, we can say that Prim's algorithm makes a locally optimal choice intending to find global optimal choice. That is why it is called as greedy algorithm. Moving ahead, let's understand how we can find out the minimum spanning tree using Prim's algorithm. Now, given a graph G consisting of vertices V and edges E, we need to construct a minimum spanning tree G' with vertices V' equal to V and edges E' equal to V minus 1, having the summation of edge weights minimal. This particular graph G contains 9 vertices and 12 edges. That means our MST G' will have 9 vertices and 9 minus 1 edges, that is 8 edges. So, with this in mind, let's create an MST for this graph G using Prim's algorithm. The first step in Prim's algorithm is to choose an arbitrary starting vertex. Here, we'll select node A as our starting vertex. Now, the next step in Prim's algorithm is to add new vertices with a minimum edge weight. In this case, from vertex A, we have 2 possible edges for traversal. The edge weight for edge AB is 1, whereas the edge weight for edge AC is 6. So obviously we'll choose vertex B here. Since we have reached vertex B, we will look into the possible edges for adding an edge with minimum weight to our MST. Edge BD have the minimum edge weight, so we'll add it to our MST. Now from vertex D, there is only one edge. Hence, we'll directly add that edge DH into our spanning tree. Now, from vertex H, there are 2 possible paths, out of which the path HI has minimum cost. Thus, we'll add it to our MST. From vertex I, there is only one edge, so we'll directly include it in our MST. Now that I have included vertex G, I'm going to check what connected edges I have from vertex G. But since there is only one edge from vertex G, we'll just insert it on our MST. From vertex E, 2 edges are going to different vertices. So we will choose the one with least edge weight, and that edge is edge EC. Now that I have included node C, I am going to examine what connected edges I have to consider from vertex C. Currently, out of these 2 highlighted edges, I want to pick that edge which has not yet been included in MST and has the minimum edge weight. But the question that arises here is, can I add this edge AC into our MST? Well, we cannot. If we add edge AC to our MST, then it won't remain a tree structure due to the creation of cycle or a loop, which we cannot allow to happen according to the Prim's algorithm. Thus, in this particular case, we'll choose age CF for insertion in our MST. And finally, the summation of age weight for this MST will become 30. Also, till the time, you must have observed that this algorithm chooses the next vertex that offers the most prominent or immediate benefit. It started with an empty spanning tree for maintaining two sets of vertices. The first set was for the vertices included in the MST, and the other one was for the vertices that haven't been included in the MST. At every step, this algorithm considered all the edges that connected the two sets and picked the one with minimum edge weight from the adjacency matrix. A group of edges that connects two sets of vertices in a graph is called cut-in graph theory. So at every step of Prim's algorithm, we find a cut of two sets. One contains the vertices already included in MST and the other containing the rest of vertices. After that, we pick the minimum edge weight from the cut and include that vertex to our MST set. That is why this algorithm is called as greedy algorithm. Having said that, let's dive into the implementation strategy for developing code for Prim's algorithm. The idea behind Prim's algorithm is simple. All the vertices of a spanning tree must be connected. Hence, the two disjoint subsets of vertices must be connected in order to create a spanning tree. And further, these vertices should only be associated with the minimum edge weight to make it a minimum spanning tree. In order to store these vertices and edges, we'll create an adjacency matrix using 2D array in C programming language. Well, the indexes of this 2D matrix will be the vertices, where the values other than 0 will be the edge weights. For indexes 0, 1 and 2, you can clearly see that the adjacency matrix is having value 0. That means there is no recurring connection or loop for these vertices. So primarily, let's add them to our graph structure. For edge 1 to 2, we have the weight value 2. So we will add edge between vertex 0 and 1. After that, we have edge between 2 and 1. The value for this edge weight is 3. So we'll add edge between 1 and 2 and assign 3 as its edge weight. Finally, the edge weight for connecting 0 to 2 is 4. So we'll insert it in our graph as well. In the next slide, we'll discuss the strategy for implementation of a Prim's algorithm. From this example, I hope you are clear with how we are going to maintain a structure of a graph using 2D matrix. In the next slide, we'll discuss the strategy for the implementation of Prim's algorithm. The first step of this algorithm is to maintain a set for keeping track of vertices included in an MST. Once we create the set, we'll assign a key value to all vertices in the input graph. Initially, we are going to set all key values as infinite, and at the runtime, we'll assign weight 0 to the first vertex. By doing that, we choose it as an arbitrary starting vertex. Once done with that, we'll start adding vertices to our minimum spanning tree. For that, we'll pick up a vertex u with minimum weight to insert it into our set. After that, we'll also update the key values for all adjacent vertices of u. On that note, let's visit a code editor to implement Prim's algorithm using C programming language.
If getting your learning started is half the battle, what if you could do that for free? Visit SkillUp by Simplilearn. Click on the link in the description to know more.
Now, in order to begin with coding implementation, we'll need to load some dependencies. For this implementation process, we are going to need a Boolean set in order to keep track of vertices included in our MST. That is why we'll include a standard Boolean library in our program. So, #include std bool.h. Once done with this addition, we'll define a number of vertices that we are going to use in our graph. I'm going to set the number of vertices to 5. So let's do that. #define vertices 5. And if you want to implement MST for a larger graph, then you must set the number of vertices to a more significant number. Now let's move to the main function. The graph that I'm going to use for generating a minimum spanning tree is supposed to be stored inside a 2D matrix. So first let's have a look at that graph. This is the graph for which we want to develop a minimum spanning tree. The first step that we must take to do that is converting this graph into 2D matrix. As discussed earlier, the diagonal values will be null or 0 and other values will be the edge weights between two nodes. So without wasting any time on this, I will directly create adjacency matrix for this graph inside our code editor. This part is about maintaining our graph in form of 2D matrix. Now, after this, we are calling primsmst function which is responsible for generating a minimum spanning tree. So let's do that here. Prims underscore mst, and we'll pass this graph to this function. But we haven't developed any code for this primsmst function, but we'll do that now. So let's create primsmst function void prims underscore mst, and we'll pass graph as an argument. Should be vertices and vertices to make it a 2D matrix. Now inside this function, we'll create an array named key to store key values of all vertices. Int key vertices. Along with it, we'll also initialize the parent in which we'll store our actual MST and Boolean set to keep track of each and every vertex of our graph. So let's create that parent array. Vertices, and we'll create Boolean set for maintaining track of all vertices. Now after this, what we'll do is we'll set the key values of all vertices to infinity, and we'll also make sure that these vertices are not part of our minimum spanning tree set. So for that, we'll create a for loop, and inside this for loop we'll use iterator element I, and we'll initialize this element to 0 till vertices and we'll increase the iterator element I for each loop. Inside this loop, we will set key I to the possible integer maximum value, and in order to use this value we'll need to add one library which is called as limits.h. So we'll add it here, hash include limits.h. Okay. After this, we will also make sure that these vertices are not part of our minimum spanning tree set or Boolean set. So for that, we'll write statement min underscore span underscore tree I should be false. That means empty. And we'll add indentation. Okay. Now in order to choose the arbitrary index, we'll set the key value of our first vertex to 0 so that it will be chosen first in our minimum spanning tree. For that, we'll write statement key 0 should be equal to 0. And as we have chosen vertex 0 as our first arbitrary vertex, so we'll also set the index 0 of the parent array to -1. By doing this, we are ensuring that the index 0 is the root node of our minimum spanning tree. Now, to choose vertices with the minimal key value, we'll create a new function named least key. So let's do that. Int least underscore key, and inside it we'll pass arguments int key, boolean set, and inside this function body we are going to set all key values to infinity. So let's do that. Int list will be equal to int underscore max, and we'll also initialize minimum underscore index as new variable. Now using a for loop, we'll traverse through all vertices. If the given vertex is not present inside the minimum spanning tree set and the key value is also smaller than the least value, then we'll set the least variable to the key value and minimum index to that particular index v. So let's create that for loop, and inside it int v as iterator element, and we'll initialize it to value 0. And the maximum limit for this v will be vertices, and we'll increase the value of this small v variable ++. Now if the chosen vertex is not present inside minimum spanning tree set, and the key value for that vertex is also smaller than list, then we will set least equal to key of v and minimum index to v, and we'll get out of this for loop and we'll return the minimum index value. On that note, let's arrive back at our primsmst function. Here, using a for loop, we'll fetch the minimum index that we have generated inside a least key function. So let's create for loop. We'll use count variable here, and we'll initialize it to 0, and we'll move this count variable till vertices -1, which is nothing but the number of vertices in our minimum spanning tree. Next, will increase this count variable. Now we have arrived inside this for loop body. Now we'll store that fetch minimum index value in variable u. So int u will be equal to least underscore key, and we'll pass key and boolean set, that is min underscore span underscore tree, and we will include this least node, that is u, to our minimum spanning tree set or boolean set, equal to true. Now here we'll use a nested loop in order to insert a complete edge which is initiating from node 0. Inside this loop, we'll further call if log to validate some conditions. So let's create that nested for loop first. Int v is equal to 0 to v till vertices v plus plus and inside this for loop we'll add if log and we'll check graph u to v and mean span tree v is equal to false, and graph u v is minimum than key of v, then what we'll do is we'll set parent of v to u and key of v to graph u v. So now you must be thinking about what exactly is this code is doing. So actually what we are doing is we are inserting node u into our minimum spanning tree. And once we include node u into our minimum spanning tree, then we check if there is any edge between u and v. V is nothing but all the vertices inside the graph. If there is edge between u and v, then we check if that v is included in our spanning tree or not. If it is not included, then we check the key value of v. If the key value of v is greater, then what we do is we set parent of v is equal to u and key value of v is equal to graph uv, which is nothing but the weight between edge u and v. So that's what this code is doing. After this, what we'll do is we'll write one printf statement. So for that, we'll need to get out of this for loop and we'll write printf statement. Printf created spanning tree for given graph is \n so that this next part comes inside the next line, and we'll also make a call to print underscore prims mst function, which is not created yet, but we'll write code for it once done with this call, and we'll pass parent and graph to it. Well, now let's create a code for this print prims mst function. Int print underscore prims mst, and will pass int parent, will pass int graph with vertices and vertices. Now inside this function, what we'll do is we'll write one printf statement to show the pattern of printing edge /t wait /n semicolon, and in next slide we'll create iterator element and we'll initialize it to 1, and we'll extend this till vertices and I++ printf modulus d dash modulus d /t \t modulus d and \n, and we'll pass parent I, graph I and parent of I. This statement will print a graph on our screen, but here is one mistake that I have made. I haven't added the indentation for this for loop. Okay, I think this should be fine now. We can say that our coding implementation is finished. Now let's run our code and check if it is working or not. Well, we have received output on our console here. That means our code is bug free and it works fine. You can verify this result by drawing the spanning tree of output on your notebook, and further you can compare it with the graph that we have shown previously. Furthermore, if you're concerned about this code, then don't be, as we can send it over to you if you drop your email IDs in the comment section below. Additionally, you can also try to run it on your local system to understand its minute implementation details and implications. So with this successful coding implementation, we came to the end of this video.
And with that, we have come to an end of this tutorial on data structures and algorithms. If you have any queries regarding any of the topics covered in this session, or if you need the codes that we executed in this particular tutorial, then please feel free to let us know in the comment section below. Our team of experts will be happy to resolve all your queries. Until next time, thank you, stay safe and keep learning.